Hello everyone and welcome to this amazing video on Deep Learning Full Course for Beginners by Simplilearn. Before we begin with the video, if you enjoy watching these kind of videos and find them interesting, then subscribe to our YouTube channel because we bring the best videos for you daily. Also hit the bell icon to never miss any updates from Simplilearn. So let's go through the agenda for this video real quick. We'll brief you with a detailed introduction to deep learning, covering the data source and neural networks. After that, we'll see the difference between AI, machine learning, and deep learning. After that, we'll take you through the roadmap of deep learning engineering, followed by deep learning with Python. We'll also walk you through some amazing concepts like PyTorch versus TensorFlow versus Keras, the difference between TensorFlow 1.0 and 2.2, and many more such concepts. After that, we'll see what GANs are, followed by CNN and RNN in deep learning, and computational graphs in deep learning. Finally, we'll cover some essential deep learning projects you can mention in your CV to make it stand out from the crowd in your upcoming interviews. Speaking of interviews, we have covered you along with the most frequently asked deep learning interview questions to help you crack the most challenging interviews. Before we move on to what deep learning is, if you are an aspiring AI and machine learning engineer, then there's no better time to train yourself in AI and machine learning. If you're looking for a course that covers everything from the fundamentals to advanced techniques, then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. Boost your career with this AI and ML course delivered in collaboration with the Purdue University and IBM. Learn in-demand skills such as machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, ChatGPT, and many more. You will receive a prestigious certificate and Ask Me Anything sessions by IBM. With 5 capstones in different domains using real data sets, you will also gain practical experience. Masterclasses by Purdue faculty and IBM experts ensure top-notch education. Simplilearn's Job Assist helps you get noticed by leading companies. This program covers statistics, Python, supervised and unsupervised learning, NLP, neural networks, computer vision, GANs, Keras, TensorFlow, and many more such skills. Admission to this postgraduate program in AI and machine learning requires a bachelor's degree with an average of 50% or higher marks, along with basic understanding of programming concepts and mathematics. And candidates with 2+ years of work experience are preferred to enroll in this program. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below. So without any further delay, let's hand over this session to our training expert.
Further ado, let's get started. So deep learning is considered to be a part of machine learning. So this diagram very nicely depicts what deep learning is. At a very high level, you have the all-encompassing artificial intelligence, which is more a concept rather than a technology or a technical concept, right? So it is more of a concept at a very high level, artificial intelligence. Under the hood is actually machine learning and deep learning. And machine learning is a broader concept, you can say, or a broader technology. And deep learning is a subset of machine learning. The primary difference between machine learning and deep learning is that deep learning uses neural networks and it is suitable for handling large amounts of unstructured data. And the last but not least, one of the major differences between machine learning and deep learning is that in machine learning, the feature extraction or the feature engineering is done by the data scientists manually. But in deep learning, since we use neural networks, the feature engineering happens automatically. So that's a little bit of a quick difference between machine learning and deep learning. And this diagram very nicely depicts the relation between artificial intelligence, machine learning, and deep learning. Now, why do we need deep learning? Machine learning was there for quite some time and it can do a lot of stuff that probably what deep learning can do, but it's not very good at handling large amounts of unstructured data like images, voice, or even text for that matter. So traditional machine learning is not that very good at doing this. Traditional machine learning can handle large amounts of structured data, but when it comes to unstructured data, it's a big challenge. So that is one of the key differentiators for deep learning. So that is number one. And increasingly for artificial intelligence, we need image recognition and we need to process, analyze images and voice. That's the reason deep learning is required compared to, let's say, traditional machine learning. It can also perform complex algorithms, more complex than, let's say, what machine learning can do. And it can achieve best performance with the large amounts of data. So the more you have the data, let's say reference data or label data, the better the system will do, because the training process will be that much better. And last but not least, with deep learning, you can really avoid the manual process of feature extraction. Those are some of the reasons why we need deep learning. Some of the applications of deep learning. Deep learning has made major inroads, and it is a major area in which deep learning is applied is healthcare. And within healthcare, particularly oncology, which is basically cancer related stuff. One of the issues with cancer is that a lot of cancers today are curable. They can be cured. They are detected early on. And the challenge with that is when a diagnostics is performed, let's say an image has been taken of a patient, to detect whether there is cancer or not, you need a specialist to look at the image and determine whether the patient is fine or there is any onset of cancer. And the number of specialists are limited. So if we use deep learning, if we use automation here, or if we use artificial intelligence here, then the system can, with a certain amount of the good amount of accuracy, determine whether a particular patient is having cancer or not. So the prediction or the detection process of a disease like cancer can be expedited. The detection process can be expedited, can be faster without really waiting for a specialist. We can obviously then, once the artificial intelligence detects or predicts that there is an onset of a cancer, this can be cross-checked by a doctor. But at least the initial screening process can be automated, and that is where the current focus is with respect to deep learning in healthcare. What else? Robotics is another area. Deep learning is majorly used in robotics, and you must have seen nowadays robots are everywhere. Humanoids, the industrial robots which are used for manufacturing process. You must have heard about Sophia, who got citizenship with Saudi Arabia, and so on. There are multiple such robots which are knowledge oriented, but there are also industrial robots that are used in industries, in the manufacturing process, and increasingly in security and also in defense. For example, image processing. Video is fed to them and they need to be able to detect objects, obstacles, and so on and so forth. So that's where deep learning is used. They need to be able to hear and make sense of the sounds that they are hearing. That needs deep learning as well. So robotics is a major area where deep learning is applied. Then we have self-driving cars or autonomous cars. You must have heard of Google's autonomous car, which has been tested for millions of miles and pretty much incident-free. There were, of course, a couple of incidents here and there, but it is considered to be fairly safe. And there are today a lot of automotive companies. In fact, pretty much every automotive company worth its name is investing in self-driving cars or autonomous cars. And it is predicted that in the next probably 10 to 15 years, these will be in production and they will be used extensively in real life. Right now, they are all in R&D and in test phases, but pretty soon these will be on the road. So this is another area where deep learning is used. And how is it used? Where is it used? Within autonomous driving, the car actually is fed with video of surroundings, and it is supposed to process that information, process that video, and determine if there are any obstacles. It has to determine if there are any cars in the side. It will detect whether it is driving in the lane. Also, it has to determine whether the signal is green or red, so that accordingly it can move forward or wait. So for all these video analysis, deep learning is used. In addition to that, the overall training to drive the car happens in a deep learning environment. So again, a lot of scope here to use deep learning. A couple of other applications are machine translation. So today we have a lot of information, and very often this information is in one particular language, and more specifically in English. And people need information in various parts of the world. It is pretty difficult for human beings to translate each and every piece of information or every document into all possible languages. There are probably at least hundreds of languages, or if not more. To translate each and every document into every language is pretty difficult. Therefore, we can use deep learning to do pretty much like a real-time translation mechanism. So we don't have to translate everything and keep it ready, but we train applications or artificial intelligence systems that will do the translation on the fly. For example, you go to somewhere like China and you want to know what is written on a signboard. Now, it is impossible for somebody to translate that and put it on the web or something like that. So you have an application which is trained to translate stuff on the fly. So this can be running on your mobile phone, on your smartphone. You scan this, the application will instantly translate that from Chinese to English. That is one. Then there could be web applications where there may be a research document which is all in maybe Chinese or Japanese, and you want to translate that to study that document, or in that case you need to translate that. So therefore, deep learning is used in such situations as well, and that is again on demand. So it is not like you have to translate all these documents from other languages into English in one shot and keep it somewhere. That is again pretty much an impossible task, but on a need basis. So you have systems that are trained to translate on the fly. So machine translation is another major area where deep learning is used. Then there are a few other upcoming areas where synthesizing is done by neural nets. For example, music composition and generation of music. So you can train a neural net to produce music, even to compose music. So this is a fun thing. This is still upcoming. It needs a lot of effort to train such neural net. It has been proved that it is possible. So this is a relatively new area. And on the same lines, colorization of images. So these two images on the left hand side is a grayscale image or a black and white image. This was colored by a neural net or a deep learning application. As you can see, it's done a very good job of applying the colors, and obviously this was trained to do this colorization. But yes, this is one more application of deep learning. Now, one of the major secret sauce of deep learning is neural network. Deep learning works on neural network or consists of neural network. So let us see, what is neural network. Neural network or artificial neural network is designed or based on the human brain. Now, human brain consists of billions of small cells that are known as neurons. Artificial neural networks is, in a way, trying to simulate the human brain. So, this is a quick diagram of biological neuron. A biological neuron consists of the major part, which is the cell nucleus, and then it has some tentacles kind of stuff on the top called dendrite, and then there is like a long tail which is known as the axon. Further again, at the end of this axon are what are known as synapses. These in turn are connected to the dendrites of the next neuron, and all these neurons are interconnected with each other. Therefore, they are like billions of them sitting in our brain, and they're all active, they're working. Based on the signals, they receive signals as inputs from other neurons or maybe from other parts of the body, and based on certain criteria, they send signals to the neurons at the other end. So they get either activated or they don't get activated based on, so it is like a binary gates. So they get activated or not activated based on the inputs that they receive and so on. So we will see a little bit of those details as we move forward in our artificial neuron. But this is a biological neuron. This is the structure of a biological neuron. And artificial neural network is based on the human brain. The smallest component of artificial neural network is an artificial neuron, as shown here. Sometimes is also referred to as a perceptron. Now, this is a very high-level diagram. The artificial neuron has a small central unit which will receive the input. If it is doing, let's say, image processing, the inputs could be pixel values of the image, which is represented here as x1, x2, and so on. Each of the inputs are multiplied by what is known as weights, which are represented as w1, w2, and so on. There is, in the central unit, basically, there is a summation of these weighted inputs, which is like x1 into w1 plus x2 into w2 and so on. The products are then added, and then there is a bias that is added to that. In the next slide we will see that passes through an activation function, and the output comes as a Y, which is the output, and based on certain criteria the cell gets either activated or not activated. So this output would be like a 0 or a 1 binary format. Okay, so we will see that in a little bit more detail, but let's do a quick comparison between biological and artificial neuron. Just like a biological neuron, there are dendrites, and then there is a cell nucleus and synapse and an axon. We have in the artificial neuron as well. These inputs come like the dendrite, if you will, act like the dendrites. There is like a central unit which performs the summation of these weighted inputs, which is basically W1, X1, W2, X2, and so on. And then a bias is added here, and then that passes through what is known as an activation function. Okay, so these are known as the weights, W1, W2, and then there is a bias which will come out here, and that is added. The bias is, by the way, common for a particular neuron, so there won't be like B1, B2, B3, and so on. Only weights will be 1 per input. The bias is common for the entire neuron. It is also common for, or the value of the bias remains the same for all the neurons in a particular layer. We will also see this as we move forward and we see deep neural network where there are multiple neurons. So that's the output. Now the whole exercise of training a neuron is about changing these weights and biases. As I mentioned, this artificial neural network will consist of several such neurons, and as a part of the training process, these weights keep changing. Initially they are assigned some random values. Through the training process, the weights, the whole process of training is to come up with the optimum values of W1, W2, and Wn, and then the B for, or the bias for this particular neuron, such that it gives an accurate output as required. So let's see what exactly that means. So the training process, this is how it happens. It takes the inputs. Each input is multiplied by a weight, and these weights during training keep changing. So initially they are assigned some random values, and based on the output, whether it is correct or wrong, there is a feedback coming back, and that will basically change these weights until it starts giving the right output. That is represented in here as sigma I going from 1 to n. If there are n inputs, wi into xi. So this is the product of w1, x1, w2, x2, and so on, right? And there is a bias that gets added here, and that entire thing goes to what is known as an activation function. So essentially this is sigma of wixi plus a value of bias, which is a b. So that entire thing goes as an input to an activation function. Now this activation function takes this as an input, gives the output as a binary output. It could be a 0 or a 1. There are, of course, to start with, let's assume it's a binary output. Later we will see that there are different types of activation functions, so it need not always be binary output. But to start with, let's keep simple. So it decides whether the neuron should be fired or not. So that is the output, like a binary output, 0 or 1. Alright, so again, let me summarize this. So it takes the inputs. So if you are processing an image, for example, the inputs are the pixel values of the image. X1, X2 up to Xn. There could be hundreds of these. So all of those are fed as, so these are some values. And these pixel values again can be from 0 to 256. Each of those pixel values are then multiplied with what is known as a weight. This is a numeric value, can be any value. So this is a number, W1. Similarly, W2 is a number. So initially some random values will be assigned, and each of these weights are multiplied with the input value and their sum. This is known as the weighted sum. So that is performed in this kind of the central unit, and then a bias is added. Remember, the bias is common for each neuron. So this is not, the bias value is not one bias value for per input. So just keep that in mind. The bias value, there is one bias per neuron. So it is like this summation plus bias is the output from this section. This is not the complete output of the neuron, but this is the bias for output for step 1. That goes as an input to what is known as an activation function. And that activation function results in an output, usually a binary output like a 0 or a 1, which is known as the firing of the neuron. Okay, good. So we talked about activation function. So what is an activation function? An activation function basically takes the weighted sum, which is, we saw, W1, X1, W2, X2, the sum of all that, plus the bias. So it takes that as an input and it generates a certain output. Now, there are different types of activation functions and the output is different for different types of activation functions. Moreover, why is an activation function required? It is basically required to bring in non-linearity. That's the main reason why an activation function is required. So, what are the different types of activation functions? There are several types of activation functions, but these are the most common ones. These are the ones that are currently in use. Sigmoid function was one of the early activation functions. But today, ReLU has kind of taken over. So ReLU is by far the most popular activation function that is used today. But still, sigmoid function is still used in many situations. These different types of activation functions are used in different situations based on the kind of problem we are trying to solve. So what exactly is the difference between these two? Sigmoid gives the values of the output will be between 0 and 1. Threshold function is the value will be 0 up to a certain value, and beyond that this is also known as a step function, and beyond that it will be 1. In case of sigmoid there is a gradual increase, but in case of threshold it's like also known as a step function. There is a rapid or instantaneous change from 0 to 1. Whereas in sigmoid, we will see in the next slide, there is a gradual increase, but the value in this case is between 0 and 1 as well. Now, ReLU function, on the other hand, it is equal to basically if the input is 0 or less than 0, then the output is 0. Whereas if the input is greater than 0, then the output is equal to the input. I know it's a little confusing, but in the next slides where we show the ReLU function, it will become clear. Similarly, hyperbolic tangent. This is similar to sigmoid in terms of the shape of the function. However, while sigmoid goes from 0 to 1, hyperbolic tangent goes from -1 to 1. And here again, the increase or the change from -1 to 1 is gradual and not like threshold or step function where it happens instantaneously. So let's take a little detailed look at some of these functions. So let's start with the sigmoid function. So this is the equation of a sigmoid function, which is 1 by 1 plus e to the power of minus x. So x is the value, that is the input. It goes from 0 to -1. So this is sigmoid function. The equation is phi x is equal to 1 by 1 plus e to the power of minus x. And as you can see here, this is the input on the x-axis. As x is the value is coming from, in fact it can also go negative. This is negative actually, so this is the 0, so this is the negative value of x. So as x is coming from negative value towards 0, the value of the output slowly, as it is approaching 0, it slowly and very gently increases. And actually at the point, let me just use a pen, at the point here it is 0.5. It is actually 0.5. Okay, and slowly gradually it increases to 1 as the value of x increases. But then as the value of x increases, it tapers off. It doesn't go beyond 1. So that is the speciality of sigmoid function. So the output value will remain between 0 and 1. It will never go below 0 or above 1. Okay, so that is sigmoid function. Now this is threshold function, or this is also referred to as a step function. And here we can also set the threshold. In this case that's why it's called the threshold function. Normally it is 0, but you can also set a different value for the threshold. Now the difference between this and the sigmoid is that here the change is rapid or instantaneous. As the x value comes from negative up to 0, it remains 0, and at 0 it pretty much immediately increases to 1. Okay, so this is a mathematical representation of threshold function. Phi x is equal to 1 if x is greater than equal to 0, and 0 if x is less than 0. So for all negative values it is 0, since we have set the threshold to be 0. So as soon as it reaches 0, it becomes 1. You see the difference between this and the previous one, which is basically the sigmoid, where the increase from 0 to 1 is gradual, and here it is instantaneous. And that's why this is also known as a step function, threshold function or step function. This is a ReLU. ReLU is one of the most popular activation functions today. This is the definition of ReLU. Phi x is equal to max of x comma 0. What it says is if the value of x is less than 0, then phi x is 0. the moment it increases, goes beyond 0, the value of phi x is equal to x. So it doesn't stop at 1, actually it goes all the way. So as the value of x increases, the value of y will also increase infinitely. So there is no limit here, unlike your sigmoid or threshold or the next one, which is basically hyperbolic tangent. Okay, so in case of ReLU, remember there is no upper limit. The output is equal to either 0 in case the value of x is negative, or it is equal to the value of x. So for example, here if the value of x is 10, then the value of y is also 10. Right? Okay, so that is ReLU, and there are several advantages of ReLU, and it is much more efficient and provides much more accuracy compared to other activation functions like sigmoid and so on. So that's the reason it is very popular. Alright, so this is hyperbolic tangent activation function. The function looks similar to sigmoid function. The curve, if you see the shape, it looks similar to sigmoid function. But the difference between hyperbolic tangent and sigmoid function is that in case of sigmoid, the output goes from 0 to 1. Whereas in case of hyperbolic tangent, it goes from -1 to 1. So that is the difference between hyperbolic tangent and sigmoid function. Otherwise, the shape looks very similar. There is a gradual increase, unlike the step function where there was an instant increase or instant change. Here again, very similar to sigmoid function, the value changes gradually from -1 to 1. So this is the equation of hyperbolic tangent activation function. Yeah, so then let's move on. This is a diagrammatic representation of the activation function and how the overall data or how the overall progression happens from input to the output. So we get the input from the input layer. By the way, the neural network has 3 layers. Typically there will be 3 layers. There is an input layer, there is an output layer, and then you have the hidden layer. So the inputs come from the input layer and they get processed in the hidden layer, and then you get the output in the output layer. So let's take a little bit of a detailed look into the working of a neural network. So let's say we want to classify some images between dogs and cats. How do we do this? This is known as a classification process, and we are trying to use neural networks and deep learning to implement this classification. So how do we do that? So this is how it works. So you have 4-layer neural network. There is an input layer, there is an output layer, and then there are 2 hidden layers. And what we do is we provide labeled training data, which means these images are fed to the network with the label saying that, okay, this is a cat. The neural network is allowed to process it and come up with a prediction saying whether it is a cat or a dog. And obviously in the beginning, there may be mistakes. A cat may be classified as a dog. So we then say that, okay, this is wrong. This output is wrong. But every time it predicts correctly, we say, yes, this output is correct. So that learning process, so it will go back, make some changes to its weights and biases. We again feed these inputs and it will give us the output. We will check whether it is correct or not, and so on. So this is a iterative process, which is known as the training process. So we are training the neural network. And what happens in the training process? These weights and biases, you remember there were weights like W1, W2 and so on. So these weights and biases keep changing every time you feed these, which is known as an epoch. So there are multiple iterations. Every iteration is known as an epoch, and each time the weights are updated to make sure that the maximum number of images are classified correctly. So once again, what is the input? This input could be like 1,000 images of cats and dogs, and they are labeled because we know which is a cat and which is a dog, and we feed those 1,000 images. The neural network will initially assign some weights and biases for each neuron, and it will try to extract the features from the images, and it will try to come up with a prediction for each image. And that prediction that is calculated by the network is compared with the actual value, whether whether it is a cat or a dog. And that's how the error is calculated. So let's say there are 1000 images, and in the first run, only 500 of them have been correctly classified. That means we are getting only 50% accuracy. So we feed that information back to the network, further update these weights and biases for each of the neurons, and we run these inputs once again. It will try to calculate, extract the features, and it will try to predict which of these is cats and dogs. And this time, let's say out of 1000, 700 of them have been predicted correctly. So that means in the second iteration, the accuracy has increased from 50% to 70%. Alright. Then we go back again, we feed this maybe for a third iteration, fourth iteration, and so on, and slowly and steadily the accuracy of this network will keep increasing, and it may reach probably, you never know, 90%, 95%. And there are several parameters that are known as hyperparameters that need to be changed and tweaked. And that is the overall training process. And ultimately, at some point we say, okay, you will probably never reach 100% accuracy, but then we set a limit saying that, okay, if we receive 95% accuracy, that is good enough for our application. And then we say, okay, our training process is done. So that is the way training happens. And once the training is done, now with the training data set, the system has, let's say, seen all these 1000 images. Therefore, what we do is the next step, like in any normal machine learning process, we do the testing, where we take a fresh set of images and we feed it to the network, the fresh set which it has not seen before as a part of the training process. And this is again nothing new in deep learning. This was there in machine learning as well. So you feed the test images and then find out whether we are getting similar accuracy or not. So maybe that accuracy may reduce a little bit. While training you may get 98%, and then for test you may get 95%. But there shouldn't be a drastic drop, like for example you get 98% in training and then you get 50% or 40% with the test. That means your network has not learned. You may have to retrain your network. So that is the way neural network training works. And remember, the whole process is about changing these weights and biases and coming up with the optimal values of these weights and biases so that the accuracy is the maximum possible. Alright, so a little bit more detail about how this whole thing works. So this is known as forward propagation, which is the data or the information is going in the forward direction. The inputs are taken, weighted summation is done, bias is added here, and then that is fed to the activation function, and then that comes out as an output. So that is forward propagation, and the output is compared with the actual value, and that will give us the error. The difference between them is the error, and in technical terms that is also known as our cost function. And this is what we would like to minimize. There are different ways of defining the cost function, but one of the simplest ways is mean square error. So it is nothing but the square of the difference of the errors, or the sum of the squares of the difference of the errors. And this is also nothing new. We have probably, if you're familiar with machine learning, you must have come across this mean square error. Now there are different ways of defining cost function. It need not always be the mean square error, but the most common one is this. So you define this cost function and you ask the system to minimize this error. So we use what is known as an optimization function to minimize this error, and the error itself sent back to the system as feedback, and that is known as back propagation. And so this is the cost function. And how do we optimize the cost function? We use what is known as gradient descent. So the gradient descent mechanism identifies how to change the weights and biases so that the cost function is minimized. And there is also what is known as the rate or the learning rate. That is what is shown here as slower and faster. So you need to specify what should be the learning rate. Now if the learning rate is very small, then it will probably take very long to train. Whereas if the learning rate is very high, then it will appear to be faster, but then it will probably never what is known as converge. Now what is convergence? Now we are talking about a few terms here. Convergence is like this. This is a representation of convergence. So the whole idea of gradient descent is to optimize the cost function or minimize the cost function. In order to do that, we need to represent the cost function as this curve. We need to come to this minimum value. That is what is known as the minimization of the cost function. Now, what happens if we have the learning rate very small is that it will take very long to come to this point. On the other hand, if you have higher learning rate, what will happen is instead of stopping here, it will cross over because the learning rate is high, and then it has to come back. So it will result in what is known as like an oscillation. So it will never come to this point, which is known as convergence. Instead, it will go back and forth. So these are known as hyperparameters, the learning rate and so on. And these have to be those numbers or those values we can determine typically using trial and error. Out of experience, we try to find out these values. So that is the gradient descent mechanism to optimize the cost function, and that is what is used to train our neural network. This is another representation of how the training process works. And here in this example, we are trying to classify these images, whether they are cats or dogs. And as you can see, actually each image is fed, in each time one image is fed rather. And these values of x1, x2 up to xn are the pixel values within this image. Okay, so those values are then taken, and for each of those values a weight is multiplied, and then it goes to the next layer and then to the next layer and so on. Ultimately it comes as the output layer, and it gives an output as whether it is a dog or a cat. Remember, the output will never be a named output, so these would be like a 0 or a 1, and we say okay, 0 corresponds to dogs and 1 corresponds to cats. So that is the way it typically happens. This is a binary classification. We have similar situations where there can be multiple classes, which means that there will be more neurons in the output layer. Okay, so this is once again a quick representation of how the forward propagation and the backward propagation works. So the information is going in this direction, which is basically the forward propagation, and at the output level we find out what is the cost function. The difference is basically sent back as part of the backward propagation, and gradient descent then adjusts the weights and biases for the next iteration. This happens iteratively till the cost function is minimized. And that is when we say the network has converged, or the training process has converged. And there can be situations where convergence may not happen in rare cases, but by and large the network will converge, and after maybe a few iterations, it could be tens of iterations or hundreds of iterations, depending on what exactly the number of iterations can vary. And then we say okay, we are getting a certain accuracy, and we say that is our threshold, maybe 90% accuracy. We stop at that and we say that the system is trained. The trained model is then deployed for production and so on. So that is the way the neural network training happens. Okay, so that is the way classification works in deep learning using neural network. And this slide is an animation of this whole process. As you can see, the forward propagation, the data is going forward from the input layer to the output layer, and there is an output, and the error is calculated, the cost function is calculated, and that is fed back as a part of backward propagation, and that whole process repeats once again. Okay, so remember, in neural networks the training process is nothing but finding the best values of the weights and biases for each and every neuron in the network. That's all training of neural network consists of. Finding the optimal values of the weights and biases so that the accuracy is maximum.
Human versus artificial intelligence. Humans are amazing. Let's just face it. We're amazing creatures. We're all over the planet. We're exploring every niche and nook. We've gone to the moon. We've gone into outer space. We're just amazing creatures. We're able to use the available information to make decisions, to communicate with other people, identify patterns in data, remember what people have said, adapt to new situations. So let's take a look at this. So you can get a picture. You're a human being, so you know what it's like to be human. Let's take a look at artificial intelligence versus the human. Artificial intelligence develops computer systems that can accomplish tasks that require human intelligence. So when we're looking at this, one of the things that computers can do is they can provide more accurate results. This is very important. Recently I did a project on cancer where I was identifying markers. And as a human being, you look at that and you might be looking at all the different images and the data that comes off of them and say, I like this person, so I want to give them a very good outlook. And the next person you might not like, so you want to give them a bad outlook. Well, with artificial intelligence, you're going to get a consistent prediction of what's going to come out. Interacts with humans using their natural language. We've seen that as probably the biggest development feature right now that's in the commercial market that everybody gets to use, as we saw with the example of Alexa. They learn from their mistakes and adapt to new environments. So we see this slowly coming in more and more. And they learn from the data and automate repetitive learning. Repetitive learning has a lot to do with the neural networks. You have to program thousands upon thousands of pictures in there, and it's all automated. So as today's computers evolve, it's very quick and easy and affordable to do this. What is machine learning and deep learning all about? Imagine this. Say you had some time to waste. Not that any of us really have a lot of time anymore to just waste in today's world. And you're sitting by the road, and you have a whole lot of time passes by. There's a few hours. And suddenly you wonder, how many cars, buses, trucks, and so on passed by in the 6 hours? Now, chances are you're not going to sit by the road for 6 hours and count buses, cars, and trucks, unless you're working for the city and you're trying to do city planning and you want to know, hey, do we need to add a new truck route? Maybe we need a bicycle lane because we have a lot of bicyclists here, that kind of thing. So maybe city planning would be great for this. Machine learning. Well, the way machine learning works is we have labeled data with features. Okay, so you have a truck or a car, a motorcycle, a bus, or a bicycle, and each one of those are labeled. It comes in, and based on those labels and comparing those features, it gives you an answer. It's a bicycle, it's a truck, it's a motorcycle. Let's look a little bit more in depth on this. In the model here, the features we're looking at would be like the tires. Someone sits there and figures out what a tire looks like. It takes a lot of work. If you try to figure the difference between a car tire, a bicycle tire, a motorcycle tire, so in the machine learning field, this could take a long time if you're going to do each individual aspect of a car and try to get a result on there. And that's what they did do. That was this is still used on smaller amounts of data where you figure out what those features are and then you label them. Deep learning. So with deep learning, one of our solutions is to take a very large unlabeled data set and we put that into a training model using artificial neural networks, and then that goes into the neural network itself when we create a neural network. And you'll see the arrows are actually kind of backward, but which actually is a nice point, because when we train the neural network, we put the bicycle in and then it comes back and says, if it said truck, it comes back and says, well, you need to change that to bicycle. And then it changes all those weights going backward, they call it back propagation, and let it know it's a bicycle, and that's how it learns. Once you've trained the neural network, you then put the new data in, and they call this testing the model, so you need to have some data you've kept off to the side where you know the answer to. And you take that and you provide the required output, and you say, okay, is this neural network working correctly? Did it identify a bike as a bike, a truck as a truck, a motorcycle as a motorcycle? Let's just take a little closer look at that. Determining what objects are present in the data. So how does deep learning do this? And here we have the image of the bike. It's 28 by 28 pixels. That's a lot of information there. Could you imagine trying to guess that this is a bicycle image by looking at each one of those pixels and trying to figure out what's around it? And we actually do that as human beings. It's pretty amazing. We know what a bicycle is, and even though it comes in as all this information. And what this looks like is the image comes in, it converts it into a bunch of different nodes. In this case, there's a lot more than what they show here. And it goes through these different layers and out comes and says, okay, this is a bicycle. A lot of times they call this the magic black box. Why? Because as we watch it go across here, all these weights and all the math behind this, and it's a little complicated on the math side. You really don't need to know that when you're programming or working with the deep learning. But it's like magic. You don't know, you really can't figure out what's going to come out by looking what's in each one of those dots and each one of those lines are firing and what's going in between them. So we like to call it the magic box. So that's where deep learning comes in. And in the end, it comes up and you have this whole neural network. It comes up and it says, okay, we fire all these different pixels and we connects all these different dots and gives them different weights, and it says, okay, this is a bicycle. And that's how we determine what the object is present in the data with deep learning. Machine learning. We're going to take a step into machine learning here, and you'll see how these fit together in a minute. The system is able to make predictions or take decisions based on past data. That's very important for machine learning, is that we're looking at stuff, and based on what's been there before, we're creating a decision on there. We're creating something out of there. We're coloring a beach ball. We're telling you what the weather is in Chicago. What's nice about machine learning is a very powerful processing capability. It's quick and accurate outcomes, so you get results right away. Once you program the system, the results are very fast. And the decisions and predictions are better. They're more accurate. They're consistent. You can analyze very large amounts of data. Some of these data things that they're analyzing now are petabytes and terabytes of data. It would take hundreds of people hundreds of years to go through some of this data and do the same thing that the machine learning can do in a very short period of time. And it's inexpensive compared to hiring hundreds of people. So it becomes a very affordable way to move into the future, is to apply the machine learning to whatever businesses you're working on. And deep learning. Systems think and learn like humans using artificial neural networks. Again, it's like a magic box. Performance improves with more data. So the more data the deep learning gets, the more it gives you better results. It's scalability, so you can scale it up, you can scale it down, you can increase what you're looking at. Currently, we're limited by the amount of computer processing power as to how big that can get, but that envelope continually gets pushed every day on what it can do. Problem solved in an end-to-end method. So instead of having to break it apart, and you have the first piece coming in and you identify tires, and the second piece is identifying labeling handlebars, and then you bring that together, that if it has handlebars and tires, it's a bicycle, and if it has something that looks like a large square, it's probably a truck. The neural networks does this all in one network. You don't really know what's going on in all those weights and all those little bubbles, but it does it pretty much in one package. That's why the neural network systems are so big nowadays and coming into their own. Best features are selected by the system, and this is important. They kind of put it's on a bullet on the side here. It's a subset of machine learning. This is important. When we talk about deep learning, it is a form of machine learning. There's lots of other forms of machine learning, data analysis, but this is the newest and biggest thing that they apply to a lot of different packages, and they use all the other machine learning tools available to work with it. And it's very fast to test. You put in your information, you then have your group of tests, and then you held some aside and you see how does it do. It's very quick to test it and see what's going on with your deep learning and your neural network. Are they really all that different? AI versus machine learning versus deep learning. Concepts of AI. So we have concepts of AI. You'll see natural language processing, machine learning, an approach to create artificial intelligence. So it's one of the subsets of artificial intelligence. Knowledge representation, automated reasoning, computer vision, robotics. Machine learning versus AI versus deep learning, or AI and machine learning and deep learning. So when we look at this, we have AI with machine learning and deep learning. And so we're going to put them all together. We find out that AI is the big picture. We have a collection of books. It goes through some deep learning. The digital data is analyzed. Text mining comes through. The particular book you're looking for, or maybe it's a genre of books, is identified. And in this case, we have a robot that goes and gives a book to the patron. I have yet to be at a library that has a robot bring me a book, but that will be cool when it happens. So we'll look at some of the pieces here. This information goes into, as far as this example, the translation of the handwritten printed data to digital form. That's pretty hard to do. That's pretty hard to go in there and translate hundreds and hundreds of books and understand what they're trying to say if you've never read them. So in this case, we use the deep learning because you can already use examples where they've already classified a lot of books, and then they can compare those texts and say, oh, okay, this is a book on automotive repair. This is a book on robotic building. The digital data is then analyzed. Then we have more text mining using machine learning. So maybe we'd use a different program to do a basic classify what you're looking for and say, oh, you're looking for auto repair and computers. So you're looking for automated cars. Once it's identified, then of course it brings you the book. So here's a nice summation of what we were just talking about. AI with machine learning and deep learning. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So you can look at artificial intelligence as the big picture. How does this compare to the human experience in either doing the same thing as a human we do, or it does it better than us? And machine learning, which has a lot of tools, is something that learns from data, past experiences. It's programmed. It comes in there and it says, hey, we already had these 5 things happen. The 6th one should be about the same. And then there's a lot of tools in machine learning, but deep learning then is a very specific tool in machine learning. It's the artificial neural network, which handles large amounts of data and is able to take huge pools of experiences, pictures, and ideas and bring them together. Real life examples. Artificial intelligence, news generation, very common nowadays as it goes through there and finds the news articles or generates the news based upon the news feeds or the backend coming in and says, okay, let's give you the actual news based on this. There's all the different things, Amazon Echo, they have a number of different Prime Music on there. Of course, there's also the Google Command, and there's also Cortana. There's tons of smart home devices now where we can ask it to turn the TV on or play music for us. That's all artificial intelligence. From front to back, you're having a human experience with these computers and these objects that are connected to the processing. Machine learning, spam detection, very common. Machine learning doesn't really have the human interaction part. So this is the part where it goes and says, okay, that's a spam, that's not a spam, and it puts it in your spam folder. Search engine result refining. Another example of machine learning, whereas it looks at your different results and it is able to categorize them as far as this had the most hits, this is the least viewed, this has 5 stars, however they want to weight it. All good examples of machine learning. And then the deep learning. Deep learning, another example is as you have like a exit sign. In this case, it's translating it into French. Sortie. I hope I said that right. The neural network has been programmed with all these different words and images, and so it's able to look at the exit in the middle, and it goes, okay, we want to know what that is in French, and it's able to push that out in French, and learn how to do that. And then we have chatbots. I remember when Microsoft first had their little paperclip. Boy, that was like a long time ago. That came up and you would type in there and chat with it. These are growing. It's nice to just be able to ask a question and it comes up and gives you the answer. And instead of it being where you're just doing a search on certain words, it's now able to start linking those words together and form a sentence in that chat box. Types of AI and machine learning. Types of artificial intelligence. This and the next few slides are really important. So one of the types of artificial intelligence is reactive machines. Systems that only react. They don't form memories, they don't have past experiences, they have something that happens to them and they react to it. My washing machine is one of those. If I put a ton of clothes in it and they get all clumped on one side, it automatically adds a weight to recenter it. So that my washing machine is actually a reactive machine working with whatever the load is and keeps it nice, and so when it spins it doesn't go thumping against the side. Limited memory. Another form of artificial intelligence. Systems look into the past. Information is added over a period of time and information is short-lived. When we're talking about this and you look at like a neural network that's been programmed to identify cars, it doesn't remember all those pictures. It has no memory as far as the hundreds of pictures you process through it. All it has is, this is the pattern I use to identify cars as the final output for that neural network we looked at. So when they talk about limited memory, this is what they're talking about. They're talking about, I've created this based on all these things, but I'm not going to remember any one specifically. Theory of mind. Systems being able to understand human emotions and how they affect decision making to adjust their behaviors according to their human understanding. This is important because this is our page mark. This is how we know whether it is an artificial intelligence or not. Is it interacting with humans in a way that we can understand? Without that interaction, is just an object. So when we talk about theory of mind, we really understand how it interfaces. That whole, if you're in web development, user experience would be the term I would put in there. So theory of mind would be user experience. How is the whole UI connected together? And one of the final things is, as we get into artificial intelligence, is systems being aware of themselves, understanding their internal states, and predicting other people's feelings and act appropriately. So as artificial intelligence continues to progress, we see ones that are trying to understand, well, what makes people happy? How would they increase our happiness? How would they keep themselves from breaking down if something's broken inside? They have that self-awareness to be able to fix it. And just based on all that information, predicting which action would work the best. What would help people? If I know that you're having a cup of coffee first thing in the morning is what makes you happy, as a robot, I might make you a cup of coffee every morning at the same time to help your life and help you grow. That'd be the self-awareness, is being able to know all those different things. Types of machine learning, and like I said on the last slide, this is very important. This is very important. If you decide to go in and get certified in machine learning or know more about it, these are the three primary types of machine learning. The first one is supervised learning. Systems are able to predict future outcome based on past data. Requires both an input and an output to be given to the model for it to be trained. So in this case, we're looking at anything where you have 100 images of a bicycle, and those 100 images are bicycle. So they're preset. Someone already looked at all 100 images and said, these are pictures of bicycles. And so the computer learns from those, and then it's given another picture, and maybe the next picture is a bicycle, and it says, oh, that resembles all these other bicycles, so it's a bicycle. And the next one's a car, and it says, it's not a bicycle. That would be supervised learning, because we had to train it. We had to supervise it. Unsupervised learning. Systems are able to identify hidden patterns from the input data provided by making the data more readable and organized. The patterns, similarities, or anomalies become more evident. You'll heard the term cluster. How do you cluster things together? Some of these things go together, some of these don't. This is unsupervised, where it can look at an image and start pulling the different pieces of the image out because they aren't the same. All the parts of the human are not the same as a fuzzy tree behind them because it's slightly out of focus, which is not the same as the beach ball. It's unsupervised because we never told it what a beach ball was, we never told it what the human was, and we never told it that those were trees. All we told it was, hey, separate this picture by things that don't match and things that do match and come together. And finally, there's reinforcement learning. Systems are given no training. It learns on the basis of the reward punishment it received for performing its last action. It helps increase the efficiency of a tool function or a program. Reinforced learning, or reinforcement learning, is kind of, you give it a yes or no. Yes, you gave me the right response. No, you didn't. And then it looks at that and says, oh, okay, so based on this data coming in, what I gave you was a wrong response, so next time I'll give you a different one. Comparing machine learning and deep learning. So remember that deep learning is a subcategory of machine learning. So it's one of the many tools. And so we're grouping a ton of machine learning tools all together. Linear regression, K-means clustering. There's all kinds of cool tools out there you can use in machine learning. Enables machines to make decisions on their own based on past data. Enables machines to make decisions with the help of artificial neural networks. So it's doing the same thing, but we're using an artificial neural network as opposed to one of the more traditional machine learning tools. Needs only a small amount of training data. This is very important. When you're talking about machine learning, they're usually not talking about huge amounts of data. We're talking about maybe your spreadsheet from your business and your totals for the end of the year. When you're talking about neural networks, you usually need a large amount of data to train the data. So there's a lot of training involved. If you have under 500 points of data, that's probably not going to go into machine learning. Or maybe you have, like the case of one of the things, 500 points of data and 30 different fields. It starts getting really confusing there in artificial intelligence or machine learning. And the deep learning aspect really shines when you get to that larger data that's really complex. Works well on a low-end systems. So a lot of the machine learning tools out there you can run on your laptop with no problem and do the calculations there. Where with the machine learning, you usually needs a higher end system to work. It takes a lot more processing power to build those neural networks and to train them. It goes through a lot of data. We're talking about the general machine learning tools. Most features need to be identified in advance and manually coded. So there's a lot of human work on here. The machine learns the features from the data it is provided. So again, it's like a magic box. You don't have to know what a tire is. It figures it out for you. The problem is divided into parts and solved individually and then combined. So machine learning, you usually have all these different tools and use different tools for different parts. And the problem is solved in an end-to-end manner. So you only have one neural network or two neural networks that is bringing the data in and putting it out. It's not going through a lot of different processes to get there. And remember, you can put machine learning and deep learning together. So you don't always have just the deep learning solving the problem. You might have it solving one piece of the puzzle. With regular machine learning and most of the machine learning tools out there, they take longer to test and understand how they work. And with the deep learning, it's pretty quick. Once you build that neural network, you test it and you know. So we're dealing with very crisp rules, limited resources. You have to really explain how the decision was made when you use most machine learning tools. But when you use the deep learning tool inside the machine learning tools, the system takes care of it based on its own logic and reasoning. And again, it's like a magic black box. You really don't know how it came up with the answer. You just know it came up with the right answer. A glimpse into the future. So a quick glimpse into the future, artificial intelligence, be using it to detecting crimes before they happen, humanoid AI helpers, which we already have a lot of. There'll be more and more. Maybe it'll actually be androids. That'd be cool to have an android that comes and gets stuff out of my fridge for me. Machine learning, increasing efficiency in healthcare. That's really big in all the forms of machine learning. Better marketing techniques. Any of these things, if we get into the sciences, it's just off the scale. Machine learning and artificial intelligence go everywhere. And then the subcategory deep learning, increased personalization. So what's really nice about the deep learning is it's going to start now catering to you. That'll be one of the things we see more and more of. And we'll have more of a hyper-intelligent personal assistant. I'm excited about that.
First, we'll understand the basics. And starting with the basics, we'll start with what is deep learning. So deep learning, often touted as an attempt to replicate human brain learning, operates through intricate mathematical functions, enabling computers to perform tasks similar to humans. For instance, it underpins groundbreaking technologies like driverless cars, as well as voice-activated assistants such as Siri and Amazon Alexa. In practice, deep learning empowers computers to learn directly from various data formats, such as images, text, or audio. Through this process, computer models achieve remarkable accuracy, occasionally surpassing human-level performance. It's not just about mimicking human cognition. It's about harnessing the immense computational power to expect vast amounts of data and extract meaningful patterns. The backbone of deep learning consists of neural networks, interconnected nodes that process data through layers, each layer refining the representation of the data. Training these networks involves adjusting parameters to minimize errors and improve accuracy, a process resembling the human learning experience, albeit on a vastly accelerated scale. While data and computational challenges exist, the field continues to evolve. Research and innovation are driving deep learning forward, opening doors to improved image recognition, natural language understanding, medical diagnostics, and more. The promise of unsupervised learning and the integration of deep learning into diverse industries paints an exciting future for this transformative technology, impacting the way we interact with machines and pushing the boundaries of what's possible. So this was all about the basics and about the deep learning. Now we'll see why we should learn deep learning. So it's a game changer in various aspects, offering state-of-the-art performance, scalability with data, reduced feature engineering, and transferability across tasks. Firstly, deep learning shines where traditional machine learning algorithms struggle. Speech recognition, image classification, and object detection are areas where deep learning algorithms like CNNs, convolutional neural networks, and recurrent neural networks (RNNs) excel due to their specialized architectures, pushing the boundaries of what's achievable. Moreover, as data becomes abundant, deep learning's performance continues to improve. Unlike classical machine learning algorithms, which plateau in performance with more data, deep learning algorithms thrive on it, offering a scalable solution for the ever expanding datasets. Another significant advantage is the reduced need for intricate feature engineering. Traditional methods often require complex manual feature extraction. In deep learning, the emphasis is on learning directly from the data, reducing the burden of feature engineering and making it more accessible for beginners. Additionally, deep learning models are transferable. Pre-trained networks such as VGG16, ResNets, and MobileNet can be leveraged as feature extraction tools for related tasks. This accelerates model training and enhances performance, especially when faced with limited data and computational resources. In essence, deep learning empowers you with cutting edge skills, enabling you to tackle complex problems, scale with data, and achieve impressive results without the need for extensive feature engineering. Its transferability across tasks provides a strategic advantage, making it an invaluable skill for modern AI and machine learning practitioners. So these were the points that show us why we should learn deep learning. And before moving on to the roadmap to become a deep learning engineer, we have a course offering for you. That is, if you are one of the aspiring deep learning enthusiasts looking for online training, or a professional who elicits to switch careers in deep learning by learning from the experts, then try giving a shot to Caltech AI and ML Bootcamp, that is in collaboration with Simplilearn. And the link to this bootcamp is mentioned in the description box below that will navigate you to the bootcamp page where you can find a complete overview of the program being offered. Now moving on to the roadmap to become an deep learning engineer. So learning deep learning as a beginner involves several essential steps, each building upon the previous to develop a comprehensive understanding and practical skills in this field. So the first is learn and master Python. So Python is the foundation for many deep learning libraries and frameworks. Start by mastering Python syntax, data structures, and basic programming concepts. It's essential to be comfortable with Python as you will use it extensively for coding deep learning models. And moving on to the next step, that is mathematics for deep learning. Develop a solid understanding of the mathematical concepts behind deep learning. This includes linear algebra, that includes vectors, matrices, operations. Then we have calculus, in that we have differentiation, integration, and then we have statistics, that includes probability and distributions. These concepts are vital to grasp the inner workings of neural networks. And then we have neural networks, the third step, that is dive into the core of deep learning, understanding neural networks, explore topics like loss functions, that is how the model measures its performance, activation functions, that is which add nonlinearity to the network. Then we have weight initialization, that is critical for model convergence, and the vanishing or exploding gradient problem, that is a challenge in deep networks. Then we have the next step, that is architectures. So familiarize yourself with various neural network architectures. Start with feed-forward neural networks, which form the basis for many models. Progress to autoencoders, convolutional neural networks CNNs for image tasks, recurrent neural networks RNNs for sequential data, transformers for NLP tasks, Siemens networks for similarity comparison, generative adversarial networks GANs for generating data, and explore evolving architectures like NEAT, neuroevolution of augmenting topologies. And now moving on to the next step, that is learning tools and frameworks. So learn to work with popular deep learning tools and frameworks. Familiarize yourself with TensorFlow, PyTorch, Keras, and MLflow. These tools simplify model development and management. So after this step, you should learn the model optimization. So understand techniques for model optimization. This includes distillation, that is knowledge transfer from large models to smaller ones. Quantization, reducing model size without significant loss of performance. And neural architecture search, that is automated methods to find optimal network architectures. Then you should have hands-on projects to practice on, that is apply what you have learned by working on hands-on projects. Start with simple tasks and gradually tackle more complex problems. Implement the different architectures you have learned. Use the frameworks and experiment with model optimization techniques. By following this structured approach, you will build a strong foundation in deep learning, enabling you to create, train, and optimize neural networks for various tasks. The combination of theoretical understanding and practical experience gained from hands-on projects will equip you to explore advanced topics and contribute to the exciting field of deep learning. and the field of deep learning is rapidly evolving. So stay updated with the latest research papers, new techniques, and emerging technologies. Engage with the AI community through forums, blogs, and conferences. And consider joining AI-focused online communities and attend conferences like Neural PS, CVPR, or ICML. And there you have it, the Deep Learning Engineer Roadmap. Remember, this journey requires dedication, continuous learning, and a passion for solving complex problems. Whether you are aiming to work in industry, research, or both, this roadmap will set you on the right path.
Then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below.
Deeper into looking at the theory behind the neural network. And we kind of flip back and forth between these because there's two huge aspects of it. One is from the outside, what are you seeing, and what's going on from the inside, so you can find to do what you need to do and give the best results you can. And we start off with what do we feed? We feed an unlabeled image to a machine which identifies it without any human intervention. And so you can see here we have a circle that comes in at 784 pixels, and it comes in by 28 by 28. And you can see how it colors in the circle on there. And then we put a triangle in. The triangle in also comes in as 28 by 28, and it has 784 pixels. So you'll see between these two, both of them are 784 pixels. This machine is intelligent enough to differentiate between the various shapes. So that's what we want to use our neural network to do, is to say, hey, this is a circle, this is a triangle. And that's more of a categorical. You can also do a regression model where you're actually putting out a float value or a numerical value. We'll be looking at the true false or the categorical model mostly, because that's where you usually start at. There is no real difference when you, as far as the way the internal functioning goes, when you start flipping between them, other than, well, we'll talk about that in just a minute. So you can actually go between the two quite easily. And the neural network provides this capability. So we're going to use this capability to look between those two. One of the things I want you to note in here is that we're looking at 784 pixels. We're looking at 784 inputs. That's very different than stock with a high-low or last year's cells based on date, where we're looking at just a couple of numbers, and they're very clear. They're numbers. They're very clear what they are, which is something you'd put into a machine learning linear regression model. This is a step up from that in that we're looking at complex patterns, and how do you figure those complex patterns out? So a neural network is a system modeled on the human brain. And we looked at that, comparing the two. Let's go ahead and look deeper into the neural network itself. We have our inputs coming in. So the inputs are fed to a neuron that processes the data and gives us an output. Input and output. This is the most basic structure of a neural network known as a perceptron. So if you see the term perceptron, that's what we're talking about. We're talking about this single node that has inputs and an output. However, neural networks are usually much more complex. Let's start with visualizing a neural network as a black box. And I always love that symbol. It's a black box. It's kind of magical. We have our inputs coming in, and we want certain outputs. The box takes inputs, processes them, and gives an output. Let's have a look at what happens within this box. And you can see me there in my secret agent getup. I got my hidden hood and everything. I guess I'm part of the Black Skull or something like that group. So let's take a look at what happens within this magic box. And remember, we're skipping back and forth between the theory of what's going on in the box, which you have to know how to fine-tune and how to build, versus looking at it from the outside. We're programming this box, and we have an input and an output to the box as a whole. Within the box exists a network that is a core of deep learning. And you can see here we're showing one layer, and we have our grid coming in. The network consists of layers of neurons. Each neuron is associated with a number called the bias. And you can think of the bias, if you overly simplify this, and we're doing a linear regression model, this is your y-intercept in your Euclidean geometry. You have to have something that offsets it. And so you always have a bias in these cells. Neurons of each layer transmit information to neurons of the next layer over channels. And so you can see each of our layers going through from left to right. These channels are associated with numbers called weights. These weights, along with the biases, determine the information that is passed over from the neuron to neuron. So just like the bias is your y-intercept in Euclidean geometry, you could look at the one weight, Remember, this is very complicated, so we're not looking at just one weight. You can look at the weight as your slope of the line. Or if you're doing x equals my plus c, it would be the m value. Neurons of each layer transmit information to neurons of the next layer. And you can see here as they light up going across into the final layer and then to the output. And in this case, the output is going to be either a square in this one, or it might light up the other one, which is a circle. The output layer emits a predicted output. So in this case, we're looking at a classification, true, false. Is it a circle? Is it a triangle? Is it a square? Let's now go deeper what happens within the neuron. So we're going to dig deeper and start getting a little bit closer to some of the math. Don't worry, you don't have to be a calculus expert or know your differential equations. Even though this is one giant differential equation, you don't need to understand those to understand what's going on. Within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. This is simply addition. We're going to sum up the weight times the output from the previous channel, and plus the bias. Sum of the weighted products is computed. This is called the weighted sum. Bias, unique to the neuron, is added to the weighted sum. The final sum is then subjected to the particular function. And we'll discuss that particular function. That part is really important because those functions have a huge impact on how well your model performs under different conditions. The final sum is then subjected to a particular function. This is the activation function. So if you ever hear the term activation function, that's what we're talking about. What activates this cell and what doesn't. As we dig deeper into activation function, an activation function takes the weighted sum of the input as its input, adds a bias, and provides an output. And a lot of times you'll actually see one formula for the sum of the weighted sum and the bias. You'll just see that as a single line of everything added together. In here we've broken it apart because it makes it clear that this bias is not computed the same as the weighted sums. Here are the most popular types of activation function. And I always find these interesting because at one point I was sitting at a table with a gentleman who was finishing his PhD. He was in his last year, and he said he went through all this stuff and he ended up just trying the 4 different activation functions on this particular problem he was working on. So knowing the math behind it doesn't necessarily mean you're going to know it right away. So even somebody who might have a PhD and be doing the calculations on this comes back out of it and ends up just trying the different activation functions to see what's going to make a difference. And a lot of times that's a final step. That's the kind of thing where you built your whole model, you've come back and you're like, wait a minute, can I do a better deal with the sigmoid function or the threshold or the rectifier? Knowing what they're doing is important so you can explain it to somebody else. And again, you probably do this on a small set of data. If you're working with big data, you don't want to take down the full server farm just to test out your 3 different series. You take a small portion of that data, test it, and then you put it through to the big data. So let's take a look at this. We have the sigmoid function, and it's used for models where we have to predict the probability as an output. It exists between 0 and 1. And you'll see that's true of all of our activation functions we're working with. Either the cell's on or off. It's true or false. And there might be a little variation in there, which as an output could be used to compute uncertainty in your solution. So if you're getting a 0.7 with this activation function, it might be, well, I'm not sure if that's really a square, or I'm not sure that's really a triangle. And that might be a flag for it to be looked at by a human observer, at least in today's models where we're at right now. And you can see here where we have the formula is simply equals 1 over 1 plus e to the minus x, where x is your value coming in, and it's going to give you a result that looks very similar to the graph on there, which is somewhere between 0 and 1, and right in the middle you can see that there's a huge you can go through all the different values and uncertainties involved. So the sigmoid function is probably the default on most of them. The next one is the threshold function. It is a threshold-based activation function. If x value is greater than a certain value, the function is activated and fired, else not. Pretty straightforward. Yes, no, true, false. I don't want to test for improbabilities. I just want a straight answer. I don't want to know if there's a partial value on there. It either is true or it's false. And the rectifier function, it is the most widely used activation function. I would debate that. Rectifier is a pretty common one, although I see the sigmoid function used to be the basic one, but it's up there. The rectifier function is very commonly used. It gives the output of x if x is positive and 0 otherwise, and you can see here again, just like it's either kind of get a value going up there, so max of x of 0. So it's like the threshold function. Yes, no, true, false. It's either 0 or it's some kind of progressive value. And then we have the rectifier function. I would argue with this because the sigmoid function used to be the most common one, but with the rectifier function, it now says it is the most commonly used or widely used activation function and gives an output of x if x is positive and 0 otherwise. This is kind of nice because it now says absolutely not, or it gives you a value of probability. Now when I say a value of probability, be very careful there. I'm not saying that it's going to tell you this is 75% chance of being a circle. I'm going to tell you that it says, hey, if this says 0.1, it probably needs to be looked at, or 0.2 or 0.3. It's going to depend on your data as to what that value means. In general, that just means it's flagging it that if it's not a 1, then chances are it needs to be looked at by a person and reevaluated. And there's a hyperbolic tangent function. This function is similar to sigmoid function, is bound to a range of -1 to 1. So you can see there's our 1 minus e to the minus 2x and 1 plus over 1 plus e to the minus 2x. Again, it's very similar to the sigmoid function. The bonus of the hyperbolic function is you have that variable coming through the middle. So again, you can look at it and you have a little bit more weight as far as you can process that down the line. That's a little bit more advanced than what we're looking at right now, and a lot of times it's not even necessary in a lot of our different uses for these activation functions. Now, we looked at activation functions, and I kind of said those are a little bit like a black box, because even if you know all the math, a lot of times you end up just playing with them to find out what works, and it also depends on what model you're working with, whether you need a flat yes, no, true, false, or you need to have something in the middle that says, hey, this isn't quite a 1, you might need to process this with the human intervention. And you can look at that. One example would be self-driving cars. You don't want a car to be yes, no, I'm going to go through the light. You want it to be like, okay, if it's almost yes, maybe we stop and have human intervention so we don't get an accident. Cost function is something you can really see and measure and is very important. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. So we have our group of data that's a square, circle, and since we're looking at geometrical shapes, we've had somebody already labeled that data. They've already said this is a triangle, this is a square, and so if this is coming up and it's giving us and it's saying a square is a triangle and it's saying a triangle is a circle, the output is wrong, and so that output can then be measured versus the actual output, and that's the cost. You might also hear this as error, because that's the error value being returned. How far off is it? And what we're looking for is the least cost, or the least error value, and it's obtained by making adjustments to the weights and biases iteratively throughout the training process. And this is called back propagation, and we're going to look in that a little deeper as we look into an example. It's really hard to see when you're just looking at arrows without actual numbers and where that flow is coming from. But you can look at this as here's our inputs. They put out a prediction. The prediction comes out and says, hey, we've already labeled this data because we're in training mode, and the training data is off. This is the cost. Can we send that error or that cost back and adjust those weights? And we do it in very small increments across large amounts of data so that those weights minimize that cost or that error. But what happens within these neurons? So let's look at a little example of this. Kind of helps if you have some kind of visual. Let's build a neural network that predict bike prices based on a few of its features. And we'll see here we have our CC, our mileage, and our ABS, and these are our 3 input layers. And then we have the bike price and the output layer. Now, it doesn't do us very good to just pump it in from the beginning and pump it out. And to be honest, I would use a machine learning linear regression model on this, since these are just straight numbers. But because we want a simple example, we're going to put this through and show you as a neural network what that looks like. And we got to put a hidden layer in there. The hidden layer helps in improving the output accuracy. And you could look at this as a bunch of ORs. So it might say, hey, when we compare these 3 values on the first hidden layer neuron, we're looking at one set of features, and then we might weight them in the second one. So these are a bunch of different ORs, kind of how the math comes out and behind the scenes. And then they go out, of course, to the bike price or the output layer. And each of the connections have a weight assigned with it. And you'll see here we have mileage CC with the weight 1 and weight 2 going into our first neuron. And you'd also have your ABS going in there. And so x1 times weight 1 plus x2 times weight 2 plus the bias of 1. And step 2 is our activation. The activation activation function coming in there. When does this fire? And the neuron takes a subset of the inputs and processes it. And then we go through and we do that with the second hidden layer neuron and the third one and so on. So you process each layer in order going forward. Now, when I told you this is in its infant stage, they now have neurons that fire into the same layer or back a layer, so that you now have a time series, and there's all kinds of wild things that they're experimenting with on these layers. This basic setup has been around since the mid-90s. It's only now, because of our technology, that it's open to almost everybody to play with it, and that's why I say this is in an infant stage in development. Is this basic math is here, but what we can do with it is amazing, and what they're actually doing with all these different things is amazing. And so we're just at the beginning of how to use all these different tools in our deep learning and our neural networks. And so once we have our hidden layer computed, the information reaching the neurons in the hidden layer is subjected to the respective activation function. And so each one of these fires an activation output, and then those are each weighted to the final output layer. So the processed information is now sent to the output layer, once again, over weighted channels. And you could look at this as each one of these is, I always look at this as like a group of people. They're all looking at the bulletin board, and the first person says, this is what I project sells for the company, and the second person, and the third, and so on. And then their perspectives are weighted based on their expertise. So your accountant might have a very high weight, where the maybe your janitor has a very low weight, because their expertise is not in accounting. And then that goes into the output layer. And once in the output layer, it goes, the output, which is the predicted value, is compared against the original value. So now we have our output layer, and since we have like already a list of bikes with the different setups and what their value is, we can now generate an error from this. The cost function determines the error in prediction and reports it back to the neural network. So this is the cost. This is how far off it is. This is your error coming back. And as you can see, this is back propagation going on. So now our error is going in reverse, because we know we're not completely correct on this particular channel. The weights are adjusted in order to reduce the error. So each time we go back, we are changing those weights to reduce that error, and we change them in small increments. You don't want to fit one input. Remember, you might have a data pool with a terabyte of data. You don't want to solve for the first set of data that comes in and that be the main solution, because everything else will be off. This is going to confuse you. That's also called a bias. So we have the bias in the cell where we're adding a value, the kind of like the y-intercept, and we have a bias of the whole neural network, which means that it's weighted towards one set of answers. So we want to make small changes in these weights so we don't create a bias. And the weights are adjusted in order to reduce the error, or the cost. The network is now trained using the new weights. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. So let's go ahead and plug in values and see how our neural network works. So here we come in here, and initially our channels are assigned with random weights. This is important because if you assign them all with the same weight, you might be able to reproduce it, but it turns out that if I put all my weights as 1 or all my weights as 0, it takes longer to train. Where if you have random weights, they already have like a little bit of adjustment and ORs built in, and that will give us a better answer and train faster. Our first neuron takes a value of mileage and CC as inputs. So here comes our computation, whatever those inputs are, and we do that again with the second neuron with those values coming in. You can see here we have weight 3 and so on, and then our third neuron coming down, and of course our fourth neuron. So we're adding all these different values coming in here in our hidden layer. The process value from each neuron is sent to the output layer over weighted channels. So again, here's our weights coming in, and we have N1, N2, N3, and N4. Once again, the values are subjected to the activation function, and a single value is emitted as the output. On comparing the predicted value to the actual value, we clearly see that our network requires training. So here we have it that our bike price we put out, we thought it was worth $2,000 on our random weights, and the bike actually was $4,000 on there. I'm guessing that's not US dollars, because that'd be a very expensive bike, but maybe it is. There's some $2,000, $4,000 bikes out there. The cost function is calculated and backpropagation takes place. And this is pretty simple. You can look at that as our, we're subtracting one value from the other. We square it, and then we take half of that. And that is propagated back up, and each layer generates its own errors. Let's go back one, because you have your predicted predicted y and your actual y. That goes back to the first layer. And then based on the value of the cost function, certain weights are changed. So when we look at the next layer, that error is not the original 4,000 minus 2,000 squared divided by 2. This error is based on the error of each cell generated. How far off is that cell as far as its weights? We're not going to show you. It's actually a very complicated differential equation, and you can probably write it out if you wanted to. You just write out each formula. That goes into the next level, and you add them all together, and you can write it out all the way through. Computers make it so you don't have to. And our neural network is considered trained when the value for the cost function is minimum. So when we get our error way down as low as we can, that's when our neural network is trained. And just recently they've come up with all kinds of different means for measuring that particular value. A little bit beyond the scope of today's neural network, but you can actually see it. How far do you do this until the neural network doesn't need to be trained anymore, and you can overtrain a neural network. Now the tools that we're looking at automatically let you know when to stop, which is really nice. And that is just, like I said, we're at the beginning stages in neural networks, and it's just really cool what they can do now, and how much of it's automated, and how much of it is experimental right now. Let's take a look at gradient descent. But what approach do we take to minimize the cost function? So here we have a nice error thing coming in. This is our cost or our error. Let's start with plotting the cost function against the predicted value. And so you can see they fed in multiple y's, and these are the errors coming in and the cost of each of these inputs and changes going on. Note, we start at a random point on the curve. So usually you put in, you pick up your data and you randomly pick where to start in your data. A lot of times you just run it from the beginning because you're going through so much data, it's not that big of a deal, but you start with one point going in. So your forward propagation goes through, you're going to go ahead and find your cost or your error. It points that on the curve, and you can see how we're plotting it right here. Since the gradient at this point is positive, we may move right. So we're going to move a little bit to the right on here. And this time the gradient is negative, we move a little bit to the left. Eventually we try out the point where the gradient is 0. This is the least value of cost function. You have to be a little careful with this because this particular, they make it look nice and simple in this graph. Sometimes these curves look like stair steps, and so there is global minimums and then there is local. There might be a local point where the gradient is 0, but it's not the global one. So it might be way off to the left where it just happens to step down a little bit and you think you're in the right gradient. And with that we have all the right weights, and we can say our network is trained. So here we have just some major, these are some of the big names out there right now in development for deep learning platforms. TensorFlow, which we'll actually do an example in a minute. Deep Learning for J, which is in the Java platform. So if you're a Java programmer. By the way, as TensorFlow is accessed, most people are using Python to access it, but it is a system that's kind of separate from a lot of the programming languages, which makes it a lot more flexible as far as use. Deep Learning for J is Java based. And then Keras is just exploding right now. And this is interesting. Keras is working with TensorFlow. It actually can sit on top of TensorFlow, and it can also do its own thing. So if you're studying deep learning, you're getting into it, you'll want to know the basics of TensorFlow, but you also are going to want to know the upper level of Keras sitting on top of TensorFlow. We're just looking at TensorFlow today, though, in our example. And there's also Torch on there. There's a bunch more that we didn't list on here. Even sklearn, or the side package in Python, has a neural network you can program, a very basic one. And it is the same basic one that you could do in TensorFlow if you stripped everything out of it, and then TensorFlow has a lot of tools they've added in, and so has Keras. But we're going to be looking specifically at TensorFlow in our example. And TensorFlow is an open source tool used to define and run computations on what they call tensors. Very common language now. So more and more we see the term tensor as being a standard in the deep learning language. And this was originally developed by Google. So let's take a little bit big in there. What are tensors? Tensors are just another name for arrays. So a tensor of dimension 5. You can see here we have A, B, K, M, Q, whatever. So it's an array coming in. And the tensor of dimension 5, 4, more like a picture. Very common to see that in a picture. You can also see a tensor even more detailed in a picture as we go to the next one, tensor of dimension 3, 3, 3. This is 3D space. You might have a picture that also has colors. That might be the third dimension. You might have 4 dimensions because you have both your grid and your different color channels and your z-plot, you can see where you can now process a very high level set of data coming in, whether as an image or features. They could be features that have nothing to do with images. So there's a lot of stuff you can do now with the tensors coming in. Thus is where the term TensorFlow comes from. So we have right now the TensorFlow is the most popular library in deep learning. And I did mention Keras now works with TensorFlow. So there's a lot of stuff you can do between the two. It's an open source software library developed by Google. So they hit a roadblock and they realized, hey, this is an infant stage technology. You know, we thought it was going to be the next greatest thing and we were going to have a hold on it, but it's really infant as far as how it's applied and what we can do with it. Let's open source it so everybody can work on it. Let's take it to the next level. And that's really what open source does to a lot of these packages when they release them. And you can run on either a CPU or a GPU. So when we look at the details, if you have your graphic processing units, what's nice about those is they run a lot faster. The downside is you have to play with them a little bit to get them up and running, and it's a hardware upgrade. When we run it, I'll be running it in the CPU mode. I have played with it in my GPU on my personal computer. You know, it does increase the processing, but I did run into some version problems with my Python and stuff like that. And when I did finally work it out, I went back to the CPU because it didn't increase my speed enough for what I was working on. But in a larger group, you might be able to put that on. If you're working with a larger stack of computers, you might want to run it in the GPU. You can create a data flow graphs that have nodes and edges. So there's our edges coming in. We didn't talk about edges, but it's a very up-and-coming way of looking at your analytical data is how do different nodes connect? What do those edges look like in between them? And it's used for machine learning applications such as neural networks. It is mostly a neural network, but they have all kinds of tools which sit on top of our basic neural network. They have new stuff evolving into the TensorFlow library. So it's very much just exploding. Great time to jump into TensorFlow because there's all kinds of cool things they're doing with it and all kinds of cool applications you can now use TensorFlow for. So let's take a look at implementation in TensorFlow. And we're going to build a neural network to identify handwritten digits using the MNIST database, or the MNIST database. And that stands for Modified National Institute of Standards and Technology Database. It is a collection of 70,000 handwritten digits, and the digit labels identify each of the digits from 0 to 9. This is a cool example because it's simple enough that you could actually run this through some basic machine learning categorizing algorithms and train them. And you'll get about the same answer because, again, it's simple grid. The digits on the grid don't have a huge amount of variation like you would, say, an automated driving car looking at the environment. So you could still do this with a lot of your different linear models and stuff like that. You could solve this and you'll get about the same answer. When I ran a comparison between TensorFlow and between some basic regression models or category models in machine learning, they came up pretty even as far as their output. So this is kind of where we start to see the complexity of something coming in this case a tensor, or a grid of information, where the deep learning model does as good as the regular models. And when you get past this kind of complexity and features, suddenly the neural networks come up with better answers, better solutions, and a better build. And that's why there's such a move into neural networks, is we live in a complicated world, and it's just really cool what we can do with this. So the handwritten digits from the NIST database, they come in, the data set is used to train the machine, a new image of a digit is fed, and the digit is identified. And if you've looked at any of our other machine learning tools where we're doing training, where we train our model to fit and then you test it out, this will look pretty familiar. And there is some tools out there for, say, untrained categorizing, where it's just looking for features that fit together. So there are tools that don't need that training. But this is where, when we talk about neural networks, we do need to train them, and this is what we're looking at. So for this, I'm going to use the Anaconda Navigator, just because it's a very nice visual tool. You might be in PyCharm or one of your other IDEs for editing Python, because we are looking at Python TensorFlow. And under Anaconda, we have the Notebook, which is something we use pretty regularly, and they have the Jupyter Lab. The Jupyter Lab is the Jupyter Notebook, but with tabs and a few new features. So we'll be using the Jupyter Lab today. And under the environment, you'll want to go ahead and if you haven't yet, you'll see that I have a number of different setups in here. Right now I have the Python version 3.6 and the TensorFlow. In this case, I have TensorFlow 1.12. If we scroll down, you can see that. Here we go, TensorFlow, and it's version 1.12. And in here, if you haven't yet, you'll need to install those. Go in and just open our terminal. And if you've never used the Anaconda, or if you're in your other thing, you might have something simple like pip. Conda is what I use for my install, and you can simply do conda install TensorFlow. And that should bring in the most current version. Now, when I installed this a few months ago, Python version, I'm not going to run this because I already have it installed on here, Python version 3.7, the newest one out, still had a couple glitches with the TensorFlow. I believe they've fixed it as of writing of this, but I'm going to stick with 3.6 just so I don't get any surprises on there. So this is Python version 3.6 with TensorFlow 1.12 on here. And if you haven't installed it yet, you also want to install NumPy for this example. That's numbers Python, or NUMPY. You can just simply run an install on there. Keep in mind, if you're in Anaconda and you've created one of these environments specific to this, keep with Conda. If you're going to use Conda. If you're going to use pip, keep with pip. Don't install one package with pip and one under Conda, because that's how they track those version numbers and how they fit together, and you can end up with a problem. Pip doesn't see Conda and vice versa. So just keep that in mind when you're running your installs. We'll go ahead and open up Jupyter Lab, and we're going to launch that. So here's my Jupyter Lab. One of the really cool features of Jupyter Lab is you have tabs now, so you can open up multiple notebooks. And this is nice because I have my notes I'm working on and then our actual window we're looking in. And we'll go ahead and zoom in a little bit here. There we go. So you have a nice, hopefully easy to see fonts. And then we'll go ahead and do a simple, or get our imports out of the way. And so we're going to import our TensorFlow as TF. That's pretty much a standard for TensorFlow. NumPy, our numbers Python, as PY, and we'll import our matplot library as PLT. Again, these are very common. So if you see TF or PY or PLT, this is a standard that most people use. Do you have to? No. You could just do import NumPy instead of doing as PY. And then from TensorFlow.examples.tutorials, this is always nice because they actually include data set we're going to play with. So we're going to import input data. So there's our data coming in. That's all we're doing is telling it this is where it's coming from. And if we're going to tell where it's coming from, we need to go ahead and create a variable with that information in it. And we'll just call this MNIST or minced. You know, I don't really know how they pronounce that. I should probably look that up. It's a very common data set to use. And there's our input data, and we're going to read data sets. And this is, if you look at this, we imported input data from our TensorFlow. And so this is a TensorFlow read statement for their tutorials. So this isn't like some special Python setup. This is just their setup. It makes it easy to pull it in. So once we get into their data sets, we need to go ahead and tell it what kind of data set. And again, this is what we brought in, but it's going to be the NINST data. And this part is very important. One hot equals true. This means that instead of importing a value from 0 to 9, we evaluate the data set, it's going to bring it in as one hot. Whenever you see one hot encoder, we're flattening that out, and we have true false for 0, true false for 1, true false for 2. So our output, if you remember from our output from the slide we did earlier, in this case I grabbed the one for bike price. Doesn't really matter which one we use. This has one output, so we have our bike price. On this, we're going to have, instead of one output, we're going to have 10 outputs representing each of the digits in there. And this code really isn't going to show us anything. It's good to see what we're actually looking at. So let's go ahead and do a figure. AX equals, go into our plot library, subplots, 10, 10. And that is, if you remember, we talked about tensor being data coming in. This is a 10 by 10 grid, or 100 pixels on there. And if we're going to display it, let's go do K0 for I in range 10. Just a simple loop through on the data. Let's do, what is it, for J in range 10. So I actually misquoted that. 10 by 10 is not the actual size of the pixels. The actual pixels are going to be, when we look at the shapes, and we'll get into that in just a second here. We'll take a quick look at the shape on there. Turns out they're, they are, I believe, 28 by 28. So let's take a look at that. And we're just going to plot these. What are we looking at? What are we working with? As a data scientist, you should always be looking back at your data and seeing what it looks like and get that human perspective, because you just never know. You know, the computer might put something out that makes no sense, and at that point you want to go back and reevaluate what you did. So we're going to go ahead and plot. We're going to plot 10 of the digits by 10 of the digits, and here's our AX. We'll create the IJ on our subplots, and we're going to do an image show. We're going to look at the training image for images of K. And then we want to reshape this. We're going to reshape this, and we're going to reshape this 28 by 28. That's how I knew I had it wrong, is because I looked down my notes and I was like, oh no, that says 28, it's not 10 by 10. And I should know that already because I've done enough messing with this data set that I should remember. But it's 28 by 28, and the aspect we're going to do is auto. And this is all, if you look at this, here's our variable NIST. The NIST is coming from data set. So this is all part of the TF TensorFlow learning or examples tutorial in there. And then we'll go ahead and do K plus equals 1. So we just keep paging through our different images. And let's see what that looks like. Let's go ahead and do a plot show. And we'll go ahead and run this so we can take a look and see what we have here. And so we have a nice plot here, and you can just see that we have some random numbers showing up in each one of these little subplots. If you're wanting a copy of this code, put a note down in the YouTube video and let us know, or come visit us at www.simplilearn.com, and we'll send you out a copy of what we're working on. You can get a copy of that for your own setup. So now we've taken a look, and we can just see we have here's our pictures that are coming on. We plotted them so we have an idea of what we're looking at. Let's go ahead and let's look at the shape of the features. So when we have this, we have our NIST train images, and we'll do the shape on there. Let's take a look and just see what we're looking at as far as our count and everything. And so you can see here we have 55,000. That's basically how many images we have, and this by 784. And in this data set, there's also our labels. So let's take a look at that. We have our NIST train labels shape. Let's take a look and see what that looks like. And there we have 10, because there's 10 digits. So we brought in, that's our output we're looking at. And so we have, there we go, 55,000. They match. They should match, because you should have equal numbers in both of those. You know, here's our data in, and here's our answer. If you remember, this is a bunch of zeros, and with one, each one will be 0001, would be what, letter 4 or something like that. So let's take a look at what our one hot encoding did for the first observation. And this is, when we're exploring data, you really want to dig in there and just see what the heck am I looking at. So we're going to look at the labels, and this would be the first label that comes up, and we'll go ahead and run this. And we look at that, you can see this is what I'm talking about. 0, 0, or 1 is 0, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0, 7 equals 1. So our very first label is a 7, but our very first label comes up that it's a 7. And so we don't have like 0 through 9. We have a bunch of zeros and just the 1 to mark it as a 7 on here. So now we've kind of looked a quick look at the data. And in here you might ask some questions like, what is 784? 24 times 24. Remember, that's the size of our grid on there, or our tensor coming in. So 784 is the setup on there. And we've gone through all this viewing the data. We'll go ahead and start looking at our TensorFlow. So let's take our X variable. This is going to be our training set. We'll do a placeholder, and then we're going to have these come in as float. Now, if I remember correctly, they're actually, 0 or 1 for the values, because they're either, but we have them coming in as a float value, and we have a little bit of a shape coming in here, and there's our 784. So we let it know that this is what our input is for our TensorFlow, and this is our training set. So we'll just put a label on there to help us track that, train set, and then W, and with W we'll go ahead and do TF variables, and we'll do this as zeros. Variables, TF zeros, and we'll set this as 784 by 10, 10 being the output, 784 being our number of variables in, and this is our weights. Remember, we have a bias in there too. And I'll go back over this in just a second as we see how that fits together in our TensorFlow. And we'll do this one with our variables. Again, we have 10, so we're going to do the bias. We're going to do it the same kind of format and setup on here. And so we'll do that as TF zeros of 10. So we'll just create an array of 10 there, and this is our bias. So with these 3 lines, and they're coming out with the eager execution, which would bypass some of what we're doing. But this is important to understand, is the first thing you have to do with TensorFlow is we have to allocate a space for the variables. And our TF placeholder and our TF variable with our weights and our biases, this actually hasn't done anything yet. So all it is placeholders. That's why it's okay to use zeros. You could have just as easily used ones or anything anything else, and it wouldn't matter. The next stage is to go ahead and set up some of the functions going on. But before we do that, just note that this hasn't done anything. Even if I execute it, all it's done is created placeholders until we do the final initialization. And so we need to go ahead and set up, we'll do y equals tf.nn.softmax. And the code for this is tf.matmul xw plus b. And this is our sum. Let's just put a note here so we can keep track of what's going on. We're finding weighted sum of inputs plus the bias. So there's our plus b, the bias. And then we need to go ahead, let's do y underscore, and again another placeholder. And this one will set, it actually will put in as tf placeholder on here. tf placeholder float none 10. There's our one hot encoder going on there. So our 10 values coming out. And we'll do a cross entropy on here. And this is going to be minus tf reduce sum. And we'll do y, here's our y underscore, which is, remember we have your y output and your actual output. So this will be our y underscore times the tf log of y. And then finally, before we do the actual initialization of all our variables, we'll set up our train step. This equals our gradient descent optimizer. Very important. Remember we looked at that chart on our slides? And so we've set up all these formulas, and here's our gradient descent optimizer, and as it keeps looking for that 0 value. That's what we're doing with that particular formula. So let's take a look and see what we're doing here. We just put together all of our pieces for TensorFlow. And, you know, the devil's in the details. We have here our training set coming in. We have to put a placeholder on there. We have our variables with their weights. We have our biases coming out. And then we put in our the weighted sum. So here's summizing our summation here. Then we have our y variable output. So there's our y, how it works, and then of course the actual output on there. And then we have our cross entropy coming in, and that's our minus tf dot reduce sum, the y times the tf log of y. And then the training step, gradient descent optimizer. And we're using a 0.01 in this, and we're going to minimize cross entropy, so we're going to let it do all the work. So once we've set up all of these different layers, we've allocated for them, we need to go ahead and initialize them. So we're going to do an init tf initialize, and it's going to be all variables. One of the cool things is they're in the process of doing away with this. So all these steps would be bundled into one instead of having to have placeholders. You initialize them in the same process going on. And then finally, everything in TensorFlow is based on your session. Now this is changing, that there's other options to be able to run this. But we want to go ahead and do session. There's our TF, which is a TF session. And then we want to go ahead and do session run. And what are we going to run? Well, we did initialization of all our variables. So this is what we're running. And this is where actually, once we do this, we actually create our TensorFlow object. So this whole piece of code right here is our TensorFlow object. We have our input coming in with our weighted variables coming in, our softmax for our matmul going out. How does it add it together for our y value? And then we have the actual float value coming out, checking on our all the way down. So you can see all the different stages going through that we're setting up. And this is one of the reasons that a lot of people like TensorFlow, is because you can designate all these different pieces one step at a time. This is also one of the reasons people don't like TensorFlow, is because you have to designate all the different layers coming down. And there's a lot of steps being made right now to minimize this, to make it either easier to automate it or to allow you to do more complicated things. And all those steps are still at play, so it's worth looking into the more advanced version of what's going on with Keras on top of TensorFlow. It's also important to understand what's going on these individual levels if you're going to play with them. It's important to understand, hey, what's going on with the finding the weighted sum of the inputs plus the bias, because there's other ways to do that. There's all kinds of other tools in there now. But this is the basic setup that you want to do on a TensorFlow coming in. And we want to go ahead and just run and init our TensorFlow. So let's go ahead and do that. Let's run this. We do get a warning here because there's a move to use global variables. This is one of the changes they're making. But as far as this example, it's not going to make a difference because we're doing, once we initialize it, this is initializing our variables. And again, these are only placeholders up here until we initialize them. And I would highly suggest put a note down there, or go over to simplylearn.com and let them know and have them email you a copy of the code so you can actually play with this code right here, because this is the body of what's going on in TensorFlow. This is the build in neural networks. And then once we've done that, now comes kind of the fun part, is we need to go ahead and train it. So we've created our TensorFlow, we've created our network, and now we need to go ahead and train it. So let's put together that training code, and let's just do for I in range 1000, 0 to 1000. So we're just going to look at the first 1000 in our training. And the way we pull that data from our mince train next batch of 100, so you look at this, we're going to be doing groups of 100, and then there's going to go through 1000 of them. This is very important that TensorFlow builds this in. This is one of the downsides of doing sklearn or one of the older packages, is they don't let you batch groups in. They wanted to have it all up front, and then you have to build your own batch programs right now. This lets us go ahead and do that, and you can see here we have batch x of s, batch y of s. So there's our x and our y. You can look at this as our training of x and our train of y, or the data in and the answer in. And then we simply do our session run. So here's our session that we've created. We're going to run it, and we want to do the train step. Remember, we initialized our train step up here in our TF, and so there's our train step. Feed is a dictionary coming in, which we're going to create right here. Is x is our batch, x of our sample, comma, and our y underscore is going to be our batch of our y sample. And so this goes through, and we've now hit the run button, and we've trained our session. We've trained this setup on here. And once we've trained it, then we need to go ahead and find out how good our accuracy was and actually start running some predictions through there. So we'll go ahead and create a correct prediction, and this is where our tf.equal, we'll use our argmax y of 1 and tf argmax of y of underscore of 1 to help us get the correct predictions on there. And then we want to use that to feed into an accuracy. And so our accuracy is going to be tf reduce mean, and we'll take that and we'll do a cast, and this is the correct prediction that we're sending in there, and it is a float value. Keep it simple, and let's go ahead and print this out so we can see what we're looking at. So what are we printing out? We need to do a session run. This session run is going to be on the accuracy. Where did accuracy comes from? This is we're casting our TF on there with the correct predictions on that. So here's our accuracy. Feed in, so it needs a dictionary for the data coming in. We're going to create our dictionary, and x is going to be our NIST test images, and y underscore there is going to be our NIST.test labels. Let me just double check and make sure I have that typed in there correctly. There we go, and let's go ahead and run that and see what comes up, and we end up with a 0.9165 for our accuracy, which means our trained neural network does a pretty good job letting us know what these different symbols are, and guessing that a 7 and a 3 and a 4, something that as humans we kind of take for granted. I even have trouble reading this, so I don't know if I would be able, like that first one, I would sit there for a long time figuring out that's a 7 versus a 2. That could have easily been a 2 to me. So you can see we do a pretty good job analyzing this data, and this is used to analyze something very complicated on these images, very different than just a straight value of cost of sales, and here's our return and our marketing. We can now create this nice neural network that does all kinds of cool things.
Let's move on to the differences between TensorFlow, Keras, and PyTorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them, while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. PyTorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, PyTorch works at the same speed as TensorFlow, as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and PyTorch. In computation speed, both TensorFlow and PyTorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. PyTorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. PyTorch is a little hard for beginners but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and PyTorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. PyTorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow Serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow Serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow Serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow Serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and PyTorch. PyTorch uses PyTorch Mobile, which makes deployment easy, but again, for TensorFlow, deployment is way easier as TensorFlow Serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi step, error prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by PyTorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the PyTorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or PyTorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy, but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn for beginners. PyTorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While PyTorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. PyTorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices, combined with the lack of Python overhead, makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
Then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below.
So many things out there that the 1.0 really needed. So when we start talking about TensorFlow 1.0 versus 2.0, I guess you would need to know this for a legacy programming job if you're pulling apart somebody else's code. The first thing is that TensorFlow 2.0 supports eager execution by default. It allows you to build your models and run them instantly. And you can see here from TensorFlow 1 to TensorFlow 2, we have almost double the code to do the same thing. So if I want to do with tf.session or TensorFlow session as a session, the session run, you have your variables, your session run, you have your tables initializer, and then you do your model fit. X train, Y train, and then your validation data, your X value, Y value, and your epochs and your batch size. All that goes into the fit. And you can see here where that was all just compressed to make it run easier. You can just create a model and do a fit on it, and you only have like that last set of code on there. So it's automatic. That's what they mean by the eager. So if you see the first part and you're like, what the heck is all this session thing going on? That's TensorFlow 1.0. And then when you get into 2.0, it's just nice and clean. If you remember from the beginning, I said Keras on our list up there. And Keras is the high-level API in TensorFlow 2.0. Keras is the official high-level API of TensorFlow 2.0. It has incorporated Keras as tf.keras. Keras provides a number of model building APIs such as sequential, functional, and subclassing, so you can choose the right level of abstraction for your project. And we'll hopefully touch base a little bit more on this, sequential being the most common form. That is, your layers are going from one side to the other. So everything's going in a sequential order. Functional is where you can split the layers. So you might have your input coming on one side, it splits into two completely different models, and then they come back together. And one of them might be doing classification, the other one might be doing just linear regression kind of stuff, or a basic reverse propagation neural network, and then those all come together into another layer, which is your neural network reverse propagation setup. Subclassing is the most complicated as you're building your own models, and you can subclass your own models into Keras. So very powerful tools here. This is all the stuff that's been coming out currently in the TensorFlow Keras setup. A third big change we're going to look at is that in TensorFlow 1.0, in order to use TF layers as variables, you would have to write TF variable block. So you'd have to predefine that.
In TensorFlow 2, you just add your layers in under the sequential, and it automatically defines them as long as they're flat layers. Of course, this changes a little bit as the more complicated tensor you have coming in, but all of it's very easy to do, and that's what 2.0 does a really good job of. And here we have a little bit more on the scope of this, and you can see how TensorFlow 1 asks you to do these different layers and values. If you look at the scope and the default name, you start looking at all the different code in there to create the variable scope. That's not even necessary in Tensor 2.0. So you'd have to do 1 before you do what you see the code in 2.0. In 2.0, you just create your model. It's a sequential model, and then you can add all your layers in. You don't have to pre-create the variable scope. So if you ever see the variable scope, you know that came from an older version. And then we have the last two, which is our API cleanup and the autograph. In the API cleanup, TensorFlow 1, you could build models using tfgans, tfapp, tfcontrib, tfflags, etc. In TensorFlow 2, a lot of APIs have been removed. And this is they just cleaned them up because people weren't using them, and they've simplified them. And that's your tfapp, your tflags, and your tflogging are all gone. So those are 3 legacy features that are not in 2.0. And then we have our TF function and autograph feature. In the old version, TensorFlow 1.0, the Python functions were limited and could not be compiled or exported, re-imported. So you were continually having to redo your code, and you couldn't very easily just put a pointer to it and say, hey, let's reuse this. In TensorFlow 2, you can write a Python function using the TF function to mark it for the JIT compilation, for the Python JIT, so that TensorFlow runs it as a single graph. Autograph feature of TF function helps to write graph code using natural Python syntax. Now we just threw in a new word in you, graph. Graph is not a picture of a person. You'll hear graph X and some other things. Graph is what are all those lines that are connecting different objects. So if you remember from before, where we had the different layers going through sequentially, each one of those white lined arrows would be a graph X. That's where that computation is taken care of, and that's what they're talking about. And so if you had your own special code or Python way that you're sending that information forward, you can now put your own function in there instead of using whatever function they're using. In neural networks, this would be your activation function, although it could be almost anything out there depending on what you're doing. Next, let's go for hierarchy and architecture, and then we'll cover 3 basic tools in TensorFlow before we roll up our sleeves and dive into the example. So let's just take a quick look at TensorFlow toolkits and their hierarchy. At the high level, we have our object-oriented API. So this is what you're working with. You have your TF Keras, you have your estimators. This sits on top of your TF layers, TF losses, TF metrics. So you have your reusable libraries for model building. This is really where TensorFlow shines, is between the Keras, running your estimators, and then being able to swap in different layers. Your losses, your metrics, all of that is so built into TensorFlow. It makes it really easy to use. And then you can get down to your low-level TF API. You have extensive control over this. You can put your own formulas in there, your own procedures or models in there. You could have it split. We talked about that earlier. So with the 2.0, you can now have it split one direction where you do a linear regression model, and then go to the other where it does a neural network. And maybe each neural network has a different activation set on it. And then it comes together into another layer, which is another neural network. So you can build these really complicated models, and at the low level, you can put in your own APIs. You can move that stuff around. And most recently, we have the TF code can run on multiple platforms. And so you have your CPU, which is basically like on the computer I'm running on. I have 8 cores and 16 dedicated threads. I hear they now have one out there that has over 100 cores. So you have your CPU running, and then you have your GPU, which is your graphics card. And most recently, they also include the TPU setup, which is specifically for TensorFlow models, neural network kind of setup. So now you can export the TF code, and it can run on all kinds of different platforms for the most diverse setup out there. And moving on from the hierarchy to the architecture, in the TensorFlow 2.0 architecture, we have, you can see on the left, this is usually where you start out with, and 80% of your time in data science is spent. pre-processing data, making sure it's loaded correctly and everything looks right. So the first level in TensorFlow is going to be your read and pre-processed data, your TF data feature columns. This is going to feed into your TF Keras or your pre-made estimators, and kind of you have your TensorFlow hub that sits on top of there so you can see what's going on. Once you have all that set up, you have your distribution strategy. Where are you going to run it? Are you going to be running it on just your regular CPU? Are you going to be running it with the GPU added in? Like I have a pretty high-end graphics card, so it actually grabs that GPU processor and uses it. Or do you have a specialized TPU set up in there that you paid extra money for? It could be if you're later on, when you're distributing the package, you might need to run this on some really high processors because you're processing it at a server level for, let's say, you might be processing this at you're distributing it, not the distribution strategy, but you're distributing it into a server where that server might be analyzing thousands and thousands of purchases done every minute. And so you need that higher speed to give them a recommendation or a suggestion so they can buy more stuff off your website. Or maybe you're looking for data fraud analysis working with the banks. You want to be able to run this at a high speed so that when you have hundreds of people sending their transactions in, it says, hey, this doesn't look right. Someone's scamming this person and probably has their credit card. So when we're talking about all those fun things, we're talking about saved model. We were talking about that earlier, where it used to be when you did one of these models, it wouldn't truncate the float numbers the same. And so a model going from one, you build the model on your machine in the office, and then you need to distribute it. And so we have our TensorFlow serving cloud on premium. That's what I was talking about if you're like a banking or something like that. Now they have TensorFlow Lite, so you can actually run a TensorFlow on an Android or an iOS or Raspberry Pi. Little breakout board there. In fact, they just came out with a new one that has a built-in, this is a little mini TPU with the camera on it so it can pre-process a video. So you can load your TensorFlow model onto that. Talking about an affordable way to beta test a new product. You have the TensorFlow JS, which is for browser and node server. So you can get that out on the browser for some simple computations that don't require a lot of heavy lifting, but you want to distribute to a lot of endpoints. And now they also have other language bindings. So you can now create your TensorFlow backend, save it, and have it accessed from C, Java, Go, C#, Rust, R, or from whatever package you're working on. So we kind of have an overview of the architecture and what's going on behind the scenes, and in this case, what's going on as far as distributing it. Let's go ahead and take a look at 3 specific pieces of TensorFlow. And those are going to be constants, variables, and sessions. So very basic things you need to know and understand when you're working with the TensorFlow setup. So constants in TensorFlow. In TensorFlow, constants are created using the function constant. In other words, they're going to stay static the whole time, whatever you're working with. The syntax for constant value, dtype 9, shape equals none, name constant, verify shape equals false. That's kind of the syntax you're looking at. And we'll explore this with our hands-on a little more in depth. And you can see here we do z equals tf.constant, 5.2, name equals x, dtype is a float. That means that we're never going to change that 5.2. It's going to be a constant value. And then we have our variables in TensorFlow. Variables in TensorFlow are in memory buffers that store tensors. And so we can declare a 2x3 tensor populated by ones. You could also do constants this way, by the way. So you can create an array of ones for your constants. I'm not sure why you do that, but you might need that for some reason. In here we have v equals tf.variables, and then in TensorFlow you have tf.ones, and you have the shape, which is 2, 3, which is then going to create a nice 2x3 array that's filled with ones. And then of course you can go in there and they're variables, so you can change them. It's a tensor, so you have full control over that. And then you of course have sessions in TensorFlow. A session in TensorFlow is used to run a computational graph to evaluate the nodes. And remember, when we're talking about graph or graph X, we're talking about all that information then goes through all those arrows and whatever computations they have that take it to the next node. And you can see down here where we have import TensorFlow as TF. If we do x equals a tf.constant of 10, we do y equals a tf constant of 2.0 or 20.0, and then you can do z equals tf.variable and it's a tf.add x comma y. And then once you have that set up in there, you go ahead and init your tf global variables initializer with tf session as session. You can do a session run init, and then you print the session run y. And so when you run this, you're going to end up with, of course, the 10 plus 20 is 30. And we'll be looking at this a lot more closely as we actually roll up our sleeves and put some code together. So let's go ahead and take a look at that. And for my coding today, I'm going to go ahead and go through Anaconda, and then I'll use specifically the Jupyter Notebook on there. And of course, this code is going to work whatever platform you choose, whether you're in a notebook, the Jupyter Lab, which is just the Jupyter Notebook but with tabs for larger projects. We're going to stick with Jupyter Notebook. PyCharm, whatever it is you're going to use in here. You have your Spider and your Qt console for different programming environments. The thing to note, it's kind of hard to see, but I have my main Pi 3.6. Right now, when I was writing this, TensorFlow works in Python version 3.6. If you have Python version 3.7 or 3.8, you're probably going to get some errors in there. Might be that they've already updated it and I don't know it, and I have an older version. But you want to make sure you're in a Python version 3.6 in your environment. And of course, in Anaconda, I can easily set that environment up. Make sure you go ahead and pip in your TensorFlow, or if you're in Anaconda, you can do Anaconda install TensorFlow to make sure it's in your package. So let's just go ahead and dive in and bring that up. This will open up a nice browser window. I just love the fact I can zoom in and zoom out depending on what I'm working on, making it really easy to adjust a demo for the right size. Go under New, and let's go ahead and create a new Python. And once we're in our new Python window, this is going to leave it untitled. Let's go ahead and import. Import TensorFlow as TF. At this point, we'll go ahead and just run it real quick. No errors. Yay! No errors. I do that whenever I do my imports because I invariably will have opened up a new environment and forgotten to install TensorFlow into that environment or something along those lines. So it's always good to double check. And if we're going to double check that, it's also good to know what version we're working with. And we can do that simply by using the version command in TensorFlow, which you should know is probably intuitively the TF dot underscore underscore version underscore underscore. And it always confuses me because sometimes you do TF dot version for one thing, you do TF dot underscore version underscore for another thing. This is a double underscore in TensorFlow for pulling your version out. And it's good to know what you're working with. We're going to be working in TensorFlow version 2.1.0. And I did tell you we were going to dig a little deeper into our constants, and you can do an array of constants. And we'll just create this nice array, a equals tf.constant, and we're just going to put the array right in there, 4361. We can run this, and now that is what a is equal to. And if we want to just double check that, remember we're in Jupyter Notebook where I can just put the letter A, and it knows that that's going to be print. Otherwise, you'd surround it in print. And you can see it's a TF tensor. It has the shape, the type, and the array on here. It's a 2x2 array. And just like we can create a constant, we can go ahead and create a variable. And this is also going to be a 2x2 array. And if we go ahead and print the V out, we'll run that. And sure enough, there's our TF variable in here. Then we can also, let's just go back up here and add this in here. I could create another tensor, and we'll make it a constant this time. And we'll go ahead and put that in over here. We'll have B TF constant. And if we go ahead and print out V and B, we go ahead and run that. And this is an interesting thing that happens in here. You'll see right here when I print them both out, what happens is it only prints the last one unless you use print commands. So important to remember that in Jupyter Notebooks. But we can easily fix that by go ahead and print and surround V with brackets. And now we can see with the two different variables we have the 3152, which is a variable, and this is just a flat constant, so it comes up as a TF tensor shape 2 kind of 2. And that's interesting to note that this label is a TF.tensor and this is a TF variable. So that's how it's looking in the back end when you're talking about the difference between a variable and a constant. The other thing I want you to notice is that in variable, we capitalize the V, and with the constant, we have a lowercase c. Little things like that can lose you when you're programming and you're trying to find out, hey, why doesn't this work? So those are a couple little things to note in here. And just like any other array in math, we can do like a concatenate the different values here. And you can see we can take AB concatenated. You just do a tf.concat values, and there's our AB axes on 1. Hopefully you're familiar with axes and how that works when you're dealing with matrices. And if we go ahead and print this out, you'll see right here we end up with a tensor. So let's put it in as a constant, not as a variable. And you have your array 4378 and 6145. It's concatenated the two together. And again, I want to highlight a couple things on this. Our axes equals 1. This means we're doing the columns. So if you had a longer array, like right now we have an array that is like, has a shape 1, whatever it is, 2, 2. Axes 0 is going to be your first one, and axes 1 is going to be your second one. And it translates as columns and rows. If we had a shape, let me just put the word shape here. So you know what I'm talking about, and it's very clear. And this is, I'll tell you what, I spend a lot of time looking at these shapes and trying to figure out which direction I'm going in and whether to flip it or whatever. So you can get lost in which way your matrix is going and which is column, which is rows. Are you dealing with the third axis or the second axis? Axis 1, 0, 1, 2, that's going to be our columns. And if you can do columns, then we also can do rows, and that is simply just changing the concatenate. We'll just grab this one here and copy it. We'll do the whole thing over. Control copy, Control V, and changes from axis 1 to axis 0. And if we run that, you'll see that now we concatenate by row as opposed to column. And you have 4, 3, 6, 1, 7, 8, 4, 7. So it just brings it right down and turns it into rows versus columns. You can see the difference there, your output. This really, you want to look at the output sometimes just to make sure your eyes are looking at it correctly and it's in the format. I find visually looking at it is almost more important than understanding what's going on, because conceptually your mind just too many dimensions sometimes. The second thing I want you to notice is this says a NumPy array. So TensorFlow is utilizing NumPy as part of their format as far as Python's concerned. And so you can treat this output like a NumPy array because it is just that. It's going to be a NumPy array. Another thing that comes up more than you would think is filling one of these with zeros or ones. And so you can see here we just create a tensor tf.zeros. And we give it a shape. We tell it what kind of data type it is. In this case, we're doing an integer. And then if we print out our tensor, again, we're in Jupyter, so I can just type out tensor. And I run this, you can see I have a nice array of with shape 3, 4 of zeros. One of the things I want to highlight here is integer 32. If I go to the TensorFlow data types, I want you to notice how we have float 16, float 32, float 64, complex. If we scroll down, you'll see the integer down here, 32. The reason for this is that we want to control how many bits are used in the precision. This is for exporting it to another platform. So what would happen is I might run it on this computer where Python does a float to indefinite, however long it wants to. And then we can take it, but we want to actually say, hey, we don't want that high precision. We want to be able to run this on any computer. And so we need to control whether it's a TF float 16. In this case, we did an integer 32. We could also do this as a float. So if I run this as a float 32, that means this has a 32-bit precision. You'll see 0 point whatever. And then to go with zeros, we have ones, if we're going from the opposite side, and so we can easily just create a TensorFlow with ones. And you might ask yourself, why would I want zeros and ones? And your first thought might be to initiate a new tensor. Usually we initiate a lot of this stuff with random numbers because it does a better job solving it. If you start with a uniform set of ones or zeros, you're dealing with a lot of bias. So be very careful about starting a neural network for one of your rows or something like that with ones and zeros. On the other hand, I use this for masking. You can do a lot of work with masking. You can also have, it might be that one tensor row is masked, 0 is false, 1 is true, or whatever you want to do it. And so in that case, you do want to use the 0s and 1s. And there are cases where you do want to initialize it with all 0s or all 1s, and then swap in different numbers as the tensor learns. So it's another form of control. But in general, you see 0s and 1s, you usually are talking about a mask over another array. And just like in NumPy, you can also do reshapes. So if we take our, remember this is shaped 3, 4, maybe we want to swap that to 4, 3. And if we print this out, you will see, let me just go and do that, Control V, let me run that. And you'll see that the order of these is now switched. Instead of 4 across, now we have 3 across and 4 down. And just for fun, let's go back up here where we did the 1s. And I'm going to change the 1s to tf.randomUniform. And we'll go ahead and just take off, well, we'll go ahead and leave that. We'll go ahead and run this. And you'll see now we have 0.0441. And this way you can actually see how the reshape looks a lot different. 0.041, 0.15, 0.71. And then instead of having this one, it rolls down here to the 0.14. And this is what I was talking about. Sometimes a lot of times you fill these with random numbers. And so this is the random.uniform is one of the ways to do that. Now, I just talked a little bit about this float32 and all these data types. One of the things that comes up, of course, is recasting your data. So if we have a D-type float32, we might want to convert these to integers because of the project we're working on. I know one of the projects I've worked on ended up wanting to do a lot of round off so that it would take a dollar amount or a float value and then have to round it off to a dollar amount. So we only wanted 2 decimal points. And in which case you have a lot of different options. You can multiply by 100 and then round it off or whatever you want to do. There's a lot of, or then convert it to an integer was one way to round it off. Kind of a cheap and dirty trick. So we can take this and we can take the same tensor and we'll go ahead and create a as an integer. And so we're going to take this tensor, we're going to tf.cast it, and if we print tensor, and then we're going to go ahead and print our tensor. Let me just do a quick copy and paste. And when I'm actually programming, I usually type out a lot of my stuff just to double check it. In doing a demo, copy and paste works fine, but sometimes be aware that copy and paste can copy the wrong code over. Personal choice, depends on what I'm working on. And you can see here we took a float 32, 4.6, 4.2, and so on, and it just converts it right down to a integer value. Sorry, integer 32 setup. And remember we talked about a little bit about reshape as far as flipping it, and I just did 4, 3 on the reshape up here, and we talked about axis 0, axis 1. One of the things that is important to be able to do is to take one of these variables. We'll just take this last one, tensor as integer, and I want to go ahead and transpose it. And so I can do, we'll do a equals tf.transpose. And we'll do our tensor integer in there. And then if I print the A out and we run this, you'll see that it's the same array, but we've flipped it so that our columns and rows are flipped. This is the same as reshaping. So when you transpose, you're just doing a reshape. What's nice about this is that if you look at the numbers, the columns, when we went up here and we did the reshape, they kind of roll down to the next row. So you're not maintaining the structure of your matrix. So when we do a reshape up here, they're similar, but they're not quite the same. And you can actually go in here and there's settings in the reshape that would allow you to turn it into a transform. So when we come down here, it's all done for you. And so there are so many times you have to transpose your digits that this is important to know that you can just do that. You can flip your rows and columns rather quickly here. And just like NumPy, you can also do your different math functions. We'll look at multiplication. And so we're going to take matrix multiplication of tensors. We'll go ahead and create A as a constant, 5839. And we'll put in a vector V, 4, 2. And we could have done this where they matched, where this was a 2 by 2 array, but instead we're going to do just a 2 by 1 array. And the code for that is your tf.matmul, so matrix multiplier. And we have a times v, and if we go ahead and run this, let's make sure we print out our av on there. And if we go ahead and run this, you'll see that we end up with 36 by 30. And if it's been a while since you've seen the matrix math, this is 5 times 4 plus 8 times 2, 3 times 4 plus 9 times 2. And that's where we get the 36 and 30. Now, I know we're covering a lot really quickly as far as the basic functionality. So the matrix, or your matrix multiplier, is a very commonly used back-end tool as far as computing different models or linear regression, stuff like that. One of the things is to note is that just like in NumPy, you have all of your different math. So we have our TF math, and if we go in here, we have functions, we have our cosines, absolute, angle, all of that's in here. So all of these are available for you to use in the TensorFlow model. And if we go back to our example, and let's go ahead and pull, let's do some multiplication. That's always good. We'll stick with our AV, our constant A and our vector V. And we'll go ahead and do some bitwise multiplication, and we'll create an AV, which is A times V. Let's go and print that out. And you can see coming across here, we have the 4, 2 and the 5, 8, 3, 9, and it produces 20, 32, 618. And that's pretty straightforward. If you look at it, you have 4 times 5 is 20, 4 times 8 is 32. That's where those numbers come from. We can also quickly create an identity matrix, which is basically your main values on the diagonal being 1s and 0s across the other side. Let's go ahead and take a look and see what that looks like. And we can do, let's do this. So we're going to get the shape. This is a simple way, very similar to your NumPy. You can do a.shape, and it's going to return a tuple, in this case our rows and columns. And so we can do a quick print. We'll do rows. Oops. And we'll do columns. And if we run this, you can see we have 3 rows, 2 columns. And then if we go ahead and create an identity matrix, the script for that, got a wrong button there. The script for that looks like this, where we have the number of rows equals rows, the number of columns equals columns, and D type is a 32. And then if we go ahead and just print out our identity, you can see we have a nice identity column with our ones going across here. Now, clearly we're not going to go through every math module available, but we do want to start looking at this as a prediction model and seeing how it functions. So we're going to move on to a more of a direct setup where you can actually see the full TensorFlow in use. For that, let's go back and create a new setup. And we'll go in here, new Python 3 module. There we go. Bring this out so it takes up the whole window, because I like to do that. Hopefully you made it through that first part and you have a basic understanding of TensorFlow as far as being a series of NumPy arrays. You got your math equations and different things that go into them. We're going to start building a full setup as far as the NumPy, so you can see how Keras sits on top of it and the different aspects of how it works. The first thing we want to do is we're going to go ahead and do a lot of imports. Date times, warnings, SciPy. SciPy is your math, so the back-end scientific math. Warnings, because whenever we do a lot of this, you have older versions, newer versions, and so sometimes when you get warnings, you want to go ahead and just suppress them. We'll talk about that if it comes up on this particular setup. And of course, date time. Pandas, again, is your data frame. Think rows and columns. We import it as PD. NumPy is your numbers array, which of course TensorFlow is integrated heavily with. Seaborn for our graphics, and the Seaborn as SNS is going to be set on top of our matplot library, which we import as MPL. And then of course we're going to import our matplot library pyplot as PLT. And right off the bat, we're going to set some graphic colors. Patch force edge color equals true. The style, we're going to use the 538 style. You can look this all up. When you get into matplot library, into Seaborn, there are so many options in here. It's just kind of nice to make it look pretty when we start up. That way we don't have to think about it later on. And then we're going to take, we have our MPLRC. We're going to put a patch edge color, dim gray line width. Again, this is all part of our graphics here in our setup. We'll go ahead and do an interactive shell. Node interactivity equals last expression. Here we are, PD for pandas. Options display max columns. So we don't want to display more than 50. And then our matplot library is going to be inline. This is a Jupyter Notebook thing, the matplot library inline. Then warnings, we're going to filter our warnings, and we're just going to ignore warnings. That way when they come up, we don't have to worry about them. Not really what you want to do when you're working on a major project. You want to make sure you know those warnings and then filter them out and ignore them later on. And if we run this, it's just going to be loading all that into the background. So that's a little back-end kind of stuff. Then what we want to go ahead and do is we want to go ahead and import our specific packages that we're going to be working with, which is under Keras. Now remember, Keras kind of sits on TensorFlow. So when we're importing Keras and the sequential model, we are in effect importing TensorFlow underneath of it. We just brought in the math, probably should have put that up above. And then we have our Keras models. We're going to import sequential. Now, if you remember from our slide, there was 3 different options. Let me just flip back over there so we can have a quick recall on that. And so in Keras, we have sequential, functional, and subclassing. So remember those 3 different setups in here we talked about earlier. And if you remember from here, we have sequential, where it's going one TensorFlow layer at a time. You go kind of think of it as going from left to right or top to bottom or whatever direction it's going in. But it goes in one direction all the time. Where functional can have a very complicated graph of directions. You can have the data split into 2 separate tensors, and then it comes back together into another tensor. All those kinds of things. And then subclassing is really the really complicated one, where now you're adding your own subclasses into the tensor to do external computations right in the middle of like a huge flow of data. But we're going to stick with sequential. It's not a big jump to go from sequential to functional. But we're running a sequential TensorFlow. And that's what this first import is here. We want to bring in our sequential. And then we have our layers. And let's talk a little bit about these layers. This is where Keras and TensorFlow really are happening. This is what makes them so nice to work with, is all these layers are pre-built. So from Keras, we have layers import dense. From Keras, layers import LSTM. When we talk about these layers, Keras has so many built-in layers. You can do your own layers. The dense layer is your standard neural network. By default, it uses ReLU for its activation. And then the LSTM is a long short-term memory layer. Since we're going to be looking probably at sequential data, we want to go ahead and do the LSTM. And if we go into Keras and we look at their layers, this is a Keras website, you can see as we scroll down for the Keras layers that are built in, we can get down here and we can look at, let's see, here we have our layer activation, our base layers. Activation, layer weights, there's a lot of stuff in here. We had the ReLU, which is the basic activation that was listed up here for layer activations. You can change those. And here we have our core layers and our dense layers. You have an input layer, a dense layer. And then we've added a more customized one with the long-term, short-term memory layer. And of course, you can even do your own custom layers in Keras. There's a whole functionality in there if you're doing your own thing. What's really nice about this is it's all built in. Even the convolutional layers, this is for processing graphics. There's a lot of cool things in here you can do. This is why Keras is so popular. It's open source, and you have all these tools right at your fingertips. So from Keras, we're just going to import a couple layers, the dense layer and the long short-term memory layer. And then, of course, from sklearn, our scikit, we want to go ahead and do our min-max scaler, standard scaler for pre-editing our data, and then metrics just so we can take a look at the errors and compute those. Let me go ahead and run this, and that just loads it up. We're not expecting anything from the output. And our file coming in is going to be airquality.csv. Let's go ahead and take a quick look at that. This is in OpenOffice. It's just a standard, you can do Excel, whatever you're using for your spreadsheet. And you can see here we have a number of columns, a number of rows. It actually goes down to like 8,000. The first thing we want to notice is that the first row is kind of just a random number put in going down. Probably not something we're going to work with. The second row is Bandung. I'm guessing that's a reference for the profile. If we scroll to the bottom, which I'm not going to do because it takes forever to get back up, they're all the same. The same thing with the status. The status is the same. We have a date, so we have a sequential order here. Here is the jam, which I'm going to guess is the timestamp on there. So we have a date and time. We have our O3, CO, NO2 reading, SO2, NO, CO2, VOC, and then some other numbers here, PM1, PM2.5, PM4, PM10. Without actually looking through the data, some of this I can guess is like temperature, humidity. I'm not sure what the PMs are. But we have a whole slew of data here. So we're looking at air quality as far as an area and a region, and what's going on with our date timestamps on there. And so code-wise, we're going to read this into a pandas data frame. So our data frame, DF is a nice abbreviation commonly used for data frames, equals pd.read_csv, and then the path to it just happens to be on my D drive, separated by spaces. And so if we go ahead and run this, we'll print out the head of our data. And again, this looks very similar to what we were just looking at. Being in Jupyter, I can take this and go the other way. Make it real small so you can see all the columns going across and we can get a full view of it. Or we can bring it back up in size. That's pretty small on there. Overshot. But you can see it's the same data we were just looking at. We're looking at the number, we're looking at the profile, which is the Bandung, the date, we have a timestamp, our O3 count, CO, and so forth on here. And this is just your basic pandas printing out the top 5 rows. We could easily have done 3 rows, 5 rows, 10, whatever you want to put in there. By default, that's 5 for pandas. Now, I talk about this all the time, so I know I've already said it at least once or twice during this video. Most of our work is in pre-formatting data. What are we looking at? How do we bring it together? So we want to go ahead and start with our date time. It's come in 2 columns. We have our date here, and we have our time. And we want to go ahead and combine that. And then we have, this is just a simple script in there that says combine date time. That's our formula we're building. We're going to submit our pandas data frame and the tab name. When we go ahead and do this, that's all of our information that we want to go ahead and create. And then goes for I in range df shape 0. So we're going to go through the whole setup, and we're going to list tab append df location I. And here is our date going in there, and then return the numpy array list tab dtypes date time 64. That's all we're doing. We're just switching this to a date timestamp. And if we go ahead and do df date time equals combine date time, and then I always like to print. We'll do df head just so we can see what that looks like. And so when we come out of this, we now have our setup on here, and of course it's edited on to the far right. Here's our date time. You can see the format's changed. So we've added in the date time column, and we've brought the date over, and we've taken this format here, and it's an actual variable with a 000 on here, Well, that doesn't look good. So we need to also include the time part of this. We want to convert it into hourly data. So let's go ahead and do that. To do that, to finish combining our date time, let's go ahead and create a little script here to combine the time in there. Same thing we just did. We're just creating a numpy array, returning a numpy array, and forcing this into a date time format. And we can actually spend hours just going through these conversions. How do you pull it from the pandas data frame? How do you set it up? So I'm kind of skipping through it a little fast because I want to stay focused on TensorFlow and Keras. Keep in mind, this is like 80% of your coding when you're doing a lot of this stuff is going to be reformatting these things, resetting them back up so that it looks right on here. And, it just takes time to get through all that. But that is usually what the companies are paying you for. That's what the big bucks are for. And we want to go ahead and a couple things going on here is we're going to go ahead and do our date time. We're going to reorganize some of our setup in here, convert into hourly data. We just put a pause in there. Now remember, we can select from DF our different columns we're going to be working with, and you're going to see that we actually dropped a couple of the columns. Those ones I showed you earlier, they're just repetitive data. So there's nothing in there that exciting. And then we want to go ahead and we'll create a second data frame here. Let me just get rid of the DF head. And DF2 is we're going to group by date time, and we're looking at the mean value. And then we'll print that out so you can see what we're talking about. We have now reorganized this, so we put in date time 03 CO. So now this is in the same order as it was before. And you'll see the date time now has our 00, same date 1, 2, 3, and so on. So it's grouped the data together so that it's a lot more manageable and in the format we want. And in the right sequential order. And if we go back to, there we go, our air quality, you can see right here we're looking at these columns going across. We really don't need, since we're going to create our own date time column, we can get rid of those. These are the different columns of information we want, and that should reflect right here in the columns we picked coming across. So this is all the same columns on there. That's all we've done is reformatted our data, grouped it together by date, and then you can see the different data coming out set up on there. And then as a data scientist, first thing I want to do is get a description. What am I looking at? And so we can go ahead and do the df2 describe. And this gives us our, describe gives us our basic data analytics information we might be looking for, like what is the mean, standard deviation, minimum amount, maximum amount. We have our first quarter, second quarter, and third quarter numbers also in there. So you can get a quick look at a glance describing the data or descriptive analysis. And even though we have our quantile information in here, we're going to dig a little deeper into that. We're going to calculate the quantile for each variable. We're going to look at a number of things for each variable. We'll see right here, Q1, we can simply do the quantile 0.25%, which should match our 25% up here. And we're going to be looking at the min, the max, and we're just going to do this. It's basically we're breaking this down for each different variable in there. One of the things that's kind of fun to do, we're going to look at that in just a second. Let me put the next piece of code in here. We got to clean out some of our, we're going to drop a couple things, our last rows and first row, because those usually they have a lot of null values, and the first row is just our titles. So that's important. It's important to drop those rows in here. And so this right here, as we look at our different quantiles, again, it's the same, we're still looking at the 25 quantile here. We're going to do a little bit more with this. So now that we've cleared off our first and last rows, we're going to go ahead and go through all of our columns, and this way we can look at each column individually. And so we'll just create a Q1, Q3, min, max, min IQR, max IQR, and calculate the quantile of I of DF2. We're basically doing the math that they did up here, but we're splitting it apart. That's all this is. And this happens a lot because you might want to look at individual. If this was my own project, I would probably spend days and days going through what these different values mean. One of the biggest data science things we can look at that's important is use your common sense. If you're looking at this data and it doesn't make sense, and you go back in there and you're like, wait a minute, what the heck did I just do? At that point, you probably should go back and double check what you have going on. Now, we're looking at this, and you can see right here, here's our attribute for our O3. So we've broken it down. We have our Q1 5.88, Q3 10.37. If we go back up here, here's our 5.8. We've rounded it off. 10.37's in there. So we've basically done the same math, just split it up. We have our minimum and our max IQR, and that's computed, let's see, where is it? Here we go. Q1 minus 1.5 times IQR. And the IQR is your Q3 minus Q1. So that's the difference between our two different quarters. And this is all data science. As far as the hard math, we're really not, we're actually trying to focus on Keras and TensorFlow. You still got to go through all this stuff. I told you 80% of your programming is going through and understanding what the heck happened here. What's going on? What does this data mean? And so when we're looking in that, we're going to go ahead and say, hey, we've computed these numbers, and the reason we've computed these numbers is if you take the minimum value and it's less than your minimum IQR, that means something's going wrong there. And that usually, in this case, is going to show us an outlier. So we want to go ahead and find the minimum value. If it's less than the minimum IQR, it's an outlier. And if the max value is greater than the max IQR, we have an outlier. And that's all this is doing. Low outlier is found, minimum value, high outlier is found. Really important, actually. Outliers are almost everything in data sometimes. Sometimes you do this project just to find the outliers because you want to know crime detection. What are we looking for? We're looking for the outliers. What doesn't fit a normal business deal? And then we'll go ahead and throw in, just threw in a lot of code. Oh my goodness. So we have, if your max is greater than IQR, print outlier is found. What we want to do is we want to start cleaning up these outliers. And so we want to convert, create a convert nan, x max IQR equals max underscore IQR, min IQR equals min IQR. So this is just saying this is the data we're going to send. That's all that is in Python. And if x is greater than the max IQR and x is less than the min IQR, x equals null. We're going to set it to null. Why? Because we want to clear these outliers out of the data. Now, again, if you're doing fraud detection, you would do the opposite. You would be cleaning everything else that's not in that series so that you can look at just the outlier. And then we're going to convert the nan hum. Again, we have x, max IQR is 100%, min IQR is min IQR. If x is greater than max IQR and x is less than min IQR, again, we're going to return a null value. Otherwise, it's going to remain the same value x equals x. And you can see as we go through the code, if I equals our HUM, then we go ahead and do, that's a column specific to humidity. That's your HUM column. Then we're going to go ahead and run a map on there and convert the non-HUM. You can see here this is just cleanup. We found out that humidity probably has some weird values in it. We have our outliers. That's all this is. And so when we go ahead and finish this and we take a look at our outliers and we run this code here, we have a low outlier, 2.04. We have a high outlier, 99.06. Outliers have been interpolated. That means we've given them a new value. Chances are these days when you're looking at something like these sensors coming in, they probably have a failed sensor in there. Something went wrong. That's the kind of thing that you really don't want to do your data analysis on. So that's what we're doing is we're pulling that out and then converting it over and setting it up method linear. So we interpolate method linear is it's going to fill that data in based on a linear regression model of similar data. Same thing with this up here with the df2i interpolate. That's what we're doing. Again, this is all data prep. We're not actually talking about TensorFlow. We're just trying to get all our data set up correctly so that when we run it, it's not going to cause problems or have a huge bias. So we've dealt with outliers specifically in humidity. And again, this is one of these things where when we start running, we ran through this, you can see down here that we have our outliers found, high-low outliers, we've migrated them in. We also know there's other issues going on with this data. How do we know that? Some of it's just looking at the data, playing with it until you start understanding what's going on. Let's take the temp value, and we're going to go ahead and use a logarithmic function on the temp value. And it's interesting because it's like, how do you heck do you even know to use logarithmic on the temp value? That's domain specific. We're talking about being an expert in air care. I'm not an expert in air care. It's not what I go look at. I don't look at air care data. In fact, this is probably the first air care data setup I've looked at. But the experts come in there and they come to you and say, hey, in data science, this is a exponentially variable on here, so we need to go ahead and do transform it and use a logarithmic scale on that. So at that point, that would be coming from your data. Here we go. Data science programmer overview, does a lot of stuff connecting the database and connecting in with the experts. Data analytics, a lot of times you're talking about somebody who is a data analysis, might be all the way usually a PhD level. Data science, programming level interfaces, database manager, that's going to be the person who's your admin working on it. So when we're looking at this, we're looking at something they've sent to me and they said, hey, domain, air care, this is a skew because the data just goes up exponentially and affects everything else. And we'll go ahead and take that data. Let me just go ahead and run this. Just for another quick look at it, we have our, we'll do a distribution DF. We'll create another data frame from the temp values and then from a data set from the log temp. So we can put them side by side. And we'll just go ahead and do a quick histogram. And this is kind of nice. Plot a figure size. Here's our PLT from Matplot library. And then we'll just do a distribution underscore DF. There's our data frames. This is nice because it just integrates the histogram right into pandas. Love pandas. And this is a chart you would send back to your data analyst and say, hey, is this what you wanted? This is how the data is converting on here. As a data scientist, the first thing I note is we've gone from a 10, 20, 30 scale to 2.5, 3.0, 3.5 scale. And the data itself has kind of been adjusted a little bit based on some kind of a skew on there. So let's jump into, we're getting a little closer to actually doing our Keras on here. We'll go ahead and split our data up. And this, of course, is any good data scientists. You want to have a training set and a test set. And we'll go ahead and do the train size. We're going to use 0.75% of the data. Make sure it's an integer. You don't want to take a slice as a float value. Give you a nice error. And we'll have our train size is 75%, and the test size is going to be, of course, the train size minus the length of the data set. And then we can simply do train comma test. Here's our data set, which is going to be the train size, the test size. And then if we go ahead and print this, let me just go ahead and run this. We can see how these values split. It's a nice split of 1298 and then 433 points of value that are going to be for our setup on here. And if you remember, we're specifically looking at the data set. Where did we create that data set from? That was from up here. That was what we called the logarithmic value of the temp. That's where the data set came from. So we're looking at just that column with this train size and the test, with the train and test data set here. And let's go ahead and do convert an array of values into a data set matrix. We're going to create a little setup in here. We create our data set. Our data set's going to come in. We're going to do a look back of 1. So we're going to look back one piece of data going backward. Then we have our data X and our data Y. For I in range, length of data set, look back minus 1. This is creating, let me just go ahead and run this. Actually, the best way to do this is to go ahead and create this data and take a look at the shape of it. Let me go ahead and just put that code in here. So we're going to do a look back 1. Here's our train X, our train Y, and it's going to be adding the data on there. And then when we come up here and we take a look at the shape, there we go, and we run this piece of code here, we look at the shape on this, and we have a new, slightly different change on here, but we have a shape of x, 1296, 1, shape of y, train y, test x, test y. And so what we're looking at is that the x comes in, and we're only having a single value out. We want to predict what the next one is. That's what this little piece of code is here for. What are we looking for? Well, we want to look back one. That's the what we're going to train the data with is yesterday's data. Yesterday says, hey, the humidity was at 97%. What should today's humidity be at? If it's 97% yesterday, is it going to go up or is it going to go down today? If 97, does it go up to 100? What's going on there? And so we're looking forward to the next piece of data, which says, hey, tomorrow's is going to, today's humidity is this. This is what tomorrow's humidity is going to be. That's all that is. All that is stacking our data so that our y is basically x plus 1, or x could be y minus 1. And then a couple things to note is our x data. We're only dealing with the one column, but you need to have it in a shape that has it by the columns. So you have the two different numbers. And since we're doing just a single point of data, we have, and you'll see with the train y, we don't need to have the extra shape on here. Now, this is going to run into a problem. And the reason is that we have what they call a time step. And the time step is that long-term, short-term memory layer. So we're going to add another reshape on here. Let me just go down here and put it into the next cell. And so we want to reshape the input array in the form of sample time step features. We're only looking at one feature. And I mean, this is one of those things when you're playing with this, you're like, why am I getting an error in the numpy array? Why is this giving me something weird going on? So what we're going to do is we're going to add one more level on here. Instead of being 1299.1, we want to go one more. And when they put the code together in the back, you can see we kept the same shape, the 1299. We added the one dimension, and then we have our train x shape 1. And this could have, depends again on how far back in the long short-term memory you want to go. That is what that piece of code is for, and that reshape is. And you can see the new shape is now 1299.11 versus the 1299.1. And then the other part of the shape, 432.11. Again, this is our x in, and of course our test x. And then our y is just a single column because we're just doing one output that we're looking for. So now we've done our 80%. That's all the writing all the code, reformatting our data, bringing it in. Now we want to go ahead and do the fun part, which is we're going to go ahead and create and fit the LSTM neural network. And if we're going to do that, the first thing we need is we're going to need to go ahead and create a model. And we'll do this sequential model. And if you remember, sequential means it just goes in order. That means if you have two layers, the layers go from layer 1 to layer 2, or layer 0 to layer 1. This is different than functional. Functional allows you to split the data and run two completely separate models and then bring them back together. We're doing just sequential on here. And then we decided to do the long short-term memory. And we have our input shape, which it comes in. Again, this is what all this switching was. We could have easily made this 1, 2, 3, or 4 going back as far as the end number on there. We just stuck to going back 1. And it's always a good idea when you get to this point, where the heck is this model coming from? What kind of models do we have available? And let me go ahead and put the next model in there, because we're going to do two models. And the next model is going to go ahead and we're going to do dense. So we have model equals sequential, and then we're going to add the LSTM model, and then we're going to add a dense model. And if you remember from the very top of our code, where we did the imports, oops, there we go, our cross, this is it right here. Here's our importing a dense model, and here's our importing an LSTM. Now, just about every TensorFlow model uses dense. Your dense model is your basic forward propagation, reverse propagation error, where it does reverse propagation to program the model. So any of your neural networks that you've already looked at that looks and says, here's the error, and sends the error backwards, that's what this is. The long short-term memory is a little different. The real question that we want to look at right now is, where do you find these models? What kind of models do you have available? And so for that, let's go to the Keras website, which is the keras.io. If you go under API/layers, and I always have to do a search, just search for Keras API layers. It'll open up and you can see we have your base layers right here, class, trainable, weights, all kinds of stuff like there. Your activation, so a lot of your layers you can switch how it activates. ReLU, which is like your smaller arrays, or if you're doing convolutional neural networks, the convolution usually uses a ReLU. Your sigmoid, all the way up to softmax, softplus, all these different choices as far as how those are set up. And what we want to do is we want to go ahead, and if you scroll down here, you'll see your core layers, and here is your dense layer. So you have an input object, your dense layer, your activation layer, embedding layer. This is your kind of your one setup on there that's most common. Convolutional neural networks, or convolutional layers, these are like for doing image categorizing, so trying to find objects in a picture, that kind of thing. We have pooling layers, so as you have the layers come together, usually you bring them down into a single layer, although you can still do like global max pooling 3D. And there is just, I mean, this list just goes on and on. There's all kinds of different things hidden in here as far as what you can do. And it changes. You know, you go in here and you just have to do a search for what you're looking for, and figure out what's going to work best for you as far as which project you're working on. Long short-term memory is a big one, because this is when we start talking about text. What if someone says what comes after the cat in the hat, little kid's book there, starts programming it, and so you really want to know not only what's going on, but it's going to be something that has a history. The history behind it tells you what the next one coming up is. Now, once we've built all our different, we built our model, we've added our different layers we want in there, play with it. Remember, if you're in functional, you can actually link these layers together and they branch out and come back together. If you do the sub setup, then you can create your own different model. You can embed a model in there that might be linear regression. You can embed a linear regression model as part of your functional split, and then have that come back together with other things. So we're going to go ahead and compile your model. This brings everything together. We're going to put in what the loss is, which we'll use the mean squared error. And we'll go ahead and use the atom optimizer. Clearly, there's a lot of choices on here depending on what you're doing. And just like any of these different prediction models, if you've been doing any scikit from Python, you'll recognize that we have to then fit the model. So what are we doing in here? We're going to send in our train X, our train Y. We're going to decide how many epochs we're going to run it through. 500 is probably a lot for this. I'm guessing it'd probably be about 200 or 300, probably do just fine. Our batch size. So how many different, when you process it, this is the math behind it. If you're in data analytics, you might try to know what this number is as a data scientist, where I haven't had the PhD level math that says this is why you want to use this particular batch size. You kind of play with this number a little bit. You can dig deeper into the math, see how it affects the results depending on what you're doing. And there's a number of other settings on here. We did verbose 2. I'd have to actually look that up to tell you what verbose means. I think that's actually the default on there, if I remember correctly. There's a lot of different settings when you go to fit it. The big ones are your epoch and your batch size. Those are what we're looking for. And so we're going to go ahead and run this. And this is going to take a few minutes to run, because it's going through 500 times through all the data. So if you have a huge data set, this is the point where you're kind of wondering, oh my gosh, is this going to finish tomorrow? If I'm running this on a single machine and I have a terabyte of data going into it, if this is my personal computer and I'm running a terabyte of data into this, this is running rather quickly through all 500 iterations. But at a terabyte of data, we're talking something closer to days, week, even with a 3.5 gigahertz machine in 8 cores, it's still going to take a long time to go through a full terabyte of data. And then we want to start looking at putting it into some other framework like Spark or something that will be able to process on there more across multiple processors and multiple computers. And if we scroll all the way down to the bottom, you're going to see here's our square mean error of 0.0088. If we scroll way up, you'll see it kind of oscillates between 0.0888 and 0.0089. It's right around 250 where you start seeing that oscillation where it's really not going anywhere. So we really didn't need to go through a full 500 epochs. If you're retraining this stuff over and over again, it's kind of good to note where that error zone is so you don't have to do all the extra processing. Of course, if you're going to build a model, we want to go ahead and run a prediction on it. So let's go ahead and make our prediction. And remember, we have our training test set and our test set, we have the train X and the train Y for training it, or train predict, and then we have our test X and our test Y going in there. So we can test to see how good it did. And when we come in here, we have, you'll see right here, we go ahead and do our train predict equals model predict train X and test predict model predict test X. Why would we want to run the prediction on train X? Well, it's not 100% on its prediction. We know it has a certain amount of error, and we want to compare the error we have on what we programmed it with the error we get when we run it on new data that's never seen, the model's never seen before. And one of the things we can do, we go ahead and invert the predictions. This helps us level it off a little bit more. Get rid of some of our bias. We have train predict equals an NP exponential M1, the train predict, and then train Y equals the exponential M1 for train Y, and then we do again that with train test predict and test Y. Again, reformatting the data so that it all matches, and then we want to go ahead and calculate the root mean square error. So we have our train score, which is your math square root times the mean square root error, train Y and train predict. And again, we're just, this is just feeding the data through so we can compare it. And the same thing with the test. And let's take a look at that, because really the code makes sense. If you're going through it line by line, you can see what we're doing. But the answer really helps to zoom in. So we have a train score, which is 2.40 of our root mean square error. And we have a test score of 3.16 of the root mean square error. If these were reversed, if our test score is better than our training score, then we've overtrained. Something's really wrong. At that point, you got to go back and figure out what you did wrong. Because you should never have a better result on your test data than you do on your training data. And that's why we put them both through. That's why we look at the error for both the training and the testing. When you're going out and quoting your publishing this and you're saying, hey, how good is my model? It's the test score that you're showing people. This is what it did on my test data that the model had never seen before. This is how good my model is. And a lot of times you actually want to put together like a little formal code where we actually want to print that out. And if we print that out, you can see down here, test prediction and standard deviation of data set, 3.16 is less than 4.40. I have to go back, and we're up here. If you remember, we did the square means error. This is standard deviation. That's why these numbers are different. It's saying the same thing that we just talked about. 3.16 is less than 4.40. Model is good enough. We're saying, hey, this model is valid. We have a valid model here. So we can go ahead and go with that. And along with putting a formal print out of there, we want to go ahead and plot what's going on. And this, we just want a pretty graph here so that people can see what's going on. When I walk into a meeting and I'm dealing with a number of people, they really don't want these numbers. They don't want to say, hey, standard deviation, unless you know what statistics are. You might be dealing with a number of different departments. Head of sales might not work with standard deviation or have any idea what that really means number-wise. And so at this point, we really want to put it in a graph so we have something to display. And with displaying, you got to remember that we're looking at the data today going into it and what's going to happen tomorrow. So let's take a quick look at this. We're going to go ahead and shift the train predictions for plotting. We have our train predict plot, NP empty like data set, train predict plot, set it up with null values. It's just kind of a weird thing where we're creating the data groups as we like them. and then putting the data in there is what's going on here. So we have our train predict plot, which is going to be our look back, our length, plus look back. We're just is going to equal train predict. So we're creating this. Basically, we're taking this and we're dumping the train predict into it. So now we have our nice train predict plot. And then we have the shift test predictions for the plotting. We're going to continue more of that. Oops, looks like I put it in here double. No, it's just, yeah, they put it in here double. Didn't mean to do that. We really only need to do it once. Oh, here we go. This is where the problem was, is because this is the test predict. So we have our training prediction. We're doing the shift on here. And then the test predict, we're going to look at that. Same thing, we're just creating those two data sets. Test predict plot, length prediction, set up on there. And then we're going to go through the plotting, the original data set, and the predictions. So we have a time axis. Always nice to have your time set on there. Set that to the time array, time axis lap. All this is setting up the time variable for the bottom. And then we have a lot of stuff going on here as far as setting up our figure. Let's go ahead and run that, and then we'll break it down. We have on here our main plot. We have two different plots going on here. The ISPU going up and the data, and the ISPU here with all these different settings on it. And so when we look at this, we have our AX1, that's the main plot. I mean our AX, that's the main plot, and we have our AX1, which is the secondary plot over here. So we're doing a figure PLT, or PLT.figure, and we're going to dump those two graphs on there. And so we take, and if you go through the code piece by piece, which we're not going to do, we're going to do the data set here, exponential, reverse exponential, so that it looks correctly. We're going to label it the original data set. We're going to plot the train predict plot. That's what we just created. We're going to make that orange, and we'll label it train prediction. Test predict plot, we're going to make that red and label it test prediction, and so forth. Set our ticks up. This actually just put ticks, time axis gets its ticks. The little marks there going along the axes, that kind of thing. And let's take a look and see what these graphs look like. And these are just kind of fun. You know, when you show up into a meeting and this is the final output and you say, hey, this is what we're looking at. Here's our original data in blue. Here's our training prediction. You can see that it trains pretty close to what the data is up there. I would also probably put a like a little timestamp and do just right before and right after, where we go from train to test prediction. And you can see with the test prediction, the data comes in red. And then you can also see what the original data set looked like behind it and how it differs. And then we can just isolate that here on the right. That's all this is just the test prediction on the right. And it's, you know, you'll see with the original data set, there's a lot of peaks we're missing and a lot of lows we're missing. But as far as the actual test prediction, it does pretty good. It's pretty right on. You can get a good idea of what to expect for your ISPU. And so from this, we would probably publish it and say, hey, this is what you expect, and this is our this is a range of error. That's the kind of thing I'd put out on a daily basis. Maybe we predict the cells are going to be this, or maybe weekly. So you kind of get you kind of flatten the data coming out, and you say, hey, this is what we're looking at. The big takeaway from this is that we're working with, let me go back up here. Oops, oh, too far. There we go. Is this model here. This is what this is all about. We worked through all of those pieces, all the tensor flows, and that is to build this sequential model. And we're only putting in the 2 layers. This can get pretty complicated. If you get too complicated, it never verges into a usable model. So if you have like 30 different layers in here, there's a good chance you might crash it, kind of thing. So don't go too haywire on that. And that you kind of learn as you go. Again, it's domain knowledge, and also starting to understand all these different layers and what they mean. The data analytics behind those layers is something that your data analysis professional would come in and say, this is what we want to try. But I tell you, as a data scientist, a lot of these basic setups are common, and I don't know how many times working with somebody and they're like, oh my gosh, if I only did a tangent H instead of a ReLU activation, I worked for 2 weeks to figure that out. Well, as a data science, I can run it through the model in 5 minutes instead of spending 2 weeks doing the math behind it. So that's one of the advantages of data scientists is we do it from programming side, and a data analytics is going to look for it. How does it work in math? And this is really the core right here of TensorFlow and Keras, is being able to build your data model quickly and efficiently. And of course, with any data science, putting out a pretty graph so that your shareholders, again, we want to take and reduce the information down to something people can look at and say, oh, that's what's going on. They can see what's going on as far as the dates and the change in the ISPU.
Now, let's talk a little bit about recurrent neural networks. So neural networks are of different types. We have CNN, we have RNN, ANN, so on. Now, RNN is one type of neural network. RNN stands for recurrent neural network. The networks like CNN and ANN are feed-forward network, which means that the information pretty much only goes from left to right or from front to back, whichever way you call it. Whereas in case of recurrent neural network, there will be some information traveling backwards as well. So that is why it is known as a recurrent neural network. And each of these types have a specific application. So for example, convolutional neural networks or CNN are very good for doing image processing and object detection using for video and images. Whereas recurrent neural networks are pretty good for doing NLP or speech recognition and so on. Okay. So for the next few minutes, we will kind of focus on recurrent neural networks, and we will see an example of how we can use RNN to do a time series analysis. So in a typical neural network, this is how it looks, right? So where you have a neuron and then the inputs are coming to the neuron, and then you have an output which goes to other neurons in the other layers. In case of recurrent neural network, what happens is you have the inputs, let's say at a given point in time, but then a part of the previous output also gets fed in along with the inputs for the given time. Now, this can be a little confusing. So let's see if we can take a little expanded view of this. So this is another view of one single neuron, which is what is known as in an unfolded manner. Okay. So if we are getting inputs or data over a period of time, then this is how the neuron will look. Remember, these are not three neurons. This is one neuron, and it is what is known as, it is shown in a unfolded way. Okay. We have unfolded this single neuron over a period of time. So at a given time, let's say t minus 1, an input of xt minus 1 is fed to the neuron, and it gets an output of yt minus 1. Then the next instant, which is xt at a time t, right? There is an input of xt, and then there is an output of yt. So this is a single neuron, but is displayed in an unfolded way. So this is like expanding it over a period of time. So let's start with this part here. This particular neuron gets an input at an instant t minus 1. Let's say time is equal to t minus 1. It gets an input of xt minus 1, and it gives an output of yt minus 1. Then when we go to the instant t, here it gets an input of xt, and it also additionally gets an input from this previous time frame t minus 1. So this yt minus 1 gets fed here, and that results in yt. All right. Then when we go to the time t plus 1, there is an input of xt minus 1 at that given time, plus the input from the previous time frame, which is a time frame of t. That also gets fed in here, and then we get an output of yt plus 1. Okay. So let me explain once again. This is a single neuron. So these are not three different neurons. A single neuron seen over a period of time from t minus 1 to t plus 1. And unlike a regular feed-forward neuron, which only gets x, in this case, the input is x, and also another input which is coming from the previous time frame, and that is what this loop is. In this, on the left hand side diagram, this loop is indicating that. Okay. So on the right hand side, it is represented in an unfolded way. Okay. So the input, if we take a time frame t, for example, is not only xt, which is the input, which is the normal input at the time frame t, but it is also getting an input from the previous time frame, which is this yt minus 1 is also being fed as an input. That is the key differentiator here. Okay. Similarly, at the instant t plus 1, it is getting a normal input of xt plus 1 plus this yt is actually being fed here, and then the output comes as yt plus 1. Okay, so this is the construct of a recurrent neural network. Now, recurrent neural networks again can be of different subtypes. It can be one-to-one, one-to-many, many-to-one, and many-to-many, depending on what kind of application we want to use. One of the examples is like the stock price. So you're feeding, so there is only one input. Only thing is it is spread over a period of time. So you're feeding the stock price input. That is what comes here as an input. And you get an output, which is again the stock price, which is probably predicted over the next 2 days, 3 days, or 10 days, or whatever. So the number of outputs and inputs is the same. There is only one input. There is only one output. Only thing is it is spread over a time. So variables are not many. Then you have one-to-many. So there is one input, but you're expecting multiple outputs. What is an example of this? Let's say you want to caption an image. So how do you want to do that? What is the input that will go here? Is just an image, which is one input. But what is the output you're looking for? You're looking for a phrase maybe, right? Not just a word, but a phrase. So it's like cat is sitting on a mat, right? So the image is, there is only one image which consists of the cat sitting on a mat, but the output are like maybe 3 or 4 words, which is saying the cat is sitting on a mat. So this is one-to-many, right? Then you can have many-to-one. Examples of this are like you're feeding some text and you want to know the output, whether the text is, what kind of sentiment is expressed by the text. It could be positive, it could be negative. So that's the output you're looking for. So you feed a large number of words, maybe the text may consist of words or lines or whatever. So that is what is the multiple inputs. But the output, all it says is the sentiment is positive. So it is just one output, or the sentiment is negative, just one output, right? So this is many-to-one. Then we have many-to-many. So what is an example of this? Let's say you want to do some translation. So how do you do a translation? You feed in a sentence maybe in a particular language, English, and then you want a sentence actually in another language. So that is like there are multiple inputs. One sentence can consist of multiple words, and the output also is a sentence consisting of multiple words. All right. So how do we implement RNN? This is an example of implementing an RNN for a particular use case. So in our particular example, we have the data about milk production over a few months, and using RNN, we want to predict, because this is time series analysis. So RNN is good to do time series analysis. So using RNN, we want to predict what will be the milk production in the future. So let us see how we can do that. I will first take you quickly through the slides, and then I will actually run this in a Jupyter notebook. The code, I will run it in the Jupyter notebook. So this is how it looks, the code looks. So while this is TensorFlow, you still use the standard Python libraries like NumPy and Pandas and even Matplotlib to do some initial processing, getting the data, processing it, cleaning it, whatever. All that can be still done within the same program. So that's what we're doing here. We're importing some libraries like NumPy and Pandas, and then we read the data file. And if we plot the data, we see here it is the data for the years 1962 to 75, and we can see that there is a certain trend, right? So this is how a typical time series data would look. Again, some of you, if you're not familiar with time series and time series analysis and so on, I would recommend you to go through some videos around that, which will make it easy to understand this. So this is how a typical time series data would look. In this case, it is nothing but there is only one variable, which is milk production, and it is spread across several years. So it's going from 1962 to 75, and that value has been plotted. So if you see, there is a certain kind of a trend here, which is basically going upwards, and there will be some seasonality. So time series data has these 3 components, right? So it will have a trend, it will have a seasonality, and then it will have some randomness. So that's what this graph is showing. And now if we want to perform analysis on this, time series analysis on this, first thing we need to do is split the data into train and test. And in this case, we will just use a straight straightforward method, which is taking the data for the first 13 years. So the idea here is we need to train our model, right? This is time series data. So and we want to predict for the future. So the way we need to use this is we have to take the data for a certain period of time and train our model. And then we use a part of the known data so that we can then ask our model to predict for that duration and compare it with the known information. So what do we mean by that? So here, if you see this data, I will show you in the notebook as well, Jupyter notebook as well. This has 13 years of data. So what we are doing is we are taking the first 12 years and using that as our training set, right? So 12 years we are doing, and this has about, I think, 14 years of data. So we are taking 13 years of data for training purpose, and then we are using the last 1 year, remaining 1 year of data for testing purpose. Because here what we can do is this 1 year data, we know the values, right? Because if we want to compare the accuracy or anything like that, we need to know the values. So in this case, we know the values of this one particular year. So we will use that. But at the same time, we train the model for 13 years of data. And for the 14th year, we will ask our model to predict and then compare it with this known value so that we know how accurate our model is. I hope that makes sense. Okay. So that's what we are doing here. 156 is nothing but 12 into 13. On a monthly basis, we get the data. The next step is to scale the data. This is all regular data manipulation, data munching activity. And then you split it. You are basically assigning the train and test data to the scaled variables. And then you need to read the data in batches. So it is very important, as I mentioned earlier also, that instead of reading the entire data in one shot, you feed the data in batches. So in order to do that, we are writing a function for that. That's all we are doing here. So that is still here what we have done is regular Python programming. There is no TensorFlow as of now here. Okay, so far what we have done is preparation, data munching. Now what we are doing is actually training our model. So this is where TensorFlow now comes into picture. So we are importing, first step is to import the TensorFlow library. So this is how you do it, import TensorFlow STF. And then you can define some variables or constants, whichever way. Now here, of course, there are a couple of ways of doing it. You can create them as TensorFlow nodes, but that is a little bit of an overhead. We will just use the regular Python variables or constants. So here I am creating regular Python variables and I'm saying number of inputs is 1. So instead of hard coding, I'm just storing them as variables. So this is number of inputs is 1, number of time steps is 12, number of neurons is 100, and so on, right? And then learning rate is 0.03 and number of iterations we are saying is 4000. Then we create placeholders. Now we will be storing the independent variables in X and the dependent variables in Y, and this we will read from an external file. Remember, I told you placeholders are used for getting data from outside and then feeding it to our model. So that's the reason we have two placeholders, one for reading the X values and another for reading the Y values. In this step, we are only just creating the nodes, right? So this is just creating the graph. And similarly, we are mentioning what is the loss function and what is the optimizer and how to run the optimizer. And once that is done, you are initializing the variables and then you're creating a saver variable or a saver instance. So saver is basically nothing but in machine learning, you can train your model and you can save it for later use. So that's where the saving comes into play. We will see how to use that as well. And then the last step is to create your session and run this graph, right? So we are initializing the variables. Remember this, we run init, so which is nothing but this one. So we are initializing the variables, whatever are there. Instead of hard coding, remember in earlier case we were hard coding how many iterations. So here we are saying for the given number of iterations which are stored in this, maybe how many iterations we said is, what is the value of iterations? This is training iterations is 4000. So we specify that based on the number of training iterations. Next batch will basically fetch the data and then we run the session. We are basically saying train is the node which we will run in the session, and this will basically train our model, and this is more for printing. Every 100 times you print it. That's all. There's nothing more to it. So for example, the output would look somewhat like this. This is for 0, this for 100, next for 200, and so on. Okay, and then you save the model. You remember saver we created, so you save the model for later use. So this is our test data. Remember, we are doing this on training data, right? So once the training is done, we then try to create the inference on the test data so that we can compare how accurate this is, right? So this is how the test set would look, and then we will basically restore this model, okay, because in the previous slide we created the model and we stored it. So now we have to restore the model and then run our test data against it and see what are the values that are predicted, what are the y values, and then compare with x to see the accuracy. So train seed is what we are seeing here. So that is what will have the predicted values, and these predicted values, what we want to do is we want to create an additional column, because remember we need to compare, because we want to find out the accuracy of this model. So we need to compare the predicted values with the actual value. So what we are doing here is adding another column called generated and assign a value to that. All right, so this is the result of the prediction, and then if we need to reshape, because we have to show this in the form of monthly results. So that's what we are doing here, and once we generate the results and then display it, we can actually see it month wise here, and the actual and the generated values. Okay, so we create a data frame which is a combination of the actual values and the predicted values from the test set. And then we can plot to see how the trend is. As you can see, pretty much the actual value is in blue color and the generated or predicted value, the curve is in yellow color. The trend is maintained. So it will probably, it's not 100% accurate, but the trend is maintained. All right, so let's do one thing. Let's go into the Jupyter notebook and take a look at how this works in TensorFlow environment. Actually, the code, I will walk you through the code. This is my Jupyter notebook, and the data is taken from this particular link. In case you're interested, you can download it from there. And this is the data for the years 1962 to 75. The first thing we do is import these libraries, because before we start with the actual TensorFlow activity, we need to prepare the data and so on. So for that, you can use your regular Python libraries, which are like NumPy, Pandas, and so on. So that's what we are doing here. And then we read the data using Pandas into a data frame. So this is a data frame, milk is a data frame, and we will do some quick exploratory analysis just to see how our data is looking. Initial 5 records that we'll get, 1, 2, 3, 4, 5, that is head. So it goes from 1962 January to 1962 May. Once we rechange, or basically we need to split this into month specifically separately. So that's what we are doing here, date to time. So we kind of do a little bit of a reindexing, and then if we plot this, this is how the data look. As you can see, there is a clear upward trend, and there is some seasonality and so on, but anyway, we will not break that up into those components. We will just use RNN to predict and test. Okay, so the next thing is to check some, if we can run like an info, it will tell us what is the information about this data set. So let us just run that. Okay, so it is just telling us how many total columns and what is the size of the file and so on and so forth. Again, in case you're interested in doing some exploratory analysis. So what we'll do next is we will take the 13 years of data for our training data set. So what are we going to do now? Let me step back. So what have we seen here? We have seen that there are 168 records, so which is nothing but 14 years of data. We now have to split this into our training and test data set. So how do we do that? I think in case of time series, we cannot do it like 80-20 like we do in normal splitting in normal machine learning process. Here it is time series data. So what we are going to do is we will take out of this 14 years, we will take the first 13 years of data and we will use that for training, and then we will test it with the last, which is the 14th year data. We will use it for testing. Okay, so that's what we are going to do here. So let's split that. So training set will consist of my 156 records, which is nothing but 13 into 12, right? My 13 years of data I'm taking for training, and then my test set will consist of the bottom 12 observations, which is last 1 year of data, which is the 14th year. Okay, so that's now done. Training and test splitting is done. The next step is to do some normalizing, which is basically we'll use our scaling, rather we will use min-max scaler, and we will just scale the data. And now we do it for both test as well as train. Now we are ready to create our RNN model. But before that, one quick thing, in order to fetch the data, we have to create a function. So that's what we are doing here. We create a function called next batch. fetch, and how you want to fetch the steps. They are all defined as our constants, if you remember, and that's what this function is all about. So we define that function. We will be calling that in our training method. All right. So from here onwards up to there, we are done with the preparation of the data and whatever functions or whatever are required. From here onwards is where the TensorFlow part starts. So the first thing we do is import the TensorFlow library. Typically, this is a very standard way of importing the library. We say import TensorFlow as TF. Now, TF is nothing but a name. So you can change it to TF1 or ABC or XYZ, whatever. So this part you can change. But by and large, everybody uses this. So I would rather recommend you also use the same syntax. So you say import TensorFlow as TF. So it's very easy for others to understand as well. And then you declare or define a bunch of constants. That's what we are doing here. Like for example, the number of time steps. In this case, it is 12. Number of neurons, there are 100. Number of outputs, it is only 1, and so on, right? And then the learning rate and all that we are declaring or defining those variables in this particular block. Next is to create placeholders. You remember the placeholders are used for feeding the data. So we have X and Y. X is for the input, which is the independent variable, and Y is the output, which is the dependent variable. And in our case, these are not different characteristics or features, but it is the same one feature or one variable, but it is over a period of time. So that's the only difference. So that's what we are doing here. And now we need to create our network, right? The neural network. So in our case, we said we will create a RNN layer. Now there are different ways or different formats of RNN, which is probably not in scope of this module. So for now, we will just assume we are creating one RNN layer, and one type of RNN is GRU cell. So we will use GRU cell, and we use this APIs for creating our layer. So each cell will be with an output projection wrapper. There is a need for doing that. And again, the details of this we will probably do in another video where we talk in detail about RNN. So for now, we are creating a GRU cell with the wrapper, and the syntax for creating the GRU cell is like this. The number of units, which we said there should be 100 neurons. What will be the activation function? In this case, it is ReLU, and then number of outputs. In our case, it is only 1. Okay, so we create the cell here. Okay, then we got the GRU cell, and then we say what is our output, which is nothing but we get the outputs and the states and their states, and which is the way we get that is tf.nnn.dynamic_rnn. So if we call this and we pass the cell and the data, which is basically in placeholder. So again, remember, all we are doing here is we are creating just the nodes for the graph. So nothing is actually getting executed from a TensorFlow perspective. Okay. All right. So once that is done, now we need to pass this, calculate the outputs and the states using the dynamic_rnn method, and we pass the cell as a parameter and then the x values as a parameter. And if we run that, we will have the outputs and the states. And this is where we actually run the training method. So, or create, not really run the training method, but we create the nodes for the training and the optimizer. Then we have the initialization of the variables, and we save this model. We create a saver object just to save the model, because we will then restore it and run it to do our predictions. So this is what we will do here. So that is another node, and this is where we actually create a session and run the training. Okay, so let's go ahead and do that. That will take a little while because we said 4,000 iterations. So we will allow it to finish. We will probably come back once the training is completed. All right, so the training is done. Now let's go and run this on the test data. So let's just quickly take a look at the test data set. So this is our 1 year data for the year of 1975. So if we see this is from January, February, and so on. And we will pass this to our model. So what are we doing here? We are restoring the model here, for example, right? This is the path that we have given when we were saving the model. Let's go go back once and show you, let me show you where we did the saving of the model. Yes, so we save the model here. So that again, we will restore that and we will use that to run it on our test data and see how well it predicts. So let's go ahead and run this. And this is just 12 records, so this will not take time. Remember, I told you training is what takes a lot of time. The regular inference, this is called inference, doesn't take much time, right? So it just depends on how much data. There were only 12 records here, so it was very quick. But in training, what we do, we pass this multiple times. There are iterations, 4,000 iterations we did, for example. So that takes longer. And in general, in machine learning, deep learning, training is what takes the maximum amount of time. All right, so let's go ahead and see the results. We will, in order to plot it, we will have to kind of adjust the format of the results. Otherwise, we will not be able to see it in a proper way. And then we will, so this is our, so what we have done is we created a data frame which consists of the predicted value and the actual value. So this is the data frame. So this is the actual value, this 834, 782 and so on. This is what our model has predicted. So it may not be so easy to see in a tabular format. So let's go ahead and plot it so that we can compare these two. So when we plot it, you will see that the trend is more or less maintained, right? So we go from the blue color is the actual values and the yellow color or the orange color, whatever is it, is the one which is generated by our model. So it pretty much is following the actual trend. So not bad for such a quick iteration and training.
This tutorial is about object detection. We will walk you through a TensorFlow code using which we will do object detection in images. We will tell you what are the libraries that are required, a little bit about the COCO dataset, and then we will show you the implementation code itself, a demo of the code. Alright, so let's get started. So what is the TensorFlow Object Detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO dataset, COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. It might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically we will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading this images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available and it will be shown in the other video, and frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that. And actually the information about that is provided in the cards, the eye symbol. So that's the video object detection in video. That's the separate tutorial. Alright, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there is something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. And in this video I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries. For example, NumPy, we need image.io, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. Alright, and then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. Alright, and then here onwards we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one, because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells, we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. So things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is here, once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. I'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic_annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically pick up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video reader, video_reader, has a neat little feature or interface whereby you can say for frame in video_reader. So it will basically provide frame by frame. So you are in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is a cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here. It is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. Thank you very much for watching this video.
Hey there learner, Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
In this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little, the MNIST database is a nice little database that has images of handwritten digits, nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation. And all of them are labeled. So you have the images and their label. And these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28. So there are 784 pixels. So pixel number 1 starts here. It goes all the way up to 28. Then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay. So in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0. This is at position 1, position 2, and so on and so forth. Let's say this is position 7. Then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay. So one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1. Therefore, we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay. So that is the significance of this one hot true. All right. And then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values. So you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set, there are 10,000, and then validation, there are 5,000. So altogether, there are 70,000 images. All right. So let's move on, and we can view the actual image by using the matplotlib library. And this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are remember, these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 708. So each of these inputs needs to be multiplied with a weight. And that's what we are talking about here. So this is a matrix of 784 values for each of the neurons. And so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned bias is only one per neuron, so it is not one per input, unlike the weights. So therefore, there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of 3 different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have 3 different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use, and reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low because it will, in that case, it will take very long. So you define the optimizer and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. The first, we have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. And we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, this 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices. So each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron. So there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of x into w, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the y value is basically the label value. So this is another placeholder. We had x as one placeholder and y underscore true as a second placeholder, and this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use a softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session. Right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code. You have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500, depending on the size of your system and so on and so forth. So in this case, we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnest function here. So we are saying mnest train.next batch. Right? So this is the advantage of using mnest database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using mnest database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously, it will not be 100% accurate. Okay. So once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data and you're trying to find out what is the actual value and what is the predicted value and seeing whether they are equal or not, tf.equal, right? And how many of them are correct and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy. and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Hey there, learner. Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
We're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials, because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlaid, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it uses useful for calculating derivatives by using back propagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense. Your layer 1 has an activation. They're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other. So it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And he uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the 2 complex models coming in. We have our image inputs, which is a 32 by 32 by 3, or 3 channels, or 4 if you're having an alpha channel. You have your dense, your layers, dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals Keras, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda, and I'll open that up and open up a Jupyter Notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Datalore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs. Where the Notebook will work fine for what we're doing. And this opens up in our browser window, because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras Tutorial. And let's change that to a capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn, or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I and range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And then we go ahead and just run that. And so once we've created our random data, and you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we could do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. Then we go ahead and scale the scaled trained samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, because there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network. But the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection, and then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow cross metrics for categorical cross entropy, so we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story, how good does your model do? And we'll go ahead and load all that, and then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, and I'm going to explain that in just a second, we have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be your input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it, like an artist. You start getting a feel for like a inverse tangent activation, or the tan-H activation. Takes up a huge processing amount, so you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out. So that you can do you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up, I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually, the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, And we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to, they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the NumPy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of setup on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, Here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with a true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the cross standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling 2D. This again is how do we deal with the images and pooling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model. Again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work. So you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train test split classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup and TensorFlow above. The path, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. we have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the negative 4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. Now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember I just flashed that at you, it had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values, are not actual numbers. if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train, split, test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, share it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a mobile net v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we're going to we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten. So we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and is processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout? The dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs, and we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before, not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there, and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y, where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is, and to do that we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. 3 people are going to sneak into this door who are without a mask and that thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just save the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model, make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did the, only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, so we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. So it's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart. or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame, setup. Again, the face, the CVT color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously, you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our facenet, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions, and the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location, because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label. no mask, we can create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running. And we can see the data coming down here. And we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95, 98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask? Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
Then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below.
So what are generative adversarial networks? Generative adversarial networks, or GANs, introduced in 2014 by Ian J. Goodfellow and co-authors, became very popular in the field of machine learning. GAN is an unsupervised learning task in machine learning. It consists of two models that automatically discover and learn the patterns in input data. The two models, called generator and discriminator, compete with each other to analyze, capture, and copy the variations within a dataset. GANs can be used to generate new examples that possibly could have been drawn from the original dataset. In the image below, you can see that there is a database that has real 100 rupee notes. The generator, which is basically a neural network, generates fake 100 rupees notes. The discriminator network will identify if the notes are real or fake. Let us now understand in brief about what is a generator. A generator in GANs is a neural network that creates fake data to be trained on the discriminator. It learns to generate plausible data. The generated instances become negative training examples for the discriminator. It takes a fixed length random vector carrying noise as input and generates a sample. Now the main aim of the generator is to make the discriminator classify its output as real. The portion of the GAN that trains the generator includes a noisy input vector, the generator network, which transforms the random input into a data instance, a discriminator network which classifies the generated data, and a generator loss, which penalizes the generator for failing to dolt the discriminator. The backpropagation method is used to adjust each weight in the right direction by calculating the weight's impact on the output. The backpropagation method is used to obtain gradients, and these gradients can help change the generator weights. Now, let us understand in brief what a discriminator is. A discriminator is a neural network model that identifies real data from the fake data generated by the generator. The discriminator's training data comes from two sources. The real data instances such as real pictures of birds, humans, currency notes, etc. are used by the discriminator as positive samples during the training. The fake data instances created by the generator are used as negative examples during the training process. While training the discriminator, it connects with two loss functions. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. In the process of training the discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real data instance as fake or a fake data instance as real. Now moving ahead, let's understand how GANs work. Now GANs consists of two networks, a generator which is represented as G of X and a discriminator which is represented as D of X. They both play an adversarial game where the generator tries to fool the discriminator by generating data similar to those in the training set. The discriminator tries not to be fooled by identifying fake data from the real data. They both work simultaneously to learn and train complex data like audio, video, or image files. Now you are aware that GANs consists of two networks, a generator G of X and discriminator D of X. Now the generator network takes a sample and generates a fake sample of data. The generator is trained to increase the probability of the discriminator network to make mistakes. On the other hand, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 and 1. Here is an example of a generative adversarial network trying to identify if the 100 rupee notes are real or fake. So first, a noise vector or the input vector is fed to the generator network. The generator creates fake 100 rupee notes. The real images of 100 rupee notes stored in a database are passed to the discriminator along with the fake notes. The discriminator then identifies the notes and classifies them as real or fake. We train the model, calculate the loss function at the end of the discriminator network, and backpropagate the loss into both discriminator and generator. Now the mathematical equation of training a GAN can be represented as, you can see here. Now this is the equation and these are the parameters. Here G represents generator, D represents the discriminator. Now P data of X is the probability distribution of real data, P of Z is the distribution of generator, X is the sample of probability data of X, Z is the sample size from P of Z, D of X is the discriminator network, and G of Z is the generator network. Now the discriminator focuses to maximize the objective function such that D of X is close to 1 and Z of Z is close to 0. It simply means that the discriminator should identify all the images from the training set as real, that is 1, and all the generated images as fake, that is 0. The generator wants to minimize the objective function such that D of Z of Z is 1. This means that the generator tries to generate images that are classified as real, that is 1, by the discriminator network. Next, let's see the steps for training a neural network. So we have to first define the problem and collect the data. Then we'll choose the architecture of GAN. Now depending on your problem, choose how your GAN should look like. Then we need to train the discriminator on real data. Now that will help us predict them as real for n number of times. Next, you need to generate fake inputs for the generator. After that, you need to train the discriminator on fake data to predict the generated data as fake. Finally, train the generator on the output of discriminator. With the discriminator predictions available, train the generator to fool the discriminator. Let us now look at the different types of GANs. So first we have vanilla GANs. Now vanilla GANs have min-max optimization formula that we saw earlier, where the discriminator is a binary classifier and is using sigmoid cross entropy loss during optimization. In vanilla GANs, the generator and the discriminator are simple multi-layer perceptrons. The algorithm tries to optimize the mathematical equation using stochastic gradient descent. Up next, we have deep convolutional GANs or DC GANs. Now DC GANs support convolutional neural networks instead of vanilla neural networks at both discriminator and generator. They are more stable and generate higher quality images. The generator is a set of convolutional layers with fractional strided convolutions or transpose convolutions, so it unsamples the input image at every convolutional layer. The discriminator is a set of convolutional layers with strided convolutions, so it downsamples the input image at every convolutional layer. Moving ahead, The third type we have is conditional GANs or CGANs. Vanilla GANs can be extended into conditional models by using an extra label information to generate better results. In CGAN, an additional parameter called Y is added to the generator for generating the corresponding data. Labels are fed as input to the discriminator to help distinguish the real data from fake data generated. Finally, we have super resolution GANs. Now, SR GANs use deep neural networks along with adversarial neural network to produce higher resolution images. Super resolution GANs generate a photorealistic high resolution image when given a low resolution image. Let's look at some of the important applications of GANs. So with the help of DC GANs, you can train images of cartoon characters for generating faces of anime characters and Pokemon characters as well. Next, GANs can be used on the images of humans to generate realistic faces. The faces that you see on your screens have been generated using GANs and do not exist in reality. Third application we have is GANs can be used to build realistic images from textual descriptions of objects like birds, humans, and other animals. We input a sentence and generate multiple images fitting the description. Here is an example of a text-to-image translation using GANs for a bird with a black head, yellow body, and a short beak. The final application we have is creating 3D objects. So GANs can generate 3D models using 2D pictures of objects from multiple perspectives. GANs are very popular in the gaming industry. GANs can help automate the task of creating 3D characters and backgrounds to give them a realistic feel.
Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in, so it takes that graphic and puts it into the input layer. You have all your hidden layers, and then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist, so we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer, ReLU is how that is pronounced, and that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN. What is convolution neural network? How CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for. And you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here, you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now, obviously, when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges. It might be looking for different parts. We'll cover that a little bit more detail in a minute. Right now, we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, it's going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, when we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here, it's turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving one over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel, and we just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value. A little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image. And then it skips over and says, I see a 3 in this image. And it says, oh, this one is rated as a 4. We don't want to sum it together because then, you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data, and so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image, and if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there that is looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant two-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it. And then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird. But we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the images using Matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but Matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember Matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape. We're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let's just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the Matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. Let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self-all train batches. So we're going to make an array of all those different images. And then, of course, we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a numpy array vstack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a numpy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where you say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case, I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we've set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self-I plus batch size because the self-I is going to keep changing. And then finally, we increment the self-I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the CFAR helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch to set up the next batch, as we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float64 to float type, or is treated as an NP float64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals TF placeholder TF float32. We just talked about the float64 versus the NumPy float. We're actually just going to keep this at float32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder TF float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our conversional 2D, our max pool, so we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it. And of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes. And then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2, or whatever it is, that's what goes into the pooling, of what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally, we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here, we're going to create our normal full layer. So at some point, we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out and create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2 by 2, and we put in the convolutional 1 that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so it knows to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling. And then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat. And then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and Graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. And the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf dot equal tf argument y prediction 1, tf dot arg max y true 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF-cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.0, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. And you can see we finished with this model at 0.5135, so still good. And if we look at when they ran this on the other end, remember there's a lot of randomness that goes into it when we see the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We've trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. What's in it for you? We will start with, of course, the fundamentals. What is a neural network and popular neural networks? It's important to know the framework we're in and what we're going to be looking at specifically. Then we'll touch on why a recurrent neural network, what is a recurrent neural network, and how does an RNN work. One of the big things about RNNs is what they call the vanishing and exploding gradient problem. So we'll look at that. And then we're going to be using a use case study. It's going to be in Keras on TensorFlow. Keras is a Python module for doing neural networks in deep learning. And in there's what they call long short-term memory, LSTM. And then we'll use the use case to implement our LSTM on the Keras. So when you see that LSTM, that is basically the RNN network. And we'll get into that. The use case is always my favorite part. Before we dive into any of this, we're going to take a look at what is an RNN, or an introduction to the RNN. Do you know how Google's autocomplete feature predicts the rest of the words a user is typing? I love that autocomplete feature. As I'm typing away, it saves me a lot of time. I can just kind of hit the enter key and it autofills everything, and I don't have to type as much. Well, first there's a collection of large volumes of most frequently occurring consecutive words. This is fed into a recurrent neural network. Analyzes the data by finding the sequence of words occurring frequently and builds a model to predict the next word in the sentence. And then Google, what is the best food to eat in Las, I'm guessing you're going to say Las Mexico. No, it's going to be Las Vegas. So the Google search will take a look at that and say, hey, the most common autocomplete is going to be Vegas in there. And usually it gives you 3 or 4 different choices. So it's a very powerful tool. It saves us a lot of time, especially when we're doing a Google search, or even in Microsoft Words has some people get very mad at it because it autofills with the wrong stuff. But you know, you're typing away and it helps you autofill. I have that in a lot of my different packages. It's just a standard feature that we're all used to now. So before we dive into the RNN and getting into the depths, let's go ahead and talk about what is a neural network. Neural networks used in deep learning consist of different layers connected to each other and work on the structure and functions of a human brain. You're going to see that thread, human brain and human thinking, throughout deep learning. The only way we can evaluate an artificial intelligence or anything like that is to compare it to human function. Very important note on there. And it learns from huge volumes of data, and it uses complex algorithms to train a neural net. So in here we have image pixels of 2 different breeds of dog. One looks like a nice floppy-eared lab, and one a German Shepherd. You know, both wonderful breeds of animals. That image then goes into an input layer. That input layer might be formatted at some point, because you have to let it know, like, you know, different pictures are going to be different sizes and different color content. Then it'll feed into hidden layers. So each of those pixels, or each point of data, goes in and then splits into the hidden layer, which then goes into another hidden layer, which then goes to an output layer. RNN, there's some changes in there which we're going to get into. So it's not just a straightforward propagation of data like we've covered in many other tutorials. And finally you have an output layer, and the output layer has 2 outputs. It has one that lights up if it's a German Shepherd, and another that lights up if it's a Labrador. So it identifies the dog's breed. Such networks do not require memorizing the past output. So our forward propagation is just that. It goes forward and it doesn't have to rememorize stuff. And you can see there, that's not actually me in the picture, dressed up in my suit. I haven't worn a suit in years. So as we're looking at this, we're going to change it up a little bit. Before we cover that, let's talk about popular neural networks. First, there's the feed-forward neural network, used in general regression and classification problems. And we have the convolution neural network, used for image recognition. Deep neural network, used for acoustic modeling. Deep belief network, used for cancer detection. And recurrent neural network, used for speech recognition. Now, taken a lot of these and mixed them around a little bit, so just because it's used for one thing doesn't mean it can't be used for other modeling. But generally this is where the field is, and this is how those models are generally being used right now. So when we talk about a feed-forward neural network, in a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the y and the h value are connected to each other. They're not necessarily the same value because h can be its own thing. And usually we draw this, or we represent it as a function. H of t equals a function of c, where h of t minus 1, that's the last h output, and x of t going in. So it's the last output of h combined with the new input of x, where ht is the new state, fc is a function with the parameter c, that's a common way of denoting it, ht minus 1 is the old state coming out, and then x of t is an input vector at time of step t. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike. So we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers. make those smaller. And finally is the gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is as you look at these layers, not only does the propagate through the first layer, goes into the second layer, back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f the h at t minus 1, and then x at t, plus, of course, you have a bias in there with any of your neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are two parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the two formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John. awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network so it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective, John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network based on the stock price data between 2012 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window. And then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here. And then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look and start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, the first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas as PD. And when I hit Run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with. The evaluate is the next biggest piece. So the actual code here, crossed is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.iLocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, or the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code, and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here we're going to pull it up from the sklearn or the skKit pre-processing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100 and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we're telling it's going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scalar, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object. We'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is the scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the ytrain. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60 since that's the value over here, and it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded two arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199. And we're making sure that that is shaped correctly. So the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers. And so the end layer needs to be one value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal, we're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the cue, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here, let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them, so let me go ahead and put all 3 of them in, and then we can go back over them. Here's the second one, and let's put 1 more in. Oops, put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in, and then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer. the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train, we have our source of data and the answers we know so far that we're going to put in there. We've reshaped that, we've come in and built our Keras, we've imported our different layers, and we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RN into the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in. For the X-train, our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because it's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. Alright, so we have epoch. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epochs. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epoch pretty close since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set test iLocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test and we're going to load that in. And then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat. And we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2. But we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works. Because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally we want to go ahead and take our X test, and we're going to create that X test, and for I in range 60 to 80. So here's our X test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our X test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final two lines, and here we have something new. Right here on these last two lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts X test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red, so it's going to be in bright red. We're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph, I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this.
Then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below.
Graphs. So computational graphs are really the heart and soul of neural networks. We talk about a computational graph. They are a visual representation of expressing and evaluating mathematical equations. The nodes and data flow in a graph correspond to mathematical operations and variables. You'll hear a lot, some of the terms you might hear are node and edge, the edge being the data flow in this case. It could also represent an actual value. They have, I think in Spark they have a graph X, which works just on computing edges. There's all kinds of stuff that has evolved from computational graphs. We're focusing just on Keras and on neural networks. So we're not going to go into great detail on everything a computational graph does. It is a core component of a neural network is what's important to know on this. So Keras offers a Python user-friendly front end while maintaining a strong computation power by using a low-level API like TensorFlow, PyTorch, etc., which use computational graphs as a backend. So one, this allows for abstraction of complex problems while specifying control flow. If you've ever looked at some of the backend or the original versions of TensorFlow, it's really a nightmare. You have all these different settings you have to put in there and create. It's a lot of back-end programming. This is like the old computers when you had to tell it how to dispose of a variable and how to properly reallocate the memory for use. All that is covered nowadays in our higher level programming. Well, this is the same thing with Keras, is it covers a lot of this stuff and does things for you that you could spend hours on just trying to figure out. It's useful for calculating derivatives by using backpropagation. We're definitely not going to teach a class on derivatives in this little video, but understanding a derivative is the rate of change. So if you have a particular function you're using in your neural network, a lot of them is just simple y equals mx plus b, your Euclidean geometry where you just have a simple slope times the intercept. And they get very complicated. They have the inverse tangent function for activation as opposed to just a linear Euclidean model. And you can think about this as you have your data coming in and you have to alter it somehow. Well, you alter it going down to get an answer, you end up with an error, and that error goes back up, and you have to have that back propagation with the derivative. You want to know how it changed so that you can figure out how to adjust it for the error. A lot of that's hidden, so you don't even have to worry about it with Keras. And in today's Keras, it'll even, if you create your own formula for computing an answer, it will automatically compute the derivative for you in a lot of cases. It's easier to implement distributed computation. So Keras is a really nice way to package it and get it off on different computers and share it. And it allows parallelism, which means that two operations can run simultaneously. So as we start developing these backends, it can do all kinds of cool things and utilize multiple cores, GPUs on a computer to get that parallel processing up. What are neural networks? Well, like I said, there are already, we talked about in computational edges, you have a node and you have a connection, or your edge. So neural networks are algorithms fashioned after the human brain, which contain multiple layers. Each layer contains a node called a neuron, which performs a mathematical operation. They break down complex problems into simple operations. So one, an input layer takes in our data and pre-processes it. When we talk about pre-processing, when you're dealing with neural networks, you usually have to pre-process your data so that it's between -1 and 1 or 0 and 1 into some kind of value that's usable. That occurs before it gets to the neural network. In fact, 80% of data science is usually in prepping that data and getting it ready for your different models. Two, you have hidden layer performs a nonlinear transformation of input. Now it can do a linear transformation. It can use just a basic Euclidean geometry, and you could think of a node adding all the different connections coming in. So each connection would have a weight, and then it would add to that weight plus an intercept in the node itself. So you can actually use Euclidean geometry. But a lot of these get really complicated. They have all these different formulas, and they're really cool to look at. But when you start looking at them, look at how they work. You really don't need to know the high math behind it to figure them out and figure out what they're doing, which is really cool. That means a lot of people can use this without having to go get a PhD in mathematics. Number three, the output layer takes the results from hidden layer, transforms them, and gives a final output. So sequential models. So what makes this a sequential model? Sequential models are linear stacks of layers where one layer leads to the next. It is simple and easy to implement, and you just have to make sure that the previous layer is the input to the next layer. So you have used for plain stack of layers where each layer has one input and one output, tensor, and this is what TensorFlow is named after. Is each one of these layers is like a tensor. Each node is a tensor, and then the layer is also considered a tensor of values. And it's used for simple classifier, declassifier models. It's also used for regression models too. So it's not just about this is something, this is a teapot, this is a cat, this is a dog. It's also used for generating the actual values. You know, this is worth $10, that's worth $30. The weather's going to be 90 degrees out or whatever it is. So you can use it for both classifier and declassifier models. And one more note when we talk about sequential models. The term sequential is used a lot, and it's used in different areas and different notations when you're in data science. So when we talk about time series, we'll talk about sequential. That is something very different. Sequential, in this case, means it goes from the input to layer 1 to layer 2 to the output. So it's very directional. It's important to note this because if you have a sequential model, can you have a non-sequential model? And the answer is yes. If you master the basics of a sequential model, you can just as easily have another model that shares layers. You can have another model where you have an input coming in and it splits. And then you have one set that's doing one set of nodes. Maybe they're doing a yes-no kind of node, where it's either putting out a 0 or a 1, a classifier, and the other one might be regression. It's just processing numbers, and then you recombine them for the output. That's what they call the cross API. So there's a lot of different availabilities in here, and all kinds of cool things you can do as far as encoding and decoding and all kinds of things. And you can share layers and things like that. We're just focusing on the basic cross model with the sequential model. So let's dive into the meat of the matter. Let's do a demo on here. Today's demo, in this demo, we'll be performing flower classification using sequential model in Keras. And we'll use our model to classify between 5 different types of flowers. Now, for this demo, and you can do this demo on whatever platform you want, or whatever user interface for developing Python, I'm actually using Anaconda, and then I'm using Jupyter Notebooks to develop in. And if you're not familiar with this, you can go under Environment. Once you've created an environment, you can come in here to open a terminal window. And if you don't have the different modules in here, you can do your Conda install, whatever module it is. Just happened that this particular setup didn't have a Seaborn in it, which I already installed. So here's our Anaconda, and then I'm going to go back and start up my Jupyter Notebook, where I already created a new Python project, Python 3. I'm in Python 3.8 on this particular one. Sequential model for flowers. So lots of fun there. So we're going to jump right into this. The first thing is to make sure you have all your modules installed. So if you don't have NumPy, Pandas, Matplotlib, and Seaborn in the Keras, and sklearn, or Scikit, it's not actually sklearn, you'll need to go ahead and install all of those. Now, having done this for years and having switched environments and doing different things, I get all my imports done, and then we just run it, and if we get an error, we know we have to go back and install something. Right off the bat, though, we have NumPy, Pandas, Matplotlib, Seaborn. These are built on top of each other. Pandas, the data frame, and built on top of NumPy, the data array. And then we bring in our sklearn, or Scikit. This is the Scikit setup, SCIKIT. Even though you use sklearn to bring it in, it's a Scikit. And then our Keras. We have our pre-processing the images, image data generator, our model. This is our basic model, our sequential model. And then we bring in from Keras layers, import dents, optimizers. These optimizers, a lot of them already come in. These are your different optimizers, and it's almost, a lot of this is so automatic now. Atom is a lot of times the default because you're dealing with a large data. And then we get our SGD, which is smaller data, does better on smaller pieces of data. And I'm not going to go into all of these different optimizers. We didn't even use these in the actual demo. You just have to be aware that they are different optimizers. And the more you dig into these models, you'll hit a point where you do need to play with these a little bit. But for the most part, leave it at the default when you're first starting out. And we're doing just the sequential. You'll see here layers dense. And then if we come down a little bit more, when they put this together and they're running the dense layers, you'll also see they have dropout, they have flatten, they have activation, they have the convolutional layer 2D, max pooling 2D, batch normalization. What are all these layers? And when we get to the model, we're going to talk about them. A lot of times when you're just starting, you can just import cross.layers, and then you have your dropout, your flatten, your convolutional neural network 2D. And we'll cover what these do in the actual example when we get down there. What I want you to take from here, though, is you need to run your imports and load your different aspects of this. And, of course, your TensorFlow TF, because this is all built on TensorFlow. And then finally, import random as RN, just for random generation. And then we get down here, we have our CV2. That is your open image, or your open CV, they call it, for processing images. That's what the CV2 is. We have our TQDM. The TQDM is for is a progress bar, just a fancy way of adding. When you're running a process, you can view the bar going across in the Jupyter setup. Not really necessary, but it's kind of fun to have. We want to be able to shuffle some files. Again, these are all different things. PIL is another image processor. It goes with the CV2. A lot of times you'll see both of those. And so we run those. We've got to bring them all in. And the next thing is to set up our directories. And so when we come into the directories, there's an important thing to note on here, other than we're looking at a lot of flowers, which is fun. Is when we get down here, we have our directory archive flowers. That just happens to be where the different files for different flowers are put in. We're denoting an X and a Z. And the X is the date of the image, and the Z is the tag for it. What kind of flower is this? And the image size is really important because we have to resize everything. If you have a neural network, and if you remember from our neural networks, let me flip back to that slide. When we look at this slide, we have two input nodes here. With an image, you have an input node, depending on how you set it up, for each pixel, and that pixel has 3 different color schemes usually in it, sometimes 4. So if you have a picture that's 150 by 150, you multiply 150 times 150 times 3. That's how many nodes, input layers, coming in. I mean, so this is a massive input. A lot of times you think, oh yeah, it's just a small amount of data or something like that. No, it's a full image coming in. Then you have your hidden layers. A lot of times they match what the image size is coming in. So each one of those is also just as big. And then we get down to just a single output. So that's kind of a thing to note in here, what's going on behind the scenes. And of course, each one of these layers has a lot of processes and stuff going on. And then we have our different directories on here. Let me go ahead and run that. So I'm just setting the directories. That's all this is. Archive flowers, daisy, sunflower, tulip, dandelion, rose. Just our different directories that we're going to be looking at. And then we want to go ahead and we need to assign labels. Remember, we defined X and Z. So we're just going to create a definition here. And the first thing is return flower type. Okay. Just returns it what kind of flower it is, I guess, assign the label to it. But we're going to go ahead and make our train data. And when you look at this, there's a couple things to take away from here. The first one is we're just appending right onto our NumPy array the image. We're going to let NumPy handle all that different aspects as far as 150 by 150 by 3. We just dump it right into the NumPy, which makes it really easy. We don't have to do anything funky on the processing, and we want to leave it like that. And I'm going to talk about that in a minute. And then, of course, we have to have the string, append the label on there. And I want you to notice right here, we're going to read the image in, and then we're going to size it. And this is important because we're just changing this to 150 by 150. We're resizing the image so it's uniform. Every image comes in identical to the other ones. This is something that's so important is when you're resizing or reformatting your data, you really have to be aware of what's going on. With images, it's not a big deal because with an image, you just resize it so it looks squishy or spread out or stretched. The neural network picks up on that and it doesn't really change how it processes it. So let's go ahead and run that. And now we've got our definition set up on there. And then we want to go ahead and make our training data. So make the train data daisy flower, daisy directory, print length of x. So here we go. Let's go ahead and run that. And we're just loading up the flower daisy. So this is going all in there, and it's setting, it's adding it in to our setup on there, to our x and z setup. And we see we have 769. And then, of course, you can see this nice bar here. This is the bar going across is that little added code in there that just makes it really cool for doing demos. Not necessarily when you're building your own model or something like that, but if you're going to display this to other people, adding that little, what was it called? TQDM. I can never remember that, but the TQDM module in there is really nice. And we'll go ahead and do sunflowers. And of course, you could have just created an array of these. But this has an interesting problem that's going to come up, and I want to show you something. It doesn't matter how good the people in the back are or how good you are at programming. Errors are going to come up, and you got to figure out how to handle them. And so when we get all the way down to the, where is it? Dandelion. Here's our Dandelion directory we're going to build. Jupyter has some cool things it does, which makes this really easy to deal with. But at the same time, you would want to go back in there depending on how many times you rerun this, how many times you pull this. So when you're finding errors going in here, there's a couple things you can do. And we're just going to, oh, it wasn't, there it is. There's our error. I knew there was an error. This processed 1,062 out of 1,065. Now, I can do a couple things. One, I could go back into our definition. And I can just put in here try, and so if it has a bad conversion, because this is where the error is coming from, just skip it. That's one way to do it. When you're doing a lot of work in data science and you look at something like this where you're losing 3 points of data at the end, you just say, okay, I lost 3 points. Who cares? Or you can go in there and try to delete it. It really doesn't matter for this particular demo. And so we're just going to leave that error right alone and skip over because it's already added all the other files in there. And this is a wonderful thing about Jupyter Notebook is that I can just continue on there and the X and Z, which we're creating, is still running. And we'll just go right into the next flower rows. So all these flowers are in there. That's just a cool thing about Jupyter Notebook. And then we can go ahead and just take a quick look and see what we're dealing with. And this is, of course, really, when you're dealing with other people and showing them stuff, this is just kind of fun where we can display it on the plot library here. And we're just going to go through and let's see, what do we got here? Looks like we're going to do like 5 of each of them, I think. Is that how they set this up? Plot library 5 by 2. Okay, oh, I see how they did it. Okay, so 2 each. So we have 5 by 2 set up on our axes, and we're just going to go in and look at a couple of these flowers. It's always a good thing to look at some of your data. No matter what you're doing, we've reformatted this to 150 by 150. You can see how it really blurs this one up here on the tulip. That is that resize to 150 by 150. And these are what's actually going in. These are all 150 by 150 images. You can check the dimensions on the side. And you can see just a quick sampling of the flowers we're actually going to process on here. And again, like I said at the beginning, most of your work in data science is reprocessing this different information. So we need to go ahead and take our labels and run a label encoder on there. And then we're just going to, LE is a label encoder. One of the things we imported, and then we always use the fit to categorical, y comma 5, x, here's our array, x. So if you look at this, here's our fit. We're going to transform z. That's our z array we created. And then we have y, which equals that. And then we go ahead and do to categorical. We want 5 different categories. And then we create our x, NP array of x. X equals x over 255. So what's going on here, there's 2 different transformations. One, we've turned our categories into 0, 1, 2, 3, 4, 5 as the output. And we have taken our x array. And remember, the x array is 3 values of your different colors. This is so important to understand. When we do this across a NumPy array, this takes every one of those 3 colors. So we have 150 by 150 pixels. Out of those 150 by 150 pixels, they each have 3 color arrays. And those color arrays range from 0 to 250. So when we take the x equals x over 255, range from 0 to 255, this converts all those pixels to a number between 0 and 1. And you really want to do that when you're working with neural networks. Now, if you do a linear regression model, it doesn't affect it as much, and so you don't have to do that conversion if you're doing straight numbers. But when you're running neural networks, if you don't do this, you're going to create a huge bias. And that means they'll do really good on predicting 1 or 2 things, and they'll just totally die on a lot of other predictions. So now we have our x and y values. X being the data in, y being our known output. And with any good setup, we want to divide this data into our training. So we have x train, we have our x test. This is the data we're not going to program the model with. And of course your y train corresponds to your x train, and your y test corresponds to your x test, the outputs. And this is, when we do the train test split, this was from the scikit, sklearn. We imported train test split. And we're just going to go ahead and do the test size at about a quarter of the data, 0.25. And of course, random's always good. This is such a good tool. I mean, certainly you can do your own division. You could just take the first, 0.25 of the data or whatever, do the length of the data. Not real hard to do, but this is randomized so that if you're running this test a few times, you can kind of get an idea whether it's going to work or not. Sometimes what I will do is I'll just split the data into 3 parts, and then I'll test it on 2, with one being I'll train it on 2 of those parts, with one being the test, and I rotate it. So I come up with 3 different answers, which is a good way of finding out just how good your model is. But for setting up, let's stick with the xtrain, xtest, and the sklearn package. And then we're going to go ahead and do a random seed. Now, a lot of times the cross actually does this automatically, but we're going to go ahead and set it up on here. And you can see we did an NP random seed from 42, and we get a nice RN number. And then we do TF random, we set the seed. So you can set your randomness at the beginning of your TensorFlow. And that's what the tf.random.set is. So that's a lot of prep. All this prep, and then we finally get to the exciting part. This is where you probably spend, once you have the data prepped and you have your pipeline going and you have everything set up on there, this is the part that's exciting, is building these models. And so we look at this model. One, we're going to designate it as sequential. They have the API, which is the Keras TensorFlow API versus sequential. Sequential means we're going one layer to the next. So we're not going to split the layer and bring it back together. It looks almost the same with the exception of bringing it back together. So it's not a huge step to go from this to an API. And the first thing we're going to look at is our convolutional neural network in 2D. So what's going on here? There's a lot of stuff that's going on here. The default for, well, let's start with the beginning. What is a convolutional 2D network? Well, a convolutional 2D network creates a number of small windows, and those small windows float over the picture, and each one of them is their own neural network, and it's basically becomes like a categorization. And then it looks at that and it says, oh, if we add these numbers up a certain way, we can find out whether this is the right flower based on this little window floating around, which looks at different things. And we have filters 32. So this is actually creating 32 windows, is what that's doing. And the kernel size is 5 by 5. So we're looking at a 5 by 5 square. Remember, it's 150 by 150. So this narrows it down to a 5 by 5. It's a 2D, so it has your x, y coordinates. And when we look at this 5 by 5, remember each one of these is actually looking at 5 by 5 by 3. So we're actually looking at 15 by 15 different pixels. And padding is just, usually I just ignore that. Activation by default is ReLU. We went ahead and put the ReLU in there. There's a lot of different activations. ReLU is for your smaller, remember I mentioned Atom. When you have a lot of data use an Atom kind of activation, or use an Atom processing. We're using the ReLU here. It kind of gives you a yes or no, but it doesn't give you a full yes or no. It has a 0 and then it kind of shoots off at an angle. Very common. It's the most common one. And then of course here's our input shape, 150 by 150 by 3 pixels. And then we have to pool it. So whenever you have a convolutional 2D layer, we have to bring this back together and pool this into a neural network. And then we're going to go ahead and repeat this. So we're going to add another network here. One of the cool things, if you look at this, is that as it comes in, it just kind of automatically assumes you're going down to the next layer. And so we have another convolutional neural network, 2D. Here's our max pooling again. We're going to do that again, max pooling. And we're just going to filter on down. Now, one of the things they did on this one is they changed the kernel size, they changed the number of filters, and so each one of these steps kind of looks at the data a little bit differently. And that's kind of cool because then you get a little added filtering on there. This is where you start playing with the model. You might be looking at a convolutional neural network, which is great for image classifications. When we get down to here, one of the things we see is flatten. So we just flatten it. Remember, this is 150 by 150 by 3. Well, and actually the pool size changes, so it's actually smaller than that. Flatten just puts that into a 1D array. So instead of being, a tensor of this really complexity with the pixels and everything, it's just flat. And then the dense is just another activation on there. By default, it is probably ReLU as far as this activation. And then, oh yeah, here we go. In sequential, they actually added the activation as ReLU. So this because this is sequential, this activation is attached to the dense. And there's a lot of different activations, but ReLU is the most common one. And then we also see a softmax. Softmax is similar, but it has its own kind of variation. And one of the cool things, you know what? Let me bring this up because if you don't know about these activations, this doesn't make sense. And I just did a quick Google search on images of TensorFlow activations. I should probably look at which website this is. But this is the output of the values. So as it adds in all those weighted x values going into the node, it's going to activate it a certain way. And that's a sigmoid activation. And you can see it goes between 0 and 1 and has a nice curve there. This also shows the derivatives. And if we come down, the 7 popular activation functions, nonlinear activations, there's a lot of different options on this. Let me see if I can find the... Oops, let me see if I can find the specific to ReLU. So this is a leaky ReLU. And you can see instead of it just being 0 and then a value between going up, it has a little leaky there. Otherwise, your ReLU loses some nodes. They just become inactive. But you can see there's a lot of different options here. Here's a good one right here with the ReLU. You can see the ReLU function on the upper left here. And then the leaky ReLU over here on the right, which is very commonly used also. One of the things I use with processing language is the exponential one or the tangent H, the hyperbolic tangent, because they have that nice funky curve that comes in that has a whole different meaning and captures word use better. Again, these are very specific to domain, and you can spend a lot of time playing with different models. For our basic model, we'll stick to the ReLU and the softmax on here, and we'll go ahead and run and build this model. So now that we've had fun playing with all these different models that we can add in there, we need to go ahead and have a batch size on here. 128, epochs 10. This means that we're going to send 128 rows of data or flowers at a time to be processed. And the epochs 10, that's how many times we're going to loop through all the data. Reduce the values, and verbose equals 1 means that we're going to show what's going on. Value, monitor what we're monitoring. We'll see that as we actually train the model. This is what's going to come out of there. If you set the verbose equal to 0, you don't have to watch it train the model, although it is kind of nice to actually know what's going on sometimes. And since we're still working on bringing the data in, here's our batch side, here's our epochs, we need to go ahead and create a data generator. This is our image data generator, and it has all the different settings in here. Almost all of these are defaults. So if you're looking at this going, oh my gosh, this is confusing, most of the time you can actually just ignore most of this. Vertical flip, so you can randomly flip pictures, you can randomly horizontally flip them. You can shift the picture around. This kind of helps, gives you multiple data off of them. Zooming, rotation, there's all kinds of different things you can do with images. Most of these we're just going to leave as false. We don't really need to do all that setup because we already have a huge amount of data. If you're short data, you can start flipping like a horizontal picture and it will generate, it's like doubling your data almost. So the upside is you double your data. The downside is that if you already have a bias in your data, you already have 5,000 sunflowers and only 2 roses, that's a huge bias. It's also going to double that bias. That is the downside of that. And so we have our model compile, and this you're going to see on all the Keras. We're going to take this model here, we're going to take all this information as far as how we want it to go, and we're going to compile it. This actually builds the model, and so we're going to run that. And I want you to notice learning rate, very important. This is the default 001. You really don't. This is how slowly it adjusts to find the right answer. And the more data you have, you might actually make this a smaller number. If you have a very small sample of data, you might go even larger than that. And then we're going to look at the loss, categorical cross entropy, most commonly used. And this is how much it improves. The model's improving is what this number means. Or yeah, that's important on there. And then the accuracy. We want to know just how good our model is on the accuracy. And then one of the cool things to do is if you're in a group of people who are studying the model, if you're in shareholders, you don't want to do this, is you can run the model summary. I do this by default, and you can see the different layers that you built into this model. Just a quick summary on there. So we went ahead and we're going to go ahead and create a, we'll call it history, but we want to do a model fit generator. And so what this history is doing is this is tracking what's going on while it fits the model. Now there's a lot of new setups in here where they just use fit and then you put the generator in here. We're going to leave it like this, even though the new default is a little different on that. Doesn't really matter, it does the same thing. And we'll go ahead and just run that. And you can see while it's running right here, we're going through the epochs. We have 1 of 10, now we're going through 6 to 25. Here's our loss. We're printing that out so you can see how it's improving, and our accuracy. The accuracy gets better and better. And this is 6 out of 25. This is going to take a couple minutes to process because we are training 150 by 150 by 3 pixels across 6 layers or 8 layers, whatever it was. That is a huge amount of processing, so this will take a few minutes to process. This is when we talk about the hardware and the problems that come up in data science and why it's only now just exploding being able to do neural networks. This is why. This process takes a long time. Now you should have seen a jump on the screen here because I did pause the recorder to let this go ahead and run all the way through its epochs. Let's go ahead and take a look and see what these epochs are. And if you set the verbose to 0 instead of 1, it won't show what's going on in the behind the scenes as it's training it. So when we look at this epic, 10 epics, we went through all the data 10 times. If I remember correctly, there's roughly a gig of data there, so that's a lot of data. The first thing you're going to notice is the 270 seconds. That's how much each of those epics took to run. And so if you divide 60 in there, you roughly get about 5 minutes worth of each epic. So if I have 10 epics, that's 50 minutes, almost an hour of runtime. That's a big deal when we talk about processing. On this particular computer, I actually have, 8 cores with 16 dedicated threads. So it runs like a 16-core computer. It alternates the threads going in. And it still takes it 5 minutes for each one of these epics. So you start to see that if you have a lot of data, this is going to be a problem if you have a number of models. You want to find out how good the models are doing and what model to use. And so each of those models could take all night to run. In fact, I have a model I'm running now that takes about a day and a half to test each model. It takes 4 days to do the whole data. So what I do is I actually take a small piece of the data, test it out to find out, get an idea of how the different setups are going to do, and then I increase that size of the data and then increase it again, and I can just take that curve and kind of say, okay, if the data is doing this, then I need to add in more dense layers or whatever. So you can do a small chunks of data and then figure out what it costs to do a large set of data and what kind of model you want. The loss, as we see here, continues to go down. This is the error. This is how much error is in there. It really isn't a user-friendly number, other than the more it trends down, the better. And so if you continue to see the loss going down, eventually you'll get to the point where it stops going down and it goes up and down and kind of wavers a little bit. At that point, you know you've run too many epics. You're starting to get a bias in there, and it's not going to give you a good model fit. The accuracy just turns this into something that we can use. And so the accuracy is what percentage of guesses, in this case it's categorical, so this is the percentage of guesses are correct. Value loss is similar, it's a minus a value loss. And then you have the value accuracy, and you'll see the value accuracy is pretty similar to the accuracy, just rounds it off basically. And so a lot of times you come down here and you go, okay, we're doing 0.5, 0.6, 0.7, and that is 70% accuracy, or in this case 68.59% accuracy. And that's a very usable number, and it's very important to have. If you're identifying flowers, that's probably good enough if you can get within a close distance and knowing what flower you're identifying. If you're trying to figure out whether someone's going to die from a heart attack or not, you might want to rethink it a little bit, or rekey how you're building your model. So if I'm working with a group of clients, shareholders in a company or something like that, you don't really want to show them this. You don't want to show them, hey, this is what's going on with the accuracy. These are just numbers. And so we want to go ahead and put the finishing touches, just like when you are building a house and you put in the frame and the trim on the house. It's nice to have a nice view of what's going on. And so we'll go ahead and do a pie plot, and we'll just plot the history of the loss, the history of the value loss over here. Epics, train, and test. And so we're just going to compute these. This is really important. And what I want you to notice right here is when we get to about 5 epics, a little more than 5, 6 epics, you see a crossover here. And it starts crossing as far as the value loss. And what's going on here is you have the loss in your actual model and your actual data, and you have the value loss where it's testing it against the test data. The data wasn't used to program your model, wasn't used to train your model on. And so when we see this crossing over, this is where the bias is coming in. This is becoming overfitted. And so when you put these two together, right around 5 and 6, you start to see how it does this switch over here. And that's really where you need to stop, right around 5, 6. It's always hard to guess, because at this point the model's kind of a black box. But you know that right around here, if you're saving your model after each run, you want to use the one that's right around 5 epics, because that's the one that's going to have the least amount of bias. So this is really important as far as guessing what's going on with your model and its accuracy and when to stop. It also is, I don't show people this mess up here. I I show somebody this kind of model and I say, this is where the training and the testing comes in on this model. It just makes it easier to see and people can understand what's going on. So that completes our demo, and you can see we did what we were set out to do. We took our flowers and we were able to classify them within about 68-70% accuracy, whether it's going to be a dahlia, sunflower, cherry blossom, rose. A lot of other things you can do with your output as far as different tables to see where the errors are coming from and what problems are coming up. And we're going to take a look at image classification using Keras and the basic setup. And we'll actually look at two different demos on here. What's in it for you today? What is image classification? Intel image classification data, creating neural networks with Keras, and the VGG16 model. What is image classification? The process of image classification refers to assigning classes to an entire image. Images can be classified based on different categories like whether it is a nighttime or daytime shot, what the image represents, etc. And you can see here we have mountains looking for mountains. We'll actually be doing some pictures of scenery and stuff like that. In deep learning, we perform image classification by using neural networks to extract features from images and classifies them based on these features. And you can see here where it says like what computer sees, and it says, oh yeah, we see mostly forest, maybe a little bit of mountains because of the way the image is. And this is really where one of the areas that neural networks really shines. If you try to run this stuff through more like a linear regression model, you'll still get results, but the results kind of miss a lot of things as the neural networks get better and better at what they do with different tools we have out there. So Intel image classification data. The data being used is the Intel image classification data set, which consists of images of 6 types of land areas. And so we have forest, building, glaciers, and mountains, sea, and street. And you can see here there's a couple of the images out of there as a setup in the Intel image classification data that they use. And then we're going to go into creating a neural networks with Keras. The convolutional neural network that we are creating from scratch looks as shown below. You can see here we have our input layer. They haven't listed max pooling. So you have, as you're coming in with the input layer, and the input layer is actually before this, but the first layer that it's going to go into is going to be a convolutional neural network. Then you have a max pooling that pulls the convolutional neural network's returns. In this case, they have 2 of those. That is very standard with convolutional neural networks. One of the ones that I was looking at earlier that was standard being used by one of the larger companies, I can't remember which one, for doing a large amount of identification, had 2 convolutional neural networks, each with their max pooling, and then about 17 dense layers after it. We're not going to do that heavy duty of a code, but we'll get you headed in the right direction. And that gives you an idea of what you're actually going to be looking at when you look at the flattened part and then the dense. We're talking like 17 dense layers afterwards. I find that a lot of the stuff I've been working on, I end up maxing it out right around 9 dense layers. It really depends on what you have going in and what you're working with. And the VGG16 model. VGG16 is a pre-trained CNN model which is used for image classification. It is trained on a large, varied data set and fine-tuned to fit image classification data sets with ease. And you can see down here we have the input coming in, the convolutional neural network 1-to-1, 1-to-2, and then pooling. And then we do 2-to-1, 2-to-2 convolutional neural network, then pooling, 3-to-2, and you can see there's just this huge layering of convolutional neural networks. And in this case, they have 5 such layers going in, and then you have 3 dense going out, or more. Now, when they took this setup, this actually won an award back in 2019 for this particular setup. And it does really good, except that, again, we only show the 3 dense layers here. And as you find out, depending on your data going in and what you have set up, that really isn't enough on one of these setups. And I'm going to show you why we restricted it, because it does take up a lot of processing power in some of these things. So let's go ahead and roll up our sleeves, and we're going to look at both the setups. We're going to start with the first classification, and then we'll go into the VGG16 and show you how that's set up. Now I'm going to be using Anaconda, and let me flip over to my Anaconda so you can see what that looks like. Now I'm running in the Anaconda here. You'll see that I've set up a main Python 3.8. I always put that in there because this is where I'm doing like most of my kind of playing around. This is done in Python version 3.8. We're not going to dig too much into versions. At this point you should already have Keras installed on there. Usually Keras takes a number of extra steps. And then our usual setup is the NumPy, the pandas, your scikit, which is going to be the sklearn, your Seaborn, and I'll show you those in just a minute. And then I'm just going to be in the Jupyter Lab where I've created a new notebook in here. And let's flip on over there to my blank notebook. Now, there's a couple cool things to note in here is that, one, I use the Anaconda Jupyter Notebook setup because it keeps everything separate, except for Keras. Keras is actually running separately in the back. I believe it's a C program. What's nice about that is that it utilizes the multiprocessors on the computer, and I'll mention that just in a little bit when we actually get down to running the code. And when we look in here, the couple things to note is here's our oops, I thought I grabbed the other drawing thing. But here's our NumPy and our pandas right here and our operating system. This is our scikit. You always import it as sklearn for the classification report. We're going to be using, well, usually import like Seaborn brings in all of your PyPlot library also. Kind of nice to throw that in there. I can't remember if we're actually using Seaborn, if they just, the people in the back just threw that together. And then we have the sklearn shuffle for shuffling data. Here's our matplotlib library that the Seaborn is pretty much built on. CV2, if you're not familiar with that, that is our image module for importing the image. And then, of course, we have our TensorFlow down here, which is what we're really working with. And then the last thing is just for visual effect while we're running this. If you're doing a demo and you're working with the partners or the shareholders, this TQDM is really kind of cool. It's an extensible progress bar for Python. And I'll show you that too. Remember, data science is not, I mean, most of this code, when I'm looking through this code, I'm not going to show half of this stuff to the shareholders or anybody I'm working with. They don't really care about pandas and all that. We do, because we want to understand how it works. So we need to go ahead and import those different setup on there. And then the next thing is we're going to go ahead and set up our classes. Now we remember if we had mountain, street, glacier, building, sea, and forest, those were the different images that we have coming in. And we're going to go ahead and just do class name labels, and we're going to kind of match that class name of I for I, class name equals the class names. So our labels are going to match the names up here. And then we have the number of classes, and print the class names and the labels. And we'll go ahead and set the image size. This is important that we resize everything, because if you remember with neural networks, they take one size data coming in. And so when you're working with images, you really want to make sure they're all resized to the same setup. It might squish them, it might stretch them. That generally does not cause a problem in these. And some of the other tricks you can do with, if you need more data, and this is one that's used regularly, we're not going to do it in here, is you can also take these images and not only resize them, but you can tilt them one way or the other, crop parts of them, so that they process slightly differently. And it'll actually increase your accuracy of some of these predictions. And so you can see here we have mountain equals 0. That's what this class name label is. Street equals 1. Glacier equals 2. Buildings equals 3. C4. Forest equals 5. Now, we did this as an enumerator, so each one is 0 through 5. A lot of times we do this instead as 0, 1, 0, 1, 0, 1. So you have 5 outputs, and each one's a 0 or a 1 coming out. So the next thing we really want to do is we want to go ahead and load the data up. And just put a label in there, loading data. just so you know what we're doing, I'm going to put in the loading data down here. Make sure it's well labeled. And we'll create a definition for this. And this is all part of your pre-processing. At this point, you could replace this with all kinds of different things depending on what you're working on. And once you download, you can go download this data set, send a note to the Simplilearn team here in YouTube, and they'll be happy to direct you in the right direction. And make sure you get this path here, so you have the right, wherever you saved it. A lot of times I'll just abbreviate the path or put it as a sub thing and just get rid of the directory. But again, double check your paths. We're going to separate this into a segment for training and a segment for testing. And that's actually how it is in the folder. And let me just show you what that looks like. So when I have my lengthy path here where I keep all my programming Simplilearn, this particular setup we're working on, image classification and image classification. Clearly you probably wouldn't have that lengthy of a list. And when we go in here, you'll see sequence train, sequence test. They've already split this up. This is what we're going to train the data in. And again, you can see buildings, forest, glacier, mountain, sea, street. And if we double click, let's go under forest. You can see all these different forest images. And there's a lot of variety here. I mean, we have wintertime, we have summertime. So it's kind of interesting. You know, here's like a fallen tree versus a road going down the middle. That's really hard to train. And if you look at the buildings, a lot of these buildings, you're looking up a skyscraper, we're looking down the setup. Here's some trees with one. I want to highlight this one. It has trees in it. Let me just open that up so you can see it a little closer. The reason I want to highlight this is I want you to think about this. We have trees growing. Is this the city or a forest? So this kind of imagery makes it really hard for a classifier. And if you start looking at these, you'll see a lot of these images do have trees and other things in the foreground, weird angles. Really a hard thing for a computer to sort out and figure out whether it's going to be a forest or a city. And so in our loading of data, one, we have to have the path, the directory. We're going to come in here, we have our images and our labels. So we're going to load the images in one section, the labels in another. And if you look through here, it just goes through the different folders. In fact, let me do this. There we go. As we look at this, we're just going to loop through the 6 different folders that have the different landscapes. And then we're going to go through and pull each file out and each label. So we set the label, we set the folder for file and list. Here's our image path, join the paths. This is all kind of general stuff, so I'm kind of skipping through it really quick. And here's our image setup. If you remember, we're talking about the images. We have our CV2 reader, so it reads the image in. It's going to go ahead and take the image and convert it to from blue, green, red to red, green, blue. This is a CV2 thing. Almost all the time it imports it, and instead of importing it as a standard that's used just about everywhere, it imports it with the BGR versus RGB. RGB is pretty much a standard in here. You have to remember that was CV2. And then we're going to go ahead and resize it. This is the important part right here. We've decided what the size is, and we want to make sure all the images have the same size on them. And then we just take our images and we're just going to append the image, append the label, and then the images is going to turn into a numpy array. This just makes it easier to process and manipulate. And then the labels is also a numpy array. And then we just return the output, append images and labels, and we return the output down here. So we've loaded these all into memory. We haven't talked much. There'd be a different setup in there because there is ways to feed the files directly into your cross model. But we want to go ahead and just load them all because it's really for today's processing and what our computers can handle, that's not a big deal. And then we go ahead and set the train images, train labels, test images, test labels, and that's going to be returned in our output append. And you can see here we did images and labels set up in there, and it just loads them in there, so we'll have these 4 different categories. Let me just go ahead and run that. So now we've gone ahead and loaded everything on there. And then if you remember from before, we imported, let me just go back up there, Shuffle. Here we go. Here's our sklearn utilities import Shuffle. And so we want to take these labels and shuffle them around a little bit, just mix them up so it's not having the same, if you run the same process over and over, then you might run into some problems on there. And just real quick, let's go ahead and do a plot so we can just, we've looked at them as far as from outside of our code. We pulled up the files and I showed you what that was going on. We can go ahead and just display them here too. And I tell you, when you're working with different people, this should be highlighted right here. This thing is like when I'm working on code and I'm looking at this data and I'm trying to figure out what I'm doing, I skip this process. The second I get into a meeting and I'm showing what's going on to other people, I skip everything we just did. So, and go right to here where we want to go ahead and display some images and take a look at it. And in this display, I've taken them and I've resized the images to 20 by 20. That's pretty small. So we're going to lose just a massive amount of detail. And you can see here these nice pixelated images. I might even just stick with the folder showing them what images we're processing. Again, this is, you gotta be a little careful of this. Maybe resizing it was a bad idea. In fact, let me try it without resizing it and see what happens. Oops. So I took out the image size and then we put this straight in here. One of the things, again, this is, put the D, there we go. One of the things, again, that we want to note whenever we're working on these things is the CV2, there are so many different image classification setups. It's really a powerful package when you're doing images. But you do need to switch it around so that it works with the PyPlot. And so make sure you take your NumPy array and change it to a uinteger8 format because it comes in as a float. Otherwise, you'll get some weird images down there. And so this is just basically we've split up, or we've created a plot. We went ahead and did the plot 20 by 20, or the plot figure size is 20 by 20. And then we're doing 25, so a 5 by 5 subplot. Nothing really going on here too exciting, but you can see here where we get the images. And really, when you're showing people what's going on, this is what they want to see. So you skip over all the code and you have your meeting, you say, okay, here's our images of the building. Don't get caught up in how much work you do, get caught up in what they want to see. So if you want to work in data science, that's really important to know. And this is where we're going to start having fun. Here's our model. This is where it gets exciting when you're digging into these models. And you have here, let me get, there we go. When you have here, if you look here, here's our convolutional neural network 2D. And 2D is an image. You have two different dimensions, X, Y, and even though there's 3 colors, it's still considered 2D. If you're running a video, you'd be convolutional neural network 3D. If you're doing a series going across, a time series, it might be 1D. And on these, you need to go ahead and have your convolutional neural network. If you look here, there's a lot of really cool settings going on to dig into. We have our input shape, so everything's been set to 150 by 150. And it has, of course, 3 different color schemes in it. That's important to notice. Activation default is ReLU. This is small amounts of data being processed on a bunch of little neural networks. And right here is the 32. That's how many of these convolutional neural networks are being strung up on here. And then the 3 by 3, when it's doing its steps, it's actually looking at a little 3 by 3 square on each image. And so that's what's going on here. And with convolutional neural networks, the window floats across and adds up all these numbers going across on this data. And then eventually it comes up with 30, in this case, 32 different feature options that it's looking for. And of course, you can change that 32. You can change the 3 by 3, so you might have a larger setup. And, if you're going across 150 by 150, that's a lot of steps. So we might run this as 15 by 15. There's all kinds of different things you can do here. We're just putting this together. Again, that would be something you would play with to find out which ones are going to work better on this setup. And there's a lot of play involved. That's really where it becomes an art form, is guessing at what that's going to be. The second part I mentioned earlier, and I can only begin to highlight this. When you get to these dense layers, one is the activation is a ReLU. They use a ReLU and a softmax here. It's a whole setup just explaining why these are different. And how they're different, because there's also an exponential, there's a tangent. In fact, there's just a ton of these, and you can build your own custom activations depending on what you're doing. A lot of different things go into these activations. There are 2 or 3 major thoughts on these activations, and ReLU and softmax are, ReLU, you're really looking at just the number, you're adding all the numbers together, and you're looking at Euclidean geometry. AX plus BX2 plus CX3 plus bias. With softmax, this belongs to the party of it's activated or it's not, except they call it softmax because when you get to 0, instead of it just being 0, it's actually a little bit less than 0, so that when it trains, it doesn't get lost. There's a whole series of these activations. Another activation is the tangent, where it just drops off and you have like a very narrow area where you have from -1 to 1, or exponential, which is 0 to 1. So there's a lot of different ways to do the activation. Again, that would be a whole separate lesson on here. We're looking at the convolutional neural network, and we're doing the 2 pools. This is so common. You'll see two convolutional neural networks stacked on top of each other, each with its own max pool underneath. And let's go ahead and run that. So we built our model there, and then we need to go ahead and compile the model. So let's go ahead and do that. We are going to use the Atom optimizer. The bigger the data, the Atom fits better on there. There's some other optimizer, but I think Atom's a default. I don't really play with the optimizer too much. That's like once you get a model that works really good, you might try some different optimizers, but Atom's usually the most. And then we're looking at loss. Pretty standard. We want to minimize our loss. We want to maximize the loss of error. And then we're going to look at accuracy. Everybody likes to say accuracy. I'm going to tell you right now, I start talking to people and I'm like, okay, what's the loss on this and that? And as a data science, yeah, I want to know how what's going on with that, and we'll show you why in a minute. But everybody wants to see accuracy. They want to know how accurate this is. And then we're going to run the fit. And I wanted to do this just so I can show you, even though we're in Python setup in here where Jupyter Notebook is using only a single processor, I'm going to bring over my little CPU tool. This is 8 cores on 16 dedicated threads, so it shows up as 16 processors. And actually, I got to run this and then move it over. So we're going to run this, and hopefully it doesn't destroy my mic. And as it comes in, you can see it's starting to go through the epochs. And I set it for 5 epochs. And then this is really nice because Keras uses all the different threads available. So it does a really good job of doing that. This is going to take a while. If you look at here, it's ETA 2 minutes and 25 seconds, 24 seconds. So this is roughly 2.5 minutes per epoch. and we're doing 5 epochs. So this is going to be done in roughly 15 minutes. I don't know about you, but I don't think you want to sit here for 15 minutes watching the green bars go across. So we'll go ahead and let that run. And there we go. There was our 15 minutes. It's actually less than that because I did, when I went in here, realized that, where was it? Here we go. Here's our model compile. Here's our model fit. And here's our epochs. So I did 4 epochs. So a little bit better, a little more like 10 to 11 minutes instead of doing the full 15. And when we look at this, here's our model. We talked about the compiler. Here's our history. We're going to history equals the model fit. We'll go into that in just a minute. And what we're looking at is we have our epochs. Here's our validation split. So as we train it, we're weighing the accuracy versus, you kind of pull some data off to the side while you're training it. And the reason we do that is that you don't want to overfit. And we'll look at that chart in just a minute. Here's batch size. This is just how many images you're sending through at a time. The larger the batch, it actually increases the processing speed. And there's reasons to go up or down on the batch size because of the smaller the batch. There's a certain point where you get too large of a batch and it's trying to fit everything at once. So 128 is kind of big. Depends on the computer you're on and what it can handle. And then of course we have our train images and our train labels going in, telling it what we're going to train on. And then we look at our 4 epochs here. Here's our accuracy. We want the accuracy to go up, and we get all the way up to 0.83 or 83%. This is actual percentage based pretty much. And we can see over here our loss. We want our loss to go down. It really fluctuates. 55, 1.2, 0.77, 0.48. So we have a lot of things going on there. Let's go ahead and graph those. Turn that up. And our team in the back did a wonderful job of putting together this basic plot setup. Here's our subplot coming in. We're going to be looking at, from the history, we're going to send it the accuracy and the value accuracy labels and set up on there. And we're going to also look at loss and value loss. So you can see what this looks like. What's really interesting about this setup, and let me just go ahead and show you, because without actually seeing the plots, it doesn't make a whole lot of sense. It's just basic plotting of the data using the PyPlot library. And I want you to look at this. This is really interesting. When I ran this the first time, I had very different results, and they vary greatly. And you can see here our accuracy continues to climb. And there's a crossover here. Put it in here. Right here's our crossover. And I point that out because as we get to the right of that crossover where our accuracy, and we're like, oh yeah, I got 0.8%, we're starting to get an overfit here. That's what this switchover means. As our value, as a training set versus the value accuracy stays the same. And so that this is the one we actually really want to be aware of, and where it crosses is kind of where you want to stop at. And we can see that also with the train loss versus the value loss right here. We did 1 epoch, and look how it just flatlines right there with our loss. So really, 1 epoch is probably enough. And you're going to say, wow, okay, 0.8%. Certainly if I was working with the shareholders, telling them that it has an 80% accuracy isn't quite true. And we'll look at that a little deeper. It really comes out here that the accuracy of our actual values is closer to 0.41% right here, even after running it this number of times. And so you really want to stop right here at that crossover. 1 epoch would have been enough. So the data is a little overfitted on this when we do 4 epochs. And, oops, there we are. Okay. My drawing won't go away. Let me see if I can get, there we go. For some reason, I've killed my drawing ability and my recorder. All right, took a couple extra clicks. So let's go ahead and take a look at our actual test loss. So you see where it crosses over. That's where I'm looking at. That's where we start overfitting the model. And this is where, if we were going to go back and continually upgrade the model, we would start taking a look at the images and start rotating them. We might start playing with the convolutional neural network instead of doing the 3x3 window. We might expand that, or find different things that might make a big difference as far as the way it processes these things. So let's go ahead and take a look at our test loss. Now remember, we had our training data. Now we're going to look at our test images and our test labels for our test loss here. And this is just model evaluate, just like we did fit up here. Where was it? One more. Model fit with our training data going in. Now we're going to evaluate it on the, and this data has not been touched yet. So this model's never seen this data. This is on completely new information as far as the model is concerned. Of course, we already know what it is from the labels we have. And this is what I was talking about. Here's the actual accuracy right here, 0.48 or 4847. So this 49% of the time guesses what the image is. And I mean, really, that's the bottom dollar. Does this work for what you're needing? Does 49% work? Do we need to upgrade the model more? In some cases, this might be, what was I doing? I was working on stock evaluations, and we were looking at what stocks were the top performers. Well, if I get that 50% correct on top performers, I'm good with that. That's actually pretty good for stock evaluation. In fact, the number I had for stock was more like 30-something% as far as being a top performer stock. Much harder to predict. But at that point, you're like, well, you'll make money off of that. So again, this number right here depends a lot on the domain you're working on. And then we want to go ahead and bring this home a little bit more as far as looking at the different setup in here. And one of the, from Simplilearn, if you remember, actually let's go back to the top, we had the classification report. And this came in from our Simplilearn or scikit setup. And that's right here. You can see it right here on the, see, there we go. Classification report right here. Simplilearn metrics, import classification report. That's what we're going to look at next. A lot of this stuff depends on who you're working with. So when we start looking at precision, this is like for each value. I can't remember what one was probably mountains. So if 44% is not good enough, if you're doing like you're in the medical department and you're doing cancer, is this cancerous or not? And I'm only 44% accurate. Not a good deal. I would not go with that. So it depends on what you're working with on the different labels and what they're used for. Facebook, 44% on guessing the right person. I would hope it does a little bit better than that. But here's our main accuracy. This is what almost everybody looks at. They say, oh, 48%, that's what's important. Again, it depends on what domain you're in and what you're working with. And now we're going to do the same model. Oops, somehow I got there it goes. I thought I was going to get stuck on there again. This time we're going to be using the VGG16. And remember, this one has all those layers going into it. So it's basically a bunch of convolutional neural networks getting smaller and smaller on here. And so we need to go ahead and import all our different stuff from Keras. We're importing the main one is the VG16 setup on there. Just aim that, there we go. There's kind of a pre-processing images, applications, pre-process input. This is all part of the VGG16 setup on there. And once we have all of those, we need to go ahead and create our model. And we're just going to create a VGG16 model in here, inputs, model inputs, outputs, model inputs. I'm not going to spend as much time as I did on the other one. We're going to go through it really quickly. One of the first things I would do is, if you remember in Keras, you can treat a model like you would a layer. And so at this point, I would probably add a lot of dense layers on after the VGG16 model and create a new model with all of those things in there. And we'll go ahead and run this because here's our model coming in and our setup. And it'll take it just a moment to compile that. Hey, what's funny about this is I'm waiting for it to download the package. Since I pre-ran this, it takes it about a couple minutes to download the VGG16 model into here. And so we want to go ahead and train features for the model. We're going to predict the train images, and we're going to test features on the predict test images on here. And then I told you I was going to create another model too, and the people in the back did not disappoint me. They went ahead and did just that. And this is really an important part. This is worth stopping for. I told you I was going to go through this really quick. So here's our, we have our model 2 coming in. And we've created a model up here with the VGG16, model equals model inputs, model inputs. And so we have our VGG16. This has already been pre-programmed. And then we come down here. I want you to notice on this right here, model 2 layers -4 to 1, x layer x. We're basically taking this model and we're adding stuff onto it. And so we've just basically duplicated this model. We could have done the same thing by using model up here as a layer. We could have had the input go to this model and then have that go down here. So we've added on this whole setup, this whole block of code from 13 to 17 has been added on to our VGG16 model. And we have a new model with the layer, input, and x down here. Let's go ahead and run that and compile it. And that was a lot to go through right there. When you're building these models, this is the part that gets so complicated that you get stuck playing in, and yet it's so fun. It's like a puzzle. How can I loop these models together? And in this case, you can see right here that the layers, we're just copying layers over and adding each layer in. This is one way to build a new model. And we'll go ahead and run that. Like I said, the other way is you can actually use the model as a layer. I had a little trouble playing with it. Sometimes when you're using the straight model over, you run into issues. And it seems like it's going to work, and then you mess up on the input and the output layers. There's all kinds of things that come up. Let's go ahead and do the new model. We're going to compile it. Again, here's our metrics: accuracy, sparse categorical loss. Pretty straightforward, just like we did before. You got to compile the model. And just like before, we're going to create a history. The history is going to be new model fit train 128. And just like before, if you remember when we started running this stuff, we're going to have to go ahead and it's going to light up our setup on here. And this is going to take a little bit to get us all set up. It's not going to just happen in a couple minutes. So let me go ahead and pause the video and run it, and then we'll talk about what happened. Okay, now when I ran that, these actually took about 6 minutes each. So it's a good thing I put it on hold. We did 4 epochs. Actually, I had to stop it because it was at 10 and switch it to 4 because I didn't want to wait an hour. And you can see here our accuracy and our loss numbers going down. And just at a glance, it actually performed, if you look at the accuracy, 0.2658. So our accuracy is going down, or 26%, 34%, 35%. And you can see here at some point it just kind of kicks the bucket. Again, this is overfitting. That's always an issue when you're running on programming these different neural networks. And then we're going to go ahead and plot the accuracy history. We built that nice little subroutine up above, so we might as well use it. And you can see it right here. There's that crossover again. And if you look at this, look how the red shifts up, how our loss functions and everything crosses over. We're overfitting. After one epoch, we're clearly not helping the problem or doing better. It's just gonna baseline. This one actually shows with the training versus the loss, value loss. Maybe second epoch. So on here, we're now talking more between the first and the second epoch, and that also shows kind of here. So somewhere in here, it starts overfitting. And right about now, you should be saying, something went wrong there. I thought that when we went up here and ran this, look at this. We have the accuracy up here is hitting that 48%, and we're down here. You look at the score down here, that looks closer to 20%, not nearly anywhere in the ballpark of what we're looking for. And we'll go ahead and run it through the actual test features here. And there it is. We actually run this on the unseen data and everything, 0.18 or 18%. I don't know about you, but I wouldn't want, at 18%, this did a lot worse than the other one. I thought this was supposed to be the super model, the model that beats all models, VGG16 that won the awards and everything. Well, the reason is that one, we're not pre-processing the data, so it needs to be more. There needs to be more as far as like rotating the data at 45-degree angle, taking partials of it, so you can create a lot more data to go through here. And that would actually greatly change the outcome on here. And then we went up here, we only added a couple dense layers. We added a couple convolutional neural networks. This huge pre-trained setup is looking for a lot more information coming in as far as how it's going to train. And so this is one of those things where I thought it would have done better. And I had to go back and research it and look at it and say, well, why didn't this work? Why am I getting only 18% here instead of 44% or better? And that would be why, is it doesn't have enough training data coming in. And again, you can make your own training data. So it's not that we have a shortage of data, it's that some of that has to be switched around and moved around a little bit. And this is interesting right here too. If you look at the precision, we're getting it on number 2, and yet we had 0 on everything else. So for some reason, it's not seeing the different variables in here. So it'd be something else to look in and try to track down. And that probably has to do with the input. But you can see right here, we have a really good solid 0.48 up here. And that's where I'd really go with, is starting with this model. And then we look at this model and find out, why are these numbers not coming up better? Is it the data coming in? Where's the setup on there? And that is the art of data science right there, is finding out which models work better and why.
Now, let's talk about our first deep learning project. We have image classification using the CIFAR-10 dataset. Now, this dataset was created by the Canadian Institute for Advanced Research. The CIFAR-10 dataset contains 60,000 32x32 color images in 10 different classes. The 10 different classes are airplanes, cars, birds, cats, deer, and others, which you can see on the screen. There are 6,000 images of each class. Now there are 50,000 training images and 10,000 test images. You can build a convolutional neural network model using the Keras library to classify each image into a category. So it is more of an image recognition kind of a project that is recommended for beginners who are new to deep learning. The next project in our list is brain tumor detection. Such projects are heavily used in the healthcare industries for detecting diseases before they occur. Brain tumors are the consequence of abnormal growths and uncontrolled cell division in the brain. They can lead to death if they are not detected early and accurately. Brain tumors can be classified into 2 types, benign and malignant. Deep learning can help radiologists in tumor diagnostics without invasive measures. A deep learning algorithm that has achieved significant results in image segmentation and classification is the convolutional neural network. It can be used to detect a tumor through brain using magnetic resonance imaging or MRI. Image pixels are first fed as input to the CNN. Softmax fully connected layers are used to classify the images. The accuracy of the convolutional neural network can be obtained with the radial basis function classifier. Next, we have Anna chatbot. Now this chatbot is the world's first open source conversation platform which comes with a graphical chart flow designer and chat simulator. Its supported channels are WebChat, Android, iOS and Facebook Messenger. The Anna chatbot is available to answer your questions 24 hours a day, 365 days a year. Anna is free for personal and commercial use. With the Anna Studio, server, simulator and SDK, which is software development kit, your development time is cut from days to hours. Using Anna, you can create chatbots to suit your needs. Chatbots play an important role in customer support for an e-commerce website. You can share real-time order and shipping updates, personalized product recommendations, and targeted offers within the conversation. Similarly, automobile brands, showrooms, and service centers can use a chatbot for lead generation, scheduling test drives, and roadside assistance. You can check the GitHub repository that's on the screen to know more about working on this project. The next project we have in deep learning is image captioning. Now, image captioning is the process of generating textual description of an image. It uses both methods from computer vision to understand the content of the image and a language model from the field of natural language processing to turn the understanding of the image into words in the right order. Microsoft has built its own caption bot where you can upload an image or the URL of an image and it will display the textual description of the image. On the screen, you can see we have the picture of Elon Musk, and the caption bot has generated a description that says, "I think it's Elon Musk wearing a suit and a tie, and he seems..." It ends with an emoticon. Another such application that suggests a perfect caption and best hashtags for a picture is Caption AI. Automatic image caption generation software can be built using recurrent neural networks and long short-term memory networks or LSTMs. Now, we have image colorization as our next project. Image colorization has seen significant advancements using deep learning. Image colorization is the process of taking an input of a grayscale image and then producing an output of a colored image or a colorized image. Colorization is a highly undetermined problem that requires mapping a real valued luminance image to a three-dimensional colored value one that has not a unique solution. ChromaGAN is an example of a picture colorization model. A generative network is framed in an adversarial model that learns to colorize by incorporating perceptual and semantic understanding of color and class distributions. The model is trained using a fully supervised strategy. If you want to implement ChromaGAN, check the GitHub link that's on the screen below. Next in our list of projects we have OpenNMT machine translation. OpenNMT is an open source ecosystem for neural machine translation and neural sequence learning. It started in December 2016 by the Harvard NLP Group and Sistran. The project has since been used in several research and industry applications. Neural machine translation or NMT is a new methodology for machine translation that has led to significant improvements, particularly in terms of human evaluation, compared to rule-based and statistical machine translation systems. OpenNMT provides implementations in two popular deep learning frameworks, PyTorch and TensorFlow. Please feel free to refer to the below GitHub link to learn more about neural machine translation. Now, we have music generation. Using deep learning, it is possible for a machine to learn the notes, structures and patterns of music and start producing music automatically. Music 21 is a Python toolkit used for computer-aided musicology. It allows us to teach the fundamentals of music theory, generate music examples and study music. The toolkit provides a simple interface to acquire the music notation of MIDI files, which stands for Musical Instrument Digital Interface. Using WaveNet architecture and long short-term memory networks, you can generate music without human intervention. Amper Music, MuBut, and JukeDeck produce smart music powered by deep learning algorithms. Then we have AlphaGo. Now AlphaGo was created by Google DeepMind and is the first computer program to defeat a professional human Go player. AlphaGo's algorithm uses a combination of machine learning and tree search techniques combined with extensive training both from human and computer play. It uses Monte Carlo tree search guided by a value network and a policy network both implemented using deep neural network technology. AlphaGo was initially trained to mimic human play by attempting to match the moves of expert players from recorded historical games. It was done using a database of around 30 million moves. Once it had reached a certain degree of proficiency, by being set to play large number of games against other instances of itself, using reinforcement learning to improve its play. Next in our list of projects we have DeepDream. DeepDream is a computer vision program which uses a convolutional neural network to find and enhance patterns in images via algorithmic pareidolia. It then creates a dream-like hallucinogenic appearance in the overprocessed images. DeepDream is an experiment that visualizes the patterns learned by a neural network. Similar to when a child watches clouds and tries to interpret random shapes, DeepDream overinterprets and enhances the patterns it sees in an image. Do check the given GitHub link to install dependencies listed in the notebook and play with the code locally. Then we have Deep Voice. Deep Voice was developed by Baidu, which is an AI system that can clone an individual's voice. The trained model takes just 3 seconds to replicate the output of a person's voice. Deep Voice 3 is a fully convolutional attention-based neural text-to-speech system that converts text to spectrograms or other acoustic parameters to be used with an audio waveform synthesis method. Below you can find the GitHub link for PyTorch implementation of convolutional networks based text-to-speech synthesis models. Now we have IBM Watson. IBM Watson helps run machine learning models anywhere across any cloud. Using IBM Watson machine learning, you can build analytical models and neural networks trained with your own data that you can deploy for use in applications. With its open, extensible model operation, Watson machine learning helps businesses simplify and harness AI at scale across any cloud. It is used in healthcare, teaching assistant, chatbot, as well as for weather forecasting. And finally, in our list of deep learning projects, we have the YOLO real-time object detection. You Only Look Once, or YOLO, is a state-of-the-art real-time object detection system. It frames object detection in images as a regression problem to spatially separated bounding boxes and associated class probabilities. Using this approach, a single neural network divides the image into regions and predicts bounding boxes and probabilities for each region. The neural network predicts bounding boxes and class probabilities directly from full images in one evaluation. The base YOLO model processes images in real time at 45 frames per second. You can use the COCO dataset and TensorFlow library to train and test the model. To learn more about YOLO object detection, check the GitHub link that's shown on the screen below.
Then accelerate your career in AI and ML with our comprehensive postgraduate program in artificial intelligence and machine learning. So enroll now and unlock exciting AI and machine learning opportunities. The link is mentioned in the description box below.
Deep learning interview questions. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. Then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, it used the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with two of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off. True, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent h function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, it used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data in your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool. But in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is what is a cost function that we're going to cover. This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function C equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error if we're training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it, because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training, and part of your data is for testing, and then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do your initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. And this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation, is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function. not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network, and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture, so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the convolutional neural network. Wonderful tutorial. Check that out and learn a lot more about the convolutional neural network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now, if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in, and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they give us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Maybe we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason, it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars. Might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there, and if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the convolution neural network, the CNN, you'd have to go to another video to review. The ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back 1. We looked at that here, where it transforms to numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units. How many hidden layers are you going to have, and how many nodes in each layer? Learning rate. Learning rate is usually multiplied once you've figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change. Otherwise, you're going to have a biased model. So you only take some little incremental changes. And that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low. You can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago. That's what the learning rate was. Training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned Epic, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one Epic run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next time you go through an epic data training. So each time you go through one epic, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the side and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epic. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck, or only Ford trucks, because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN, convolutional neural network? First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so you can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you can see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features. And it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8. pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here is we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of t-1, and the hidden layer, that's what the H stands for, hidden layer of t, and the formula is going in. As we can see here, we have the hidden layers. We have t-1 and then h of t, where t stands for time. So this is a series. Remember, working with series, and we want to remember the past. And you can see you have your input of t, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your x of t plus 1. So when you have that coming in, then you have your h value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them. We might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 dtype tf float 32, or b equals the tf variable minus 3 comma dtype float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run b comma feed dictionary equals a 3.0. Print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger fake wine shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are two main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
And with that, we have come to the end of this deep learning full course for beginners by Simplilearn. I hope you found it valuable and entertaining. Please ask any questions about the topics covered in this video in the comment box below, and a team of experts will assist you in addressing your problems as soon as possible. So thank you so much for being here today. We'll see you next time. Until then, Keep learning and stay tuned to Simplilearn for more amazing updates.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.